In today's world, data is everywhere, but the real power comes from turning that data into intelligent decisions. From recommendation systems to fraud detection and self-driving systems, machine learning is already shaping the future of every industry. With that being said, I welcome you all to this session on machine learning with Python full course. Before I begin our session, just a quick info guys. If you want to build a strong career in AI and machine learning, then Simplilearn offers an advanced professional certificate course in generative AI and machine learning, designed in collaboration with AICTE Consortium of IIT Kanpur and powered by industry partners like Microsoft Azure. This program includes live online classes, hands-on projects, expert mentorship, and career support, helping you move from fundamentals to real-world AI applications. Now, coming back to the course. In this course, we will learn how to use Python for machine learning from scratch to advanced levels. We are going to start with Python refresher and maths and statistics. Then we are going to move into data processing and exploratory data analysis. After that, we are going to explore core machine learning concepts like supervised, unsupervised, regression, classification, clustering, model evaluation techniques. We will also understand advanced areas like deep learning with TensorFlow and Keras, NLP, reinforcement learning, and real-world ML project building. And finally, we are going to apply everything through hands-on industry projects like sales prediction, customer analysis, recommendation systems, and predictive modeling. By the end of this course, you will not just understand machine learning, but you'll also be able to build real intelligent systems using Python.
Okay, till now, the responses of 5 participants, I have no experience in machine learning, only one. I have some knowledge of machine learning, but don't use it regularly. That is 2 participants. So 3. We have more participants here, right? We have got 6 participants. So, okay, 1 is still pending. Okay. 2 more responses pending, people. Can I have the 2 responses, please? Servina. Okay. You have filled it. Okay. And did we miss out on any participant here? We should have 5 responses at least. Anyone who did not record the responses? I actively work in machine learning 1. I have no experience in machine learning 1 and I have some knowledge. So we have got 1 participant who does not have any exposure to machine learning. The remaining, we have all the participants are already aware of machine learning. That is good. Beginner, only 1, and intermediate, 3. Okay, that makes it easier. Now let us go down. Fresher 1, IT 1, operations 1, product management 4. Okay, that is from the domain you all are coming from. What is the primary goal? Acquiring skills and knowledge to get in certified 1. Helping area growth in this domain 1. Theory and concepts first, then practice. Okay, that is, I have got only 1 participant is okay with that. So everyone, what does the majority of the participants want? No theory and practice and concepts. See, all the algorithms, like we'll take up machine learning. Today, first session will be totally more or less theory based. Ideally going by what I see in the sheet. Okay. So first session will be totally majorly 80% theory. That is brushing up on machine learning and why do we need machine learning? What are the basic points you should be aware of when you are doing machine learning? There's some rules which you follow in machine learning. And those rules are standard rules. How the machine learns and how it predicts an outcome in the future. So there are some preset rules. Most of the participants are already aware and people who are not aware. So we'll be brushing up on the basic rules. Okay, so today's session, let me talk about the agenda today, what we are going to do today. First is we'll go through the basic rules of machine learning. What is machine learning and why do we do machine learning? What is the need of machine learning? That is the first step. Then we'll go through the standard rules which we follow when we use machine learning. Now, as most of the participants are already aware, so I prefer participants who are very new to hear out what we are discussing and what are the rules and what is the need of machine learning and all that. And then when we do hands-on, so second half, I'll try to start off with hands-on, but again, depending on the majority. If you are all okay with the theory part, I did the entire session. If I just do theory, it might be very, very boring. So we'll try to take up a bit of coding in the second half of the session. When I'm explaining the theory, I do not want to be the only one speaking. That will again make it very, very monotonous if I just show you slides and I keep on talking. So I'll appreciate if learners also help me out when I'm explaining the concepts. Going by the responses we received from this batch, most of the people are aware of machine learning, if not very proficient. And I've got 1 participant who's using it regularly. So I need more responses from the participants. Let us make it more interactive. Let us not look like a classroom where the trainer is keeping on speaking and speaking and speaking and referring to slides. Right? That will not be very interesting. So I'll need more responses and more interaction throughout the session. Second half will be totally dedicated. I'll try to start off with at least one modeling exercise once you're aware of the basic rules and the standard steps which we follow. But yes, a lot of theory and a lot of concepts to be done here. It's not very simple. If you want to avoid theory and concepts, then it will not be a great idea, specifically for machine learning, where you need to be very, very clear on the concepts. So let's start off. Before I start on, let me introduce myself. My name is Madhupurna Bhet. I have over 13 years, more than that, experience in this domain, data science domain. So I started off with analytics and then I slowly ventured into data science. I majorly have corporate experience. Over the last 2, 3 years, couple of years, I am totally into trading now. So started off with analytics, ventured into data science. So I've seen the transition happening from analytics to data science. So how this entire term changed, the programming language changed. So I have been through that transition phase when analytics was not a very popular domain at all. To this date, when you cannot think anything beyond AI. So I have been through it all from the beginning. Because I have been working with companies like TCS, Citigroup, Usha Martin Technologies, HDFC Bank, quite a vast experience in the corporates. And towards the later stage with Tech Mahindra, I started with data science. Usually I started with corporate trainings and then slowly joined Simplilearn. So I have majorly the corporate experiences more rather than the training experience. Okay, so that is all about me. Now let me take you through. Okay, now first let us start with a very basic question. Okay, why do you think you need machine learning? And I want responses from participants who are already aware of machine learning or have an idea about machine learning. Why do you think we need machine learning? Everyone has gone through the applied data science with Python course, so you know what that course aims to do, right? It prepares your data for the modeling stage. So it is all about pre-processing your data, cleaning your data to the final modeling part. So it's applied data science with Python, you have learned about dealing with the data, handling the data, exploring the data. That is what that course aims to do. Now, why do we need machine learning? Because the volume of data has been increasing manifold. Okay, whatever we used to do when I first started off, when we were into analytics, right? Then we did not have the concept of big data and data science, and all these terms were not even present the time we started working. Then it was all about analytics and insights. So we used to have the use cases, problem statements. We used to have historical data, obvious. And then we used to find out solutions to the business problem. That was our task. So ideally, we used to do the same thing which we do now, but only the name changed and that the programming language changed. We started with SAS and now we are working with R. Now there are reasons behind that. Now, why did the name change from analytics and insights to data science? Okay. The reason is only very simple, which Meghat said, big data, lots of data. So think about 15 years from now, or like past, yeah, like 15 years back, we did not have this access to internet, this easy access to internet where we are always having, always online, everyone. Now, when you see, look around, everyone is online, always fiddling with their phones. Internet is super fast, super cheap, easily accessible to everyone. Everyone have their social media profiles. Whomever you talk to, they have their social media presence. They are doing everything online. So there's a huge volume of data that has been generated today. If I look at it 15 years ago, internet was not this easily accessible. We did not have this social media presence. The online presence, the online activities were restricted. Right now, we do not. We do everything online, right? Okay. We do everything online today. Right? So a lot has changed. So basically, did the work change? No, the work did not change. The work is the same. What we used to do 15 years back, we are doing the same thing today. But yes, the volume of the data with which we used to work has changed manifold. Okay, because of the easy access to internet and more online presence. Now, because the volume of the data has increased, Now, this data has to be explored and studied to get important information. Because eventually when we do it, when we do any, say, data, when you're doing data science, naturally you're trying to solve a problem, right? Your basic objective is to solve a problem. That is what you want to do in data science. That is your task, right? That is why the clients will pay you to solve their problem. Now, when we have this huge volumes of data, and there is lots of data, so we try to explore the data, understand the data with the basic objective of getting more information from the data. And the information which we get from the data helps us to solve the problem we have in hand or to solve the business problem which we are addressing. So this data plays a very important part. So we equate data to information. Now, why this big data? The volume of data has increased over the years. Big means huge, big data. And why is data science just a nice term to give? So because everything, your entire solution to a business problem rests on the information which you get. So data is prime, data is information. And without that information, none of the business problems can be solved. So that is why it's called data science. The work remains the same. Only the volume of the data has increased. Now coming to the next part, why do we need machine learning? Well, because this huge volume of data, there is a dearth of resources. Even in today's time, you'll have many people who are transitioning from, say, IT or say engineering or say any other domain into data science, right? Where they do not have any prior exposure to statistics or say economics or say how the market works. So why this transition? Because there's a huge demand. Why this huge demand? Because there is a dearth of resources. When we started off with data science, it was called a niche skill set because it's an unusual combination, statistics, mathematics, economics. It was an unusual combination which people usually do not have. So we were called the niche skill set people, where you have very few resources of this skill set. So there is a dearth of resources who can work on data science or analytics to be specific. So you have this huge volume of data and there is a dearth of resources. And if per second, we can imagine globally what amount of data is generated, what amount of information is generated every second. With today's online presence of each and every individual accessing the internet and revealing more and more about their preferences online. And this huge information has to be accessed. The information has to be extracted and made usable to the businesses so that they can function profitably. The major challenges which any business will face is to identify who are the right customers, whether the product will do well in the market. If they have a low market share, why are they having a low market share? How can they increase the sales? These are basic questions which any business will have ideally. How can they improve from where they are standing today? And all these questions can be answered from the customers. Right? And we are the customers and we are revealing more and more information about ourselves the moment we come online. Unknowingly, we reveal more and more information about us. That information is being captured and used to the benefit of the business. Okay. Now there is a dearth of resources who can access this entire data that is generated and use the data in a form which can be beneficial to the businesses. So what do? We train a machine to do this job. Because humans have some limitations, right? Machines do not. You can keep on making a machine work on tasks which do not require a human intervention. So we train a machine to do this task so that we can access the entire volume of data, generate the information from it, and use it for the benefit of the businesses so that they can work profitably. Did you understand this? What is the need of machine learning? Yes, people. Can I have responses from the beginners? Okay, I'm not getting into all this. I think all of you know this. Identify patterns and relationships, gain insights into unknown data, take information-driven decisions. What is the purpose? When we solve a business problem, we get the insights. What are insights? The actionable items on the part of the business. So machine learning is what? The machine will learn from the historical data, which you all said from the past, and then predict the future And when we solve a business problem, we generally give some conclusions, right? You need to do this and this and this, which will help you solve the business problem. The recommendations which we give, the information which we give are called the insights, which helps the business solve the business problem they're currently facing. Those are called the insights, the information or the conclusions which we have for solving a particular business problem. Okay, now there are some machine learning terms which usually are there, but rarely we do use it. We stick to the basic terms only. So one is the inputs. Inputs are nothing but the information which is already there. Attribute is also called attributes. It's also called features. All of this mean the same thing. Whether you say it's an input, whether you say it's a feature. Feature means what? A variable. Now, when you see a data set, when you see an Excel sheet, right, you will find some columns and rows, right? A, B, C column. And then you have data. This is how a basic table looks like. 40, 50, and 80, and so on. We have data here. But 50, if I ask you what is 50, you'll need to refer to B, right? You say the value of B is 50. That will give meaning to this value. So what do I need? I need a label to understand that data. Those are nothing but the features. I did the column names. If think of a data set where you do not have column names, will you be able to understand the data? The column names, the features give meaning to the data. So those are the inputs. I did the information which we have. It is called inputs, it's called features, it's called attributes, same thing. Response is what? Whenever we are solving any business problem, we are solving for a particular value, right? When I say solve this equation, you're solving for y, right? The unknown. When I'm solving, I'm trying to find the value of something. That is my response variable. It is also called the label variable, outcome variable, target variable. So whenever we are dealing with a problem, we are trying to find out something which we do not know. That is my outcome. That is my response. That is my label. That is my target. Also called the dependent variable. Now, what are observations? The values which you have, 40, 50, 80, and so on. The actual data which we have. Those are the observations. That can be called records, that can be called examples, that can be called samples. So we do not use all these terms all together, but yes, we use some of them at times. So these are the terms which are specific to machine learning. Okay, now machine learning approach, these are the steps which you follow. We'll come to the steps towards the end. Okay, choosing the right model. Now you might think, which model am I talking about? Identify the problem type. So basically, you'll understand it once we go through the lower slides. Then we'll come back to this slide. Understand the data set and extract its features. Which are the features now here? You can see a data set which is displayed, right? Where we have a 3-column data set where I have some values. What are these? These are my observations. 16, 11. So this entire array, this 2D array is my observations or records or samples. Okay. What are the features here? Features are the input feed variables. What is response? Something which we are trying to find a value of. In this example, what are we trying to find a value of? We're trying to find the hourly rate which will be offered to an employee. We're trying to predict. It is not known to us. There's something which is done. We label it as y. Like in standard equations, y is the unknown. How do we find out the value of y? With the help of x's. Any normal equation which we have done. Simultaneous equation, straight line equation. That is how we have solved, right? We have solved for the value of y with the help of x's. So that is why we refer to the unknown quantity of the unknown value as y. Okay. We find out the value of y with the value of x. So these are my x, the known values of x. In this example, what are we doing? We are trying to find out what is the hourly rate or how much should I pay per hour to a person who has got this much years of education and who has received a professional training. So there are two inputs. I have got information on the years of education of a person, and I also have the information on whether he has received any professional training. I have both of this information. What do I have to predict? Whether the person, what amount or what is the salary I'll offer to the person, knowing his years of education and his professional training expertise per hour. That is what I have to find. What is given to me is education and professional training responses. Okay. So these two are given. So the values which are given, the information which are given, those are my x's. And what do I have to find out? That is my y, unknown or target. Okay. And the body, with the data with which I'll find out the value of y and the x's which are given to me. The entire data is my observations or the rows. Before I go to supervised and unsupervised. Data science is different from data analytics, right? DA means data analyst. Data analyst is different and data science is different. Data science is the entire, all the process we are covering. Data analyst is just dealing with the data. You work on the data. Why do you have to work on the data? You prepare the data for the final stage of modeling. You will not build predictive models or you will not use algorithms on the data. That is not what the data analyst does. The data analyst will ensure that the data is in the correct form. You can extract all the information from the data, deep dive into the data and extract important information. That is what a data analyst does. BA is different. They deal with the visualization part. When we are giving the inferences at the end, usually you'll not give the inferences saying that, okay, you need to do this, you need to do that. You'll not tell it to the business, right? Because the business will not be very technically proficient as much as you, right? And they'll not have that time. So you'll not give algorithms or you'll not show him the output. The business will not understand. So how do you have to give your insights to the business? In what way? You'll ideally go for visualizations, right? Visualizations are easy to understand. So BA deals with all this visualization. We can create basic visualizations ourselves. But what about more customized and more better visualization? BA, business analyst, they deal majorly with visualization. Every company will have their own tool for creating visualizations. Like you are already aware of Tableau, right? Tableau and Power BI. Most companies have their own tools for creating the visualization. So BA, business analyst, deal with the visualizations part or the final inferences after modeling. AI engineer is what you're doing. You're learning machine learning, then you learn deep learning, then you write generative AI. Engineering is, they know it all. The entire process they are adept with. Data engineers are different. Data engineers predominantly work on the data, on fetching the data. The data is stored in Hadoop, right? HDFS, big data. So they are more proficient with Java on how to work on the big data platform. That is data engineers. Data scientists will ideally depend on the data engineers and they have to work closely. Data engineers are responsible only for the data, not for solving a business problem. Data scientists are responsible for solving a business problem. So you'll have data engineers more proficient with Java and Hadoop. Data scientists have no knowledge there. They work with the data to give a solution. They are more proficient with Python or say SAS or say R. They are more on the analysis part. Data engineers are more on the getting the data from different multiple sources or from Hadoop, getting the data in the correct form and giving the data to the data scientist to analyze and find a solution to the problem. And BA, DA, these are totally different. Data analysts will only focus on the data. They do not work with modeling or analysis or all that part. And BA is totally in the inference part. Okay. Data scientists are people who do all the steps. Okay. Data scientist and data analyst, there is a clear difference. Data scientists will not only work on the data cleaning part, data pre-processing part, and preparing the data. They will not only work on that. They will use the data further, fit an algorithm, and find out a solution to the business problem. But when you talk about data analysts, they are only concerned with the data part, digging deep into the data, finding out important insights, finding the root cause of the problem through the data. Okay, doing a root cause analysis. Why did this problem come up? Diagnostic analysis. So all their work is centered around the data. That is data analyst. Data scientist is one step further. They will not only do that, they will also fit an algorithm, use a model, find out the solutions, whether it's working or not, and then finally generate the insights. Their scope is larger. Data scientists, data engineers, data analysts, business and scope is limited. Okay. What about Tharini? Tharini, you've joined quite late. We already have done the surveys. So is it your first time with machine learning or you're already aware of machine learning? Okay, now let us come to the types of machine learning. We have three kinds of machine learning. One is called a supervised learning. One is called unsupervised learning. And there is a third branch too, which is still work in progress, ideally. Okay. Reinforcement learning. Okay, now who will tell me what is supervised learning, people? Supervised learning is, the name is itself very self-explanatory. It says supervised learning. Supervised learning is what? There is a supervisor. That is why it's called supervised learning. You are right now doing a supervised learning. Why? Because you have a trainer explaining things to you. That is supervised learning. Where you have a person to guide you. Where you have a source which guides you towards a solution. That is called supervised learning. Now, when we talk about supervised learning, if there is a source which guides you towards a solution, that source is the supervisor. And what are you doing? You're doing a supervisor. Currently, all of you are doing a supervisor. Now, who is the supervisor here? The supervisor is the historical data. Why do we call it supervised learning? See, when we usually go for all the astrological apps which we have today, right, which predicts the future for you. We have got many astrological apps, right, which predicts future. Now, in all these astrological apps, what do you see whenever you log into any app or whenever you go to an astrologer? Say, the first question which comes up to you is, where were you born? What is your birth date? What is the place of birth? What is the time of birth? Basic questions, right? But they ask these questions about your birth details, the place where you were born, the day where you were born, the date when you were born. That is past, right? But they need all this information to understand what is going to happen to you in the future, right? So your past gives an idea of what is going to happen to you in the future. Now, similarly, think of a machine learning algorithm. It will help you predict, right, the future. So why do we have this machine learning? Why do we have this data science? Because businesses might want to know, right? What is the demand? What will be the demand for my product? Say 10 years down or 6 months later. Tell me what will be the demand for my product. So that I can plan the supply accordingly. Correct. That is a concern of a business. Now, a machine learning algorithm will help you predict or forecast the demand for a product 6 months later in the future. But how will it predict the future without knowing the past? Not possible. So you have to know the past to predict the future. And how do we know the past? That information is given to us. That is what we call historical data. Now, whenever you start off with any business problem, when we were working in analytics ideally, whatever analytics you do, with the business problem, you get some information about the business. If I do not give you any information about the business, you'll never be able to solve the problem of the business, right? You have to know how the business is functioning. Then only you can identify the loopholes. Then only you can identify the areas which needs some refinement so that the problem gets solved. But if you're not aware of the problem, of how the business has been working all the while, you'll not be able to find a solution to that problem. So it's important that you know about the past to predict the future. Why do we call it historical data? Because that is the data which tells us about what has happened in the past or how the business has been functioning all the while, so that we can dig into the data, understand how things were working in the past, and identify, do a diagnostic analysis. Okay, what might have gone wrong? Say, I'll give you an example. The sales are dropping. That is the concern of the business. And we are tasked to inform the business on the remedial steps and how to improve the sales, how to hike up the sales. So if I do not know how the business has been working in the past, I'll not be able to identify what is the reasons why the sale is dropping. First, I have to identify the reason, right? Then only I can fix that problem. How do I identify the reason? From the past information. So ideally, the past information or the historical data is serving as the supervisor or the source which will guide you towards the solution. What is the solution? You will give the insights on how to increase the sales. There might be some products which record lower sales. So pair it up with the product which records higher sales. Okay? And give the product which does not sell free with the product which sells more. Say X is selling more. Y is not sold at all. People do not buy Y at all. What will you do in pair up X and Y? Give Y for free for a certain period of time. Right? So people will go to buy X. They'll get Y for free. They'll use it. And the product is good, they'll come back and purchase it again. That is just one of the methods. But if I do not know what is the root cause of the problem, I'll not be able to solve it. Right? So we can identify that from the past information. That is my historical data. So supervised learning is all about those algorithms which can predict the future with the help of historical data, which serves as the supervisor. That is why it's called supervised learning. Okay. Now, when we have past information, we can always predict the future, right? Without past information, we cannot predict the future. So supervised learning methods help you to predict the future or forecast the future. Okay. Now, what is the difference with unsupervised learning then? In unsupervised learning, we do not have information. We do not have past information. And if we do not have past information, we can never predict the future out. Say you do not tell the astrologer what is your date of birth, what is the time of birth, and none of the details you give to the astrologer, and tell the astrologer, now tell me what is going to happen to me. The astrologer will give up and say that I cannot predict what is going to happen to you. Right? So without knowing the future, past, you cannot predict the future. So when I talk about unsupervised learning, is what lack of a supervised, lack of past information. If there is a lack of past information, I can never predict the future. That is what unsupervised learning talks about. In unsupervised learning, we cannot predict the future outcome. The maximum we can do is we can organize things. We deal with the current data and then we organize it as per our requirement. That is unsupervised learning. So we cannot build a predictive model with unsupervised learning. We can do that with supervised learning. So with unsupervised learning, no predictive model can be built. What prediction am I talking about? I'm talking about the prediction about the future. So I cannot have a predictive model with unsupervised learning. I cannot predict the future because I have no access to the past. In this case, I have access to the past, which is my supervisor. So a predictive model can be built. Okay. Now the third one is reinforcement learning. In reinforcement learning, it's very simple. It is like learning by doing. It is like learning by doing. Learning by doing means what? You have the self-driven cars. You have got AlphaGo, which is a game which is being played by a machine against a human opponent. Okay. These are all examples of reinforcement learning. Reinforcement learning happens in what way? It's learning by doing. I'll give you a small example here. Say there's a child at home who comes back home every day, and once he comes back home, he does not do the homework. The next day he goes to school. He gets a good scolding from the teacher. Okay. He comes back home that day and does the homework the second day. He goes back to school on the third day. The teacher checks his copy, sees the homework is done, and praises him. Okay, well done. The third day he comes back home. Again, he does not want to do the homework. Fourth day he goes to school. Again, the teacher checks his homework, sees it's not done. Again, gives him a sound scolding. Okay. Now the child no one is telling him that, see, you need to do the homework. But what information does the child get from the way things are working? He sees the day I do the homework, I get the teacher praises me, tells me well done. Days when I do not do the homework, I get a sound scolding from the teacher. So now he decides, okay, this is the correct way of working. I should be doing my homework. Then the teacher will praise me. If I do not do the homework, the teacher will scold me. So he learns the correct way of doing with the help of rewards or punishments. That is learning by doing. There is no supervisor there, no historical data there. It is a learning which is achieved by making mistakes and learning from the mistakes and not repeating those mistakes again. Okay? That is reinforcement learning. So a lot of work is happening in reinforcement learning. Right now we have algorithms for supervised learning and unsupervised learning. We'll focus on this too. Okay, now let us go to the next one. In supervised learning, we have got two kinds of problems. One is called regression, one is called classification. Remember, in supervised learning, we can predict the outcome in the future, like I said before. You can always predict what is going to happen in the future with supervised learning. Why? Because we have access to the past. And if we have access to the past, we can always predict what is going to happen in the future. In supervised learning, we have got two problem types. One is a regression problem, one is a classification problem. Now, what is regression? Regression, now, when we are predicting in the future, we must be predicting the value of a certain variable, something we are predicting, right? I am predicting the sales. I am predicting the price. Say sales 6 months from now, what will be the demand of sales? Okay, now demand of a product. So I'm predicting the demand, I'm predicting the sales, I'm predicting the price, some variable I'm trying to find a value of. If that variable can be expressed as a numerical value, then it is a regression graph. On the other hand, if I'm trying to predict something which cannot be expressed in numerical terms, then it is a class. Okay? So basic difference, let me give you examples. In regression, say you are forecasting the sales. Say the business wants you to forecast the sales for the next 6 months. You're forecasting the sales. You say over the next 6 months, the average sales which you're going to, the average demand for your product will be 500 units. But I can specify that in a number, right? I'm saying 500. So it's a numerical value. Then I'm dealing with the regression. Okay. What is classification then? Say you want to know, you want to predict. All of you apply for a loan here. There are few people who will get the loan. There are few participants who will not get a loan. Now, getting the approval for a loan depends on several factors like CIBIL score, your income, your family size, your past loan history, several factors, right? So few of the participants might get the loan approved and few of the participants might get the loan rejected. Now I want to predict for a new participant who comes in and joins the session now, whether he'll get the loan approved or denied. So what am I predicting? Whether he'll get the loan or not get the loan. So either it will be a yes, he gets the loan, or a no, he does not get the loan. And dichotomous response. Can I express it in a number? I can just express it in either yes or no. So when I'm trying to predict something which cannot be expressed as a number or in numerical terms, we call it a classification. Okay. Now coming to unsupervised. In unsupervised learning, we are not predicting anything. We cannot tell about the future at all in unsupervised learning. What is the maximum we can do? We have our data. The data is given to us, right? And we'll have to do something with the data. Either I say segment the data. Okay. Divide it into parts based on something, based on its usage. Say I give you 1,000 products and I tell you, okay, these are 1,000 items which I've given you. Now segment it or group them based on their usage. Okay. So the grocery items, group it together. The stationery items, put it together. The frozen items, put it together. And I give you, say, 100 items. So let us see which are the grocery items and put it together in a group. You check which are the stationery items out of this 100 items. You put them in a group. The frozen items you check and you put it in a group. You're organizing the data. Okay. So that is what we can do with unsupervised. For that, I do not have to know, okay, what are grocery items and the past history about grocery items. I can just group them based on the usage. What purpose are stationery items used? What purpose are grocery items used? What purpose are frozen items? Or their method of usage. For that, I do not have to know about it from the past or earlier. It is basically organizing your data. That is the maximum we can do with unsupervised. But we cannot predict if a new item comes now, 101th item comes. I cannot predict that whether it will be a frozen item or whether it will be a grocery item or whether it will be a stationery item. That I cannot predict. Because I cannot predict any unknown. Unknown prediction can be possible only if I have got past information. Or in unsupervised learning, I do not have past information. So I can never predict random. Okay. So in this case, we have got one thing, that is clustering. That is the only algorithm which we have for unsupervised learning. Clustering basically means the same. Say I've got a box where I've got circles, where I've got crosses, and where I've got triangles. Okay, all together. I want to organize it. How will I organize it? I'll keep the circles together. I'll keep the crosses together, right? And I'll keep the triangles together. How does it help me? How do I do that? Because they all look similar, right? So I'll organize them. Okay, these are separate. This is the second group, this is the third group. All the items are together. Now I've segregated it. Okay. Now, dimension reduction will come to it. But before that, I want to know if any one of you have a question. Harishankar Lakshmipati joined in very late. So Tharini and Harishankar, I do not have an idea whether you are already aware of machine learning. Here, they will not be able to predict. Again, predicting is a word which we do not use. So when you say clustering is, yes, we'll arrange the things and give it to the client, but we cannot predict. Predicting is possible when you have historical data, when you have past information. You cannot predict with clustering. So the client will not be able to predict. The client will have everything organized. Data means the raw information, right? So when you say reducing data by condition, what do you imply here? Reducing the number of rows in the data set? Data is the rows, right? The rows contain the information of the data. When you say reducing data by condition, do you mean reducing the number of rows in a data set? So dimension reduction in very simple terms is reducing the number of features which we use in our model. Now, why a reduction is required here? That might be the next question. Why do we need to reduce it? We know it's reducing the number of features, but why do we need to reduce? Features are what? The input, right? That is what we learned. Excess. Why do we have to reduce the excess? That might be the next question. When I now see, I'll give you two equations in the, you tell me which is easier to solve. Y equal to 2x1 plus 3x2 plus plus x4 plus, x3 plus 5x4. This is equation 1 and second equation. This is 2x1 plus 3x3. Which one is easier to solve, people? 1 or 2? No machine learning here. Normal mathematics equations. Which equation is easier to solve? 1 or 2? Why 2? Look, okay. I asked you to choose between both. Which equation is easier to solve? So I will give you the values of x1, x2, x3, x4. But which one will you solve faster? Obviously 2. Because I've got only 2 x's, right? I'll just plug in the value of x1 and x3 and I'll solve this. But to solve equation 1, yes, it will be easy. But I'll take a longer time to solve. So what are x's in machine learning terminologies? Those are the features of the inputs. So we always go for fewer x's. Now the reason is simple. The reason you already understood, right? To build a simpler model. We do not want to build a model which is unnecessarily complicated and time consuming. We want to build a simple model which we can explain simply. If I include many features, I'll have to explain the significance of each feature to the business. That is also required. I have to finally explain my findings to the business, right? If I include too many features, I'll have to explain the significance of using these features to the end client too, right? That is a task. Second thing is your model becomes too complicated. It converges to a solution much later because I'm using too many inputs. So the solution of Y becomes overtly complicated. It means we come to a solution, but it takes a long time consuming. Resource consumption is more. And there are other problems like overfitting and multicollinearity, which right now might be sounding very, very new, but slowly we'll get used to it. What is multicollinearity and overfitting? Okay. This is called dimension reduction. So we do not want to work with too many features. We work with fewer features. Now, the next thing which should come in your mind is, if I'm using less features, am I not losing out on information? But you said information is important. Data is very important, right? The beginning I said that data is information. I do not want to lose out on the rows. So if I'm dropping information about x2 in equation 2, I'm dropping information about x2 and x4. Then I'm losing out on information of x2 and x4, right? Information is data again. So do I really want to lose out on the information? No. Because the more information I have, the better solutions I'll provide. The less information I have, my solutions will not be that accurate. So I'll definitely want more information. But if I'm dropping features, how do I retain that information? I'm losing information. So there is a trade-off. Then what do we do? We will not work with 4 variables, x1, x2, x3, x4. Rather, we'll extract the information from, that is where I think, who said this? Varuni, right? That also comes up, is a part of your feature engineering. So what do? We take all these features, we extract information from all these features, and we store it in fewer features, 1 or 2 features. How does it help us? It helps us in retaining all the information, but keeping the feature count less. So what I do is, from x1, x2, x3, x4, I'll extract all the information and store it into 2 new variables. So let that be a1 and a2. Now I can solve the value of y using only a1 and a2. I do not need x1, x2, x3, x4, none of them. I am extracting all the information of x1, x2, x3, x4 into a1 and a2. Now these are the 2 variables of interest. I'll find out the value of y using a1 and a2 only. So how does that solve my problem? I'm working with fewer features, a1 and a2 only. My solution will happen faster, less time consumption, less resource consumption, right? And I'll be able to eliminate other problems like overfitting and multicollinearity, which we'll do later. So basically, I can solve all the problems by reducing the number of features. It is always a good way whenever you're building models to understand your data so that you can understand which variables are important and which variables are not. So if the variable is not important, I'll not include it. because it will unnecessarily complicate the model or complicate it will, like, let's forget about model, it will complicate an equation, right? So if for finding out the value of y only x1 and x3 is required and I can easily find out the value of y, I'll not use x2 and x. Did we all understand this now? That is which I explained in very simple terms. That is dimension reduction. Always work with the required number of variables. Which variables will help you? Say, I'll give you another example. Say I want to find out the weight change. How much weight I'll gain or lose in the next 1 week. I'm talking about calorie intake. I'll talk about the number of hours I sleep. Okay. I'll talk about my activity levels. How active I am. Do I work out every day? Then is my water intake. Then is my gender. Then is my, say, I'm including all this information. Gender and finally age. So I have got calorie intake, number of hours I sleep, activity levels, water intake, gender, and age. Now see, if I really want to track how much weight I'll gain or lose in the next 1 week, all these features and all this information is required. You'll tell me that, okay, tell me how much of calories you consume, number of hours you sleep. If you sleep less, you'll eventually put on weight. If you consume more calories than required, then you put on weight. If you're not active, sedentary, sitting down at one place, you'll put on weight. Water intake, do not have enough water, again, has an impact on your weight, on your digestion. Gender doesn't have an impact, no, hardly has an impact. Age, no impact. A child can be obese, a very senior citizen can be obese as well. A senior person can be obese as well. It depends on your lifestyle, not on your age. So if I try to solve this problem, what I'm trying to predict is weight changes, then out of all the information I have, I'll first strike out gender and second age, and I'll work on the remaining variable, which have a direct impact on me. So we work with only the variables or the x's which will help me solve the value of y. I'll not include those x's which does not have an impact on it. So what did I do? I reduced the number of features. So dimension reduction, in other words, is feature reduction. Now, ideally, it is feature reduction or dimension reduction happens in 3 steps, which I assume you all should have been doing till now. Let me know, we can take it up later. No, we can do this in detail, how it happens. Okay. So that is all. I think we are good with this. How does a machine learn? How does it differ when we are talking about? See, you'll find very less resemblance with what you see on screen. I'm not reading out from the text. So this is for your reference. What is left right now is how a machine learns. From traditional programming, how does machine learning differ? That is learn. What are the basic steps? What do we do when we are building a machine learning model? So we'll cover up these two, and then we'll go to the main slide, which we skipped in the beginning. This is the entire machine learning approach or the life cycle. We'll revise on this. And then we'll start off with a very, very basic problem statement. Very basic, the first model we will try to build. Clear, people? So let me see on the other side of the break what happens. I'll open up your polling activity. I'll appreciate if all of you respond to your polling activity so that I have an idea, because most of the people are not responding yet. So I'll have an idea of how this session is going. Put down your comments. Tell me if the pace is fast for you or you need me to go slower. Okay, while you respond to your polling activity. Now, we'll come to this later. The topics which we had left is how does a normal traditional algorithm work, and how does machine learn? Okay. Okay. Now see, in traditional programming, what happens? Okay, 1 second. Okay. In traditional programming, what happens? We have a program, right? Algorithm is what? A solution to a problem. Whenever we define an algorithm, how do we define it? It's a solution to a problem. That is what an algorithm is. So when we design a program, say you want to find the mean of 10 numbers, or say n number of numbers, you write a program for it. So whenever a number is inputted, include that, find the sum of all the numbers and divide it by the count of the numbers. Okay, that gives you the mean. So that is our traditional programming. I write the program, then the input comes here. Okay. The input is fed to the program or the algorithm, and we get an output. That is how traditional programming works. Now, what is the difference with machine learning? In machine learning, we say the machine learns. In this case, see, like you all are in this course right now, you are in the learning phase, right? So you all are, we have got how many sessions? 13, 14 sessions approximately. So in all these sessions, what are we doing? What we are doing right now is we are learning, right? All the sessions, we are learning about machine learning, about the algorithms. Towards the end, with what will happen after the sessions end, after 13 sessions, we'll ideally be solving a course and project, right? When you solve a course and project, what will happen? We'll give you a problem statement. You'll have to solve that problem statement and come up with a response. Okay? That is what you will do. So right now you're in the training phase. At the end of the what will you be in a testing phase? In the testing phase, what will you have to do? You'll have to solve a course and project, and you will have to submit your solutions for evaluation. Then we'll evaluate you, you'll get a score, and you can unlock your certification. That is what happens, right? Similarly, think of a machine. It undergoes a training phase where it learns, and then finally, when it has learned, we test the model, okay, or we test the machine. We test the machine performs on the test, and based on the performance, we evaluate the machine. Like we evaluate the machine as well. Okay, the machine is evaluated, and then the machine is given a score. Okay, so you scored this much, you score 80%, you score 90%. And based on the evaluation score, we decide of whether to deploy that machine into production, or we need to rework on the machine. Like when you get the score, ideally, if you get a very good score, then you're fit for production. Right? If you get a low score, then please rework on the project and submit it for reevaluation. Means we need to rework. Same thing happens with the machine. So what did we understand? The machine goes to the training phase. So there are two phases. One is training. One is testing. Okay. So, but we have one set of data, right? The data which is given to us is a single table of data. This is the data. It has few rows and say columns A, B, C. Okay, and then it has observation. This is the entire data. This is the historic information or historical information which is given to us. And whatever work we do it with this data set only. Now I'll have to train the model. Then I have to test it and see if it's fit for production. Then only it will be deployed, right, into production. But we have the single data set. Now this data set has to be broken up into two parts, because one part I'll reserve for training the model and the second part I'll reserve for testing them. Because all I have is this information. I'll have to utilize this information for training my model. And I'll also have to utilize this information. Using this information, I have to test the model. Now say, if I split it up into two parts, let's say I create a split here. So how many rows do I have? 1, 2, 3, 4. So I reserve 3 record information, 3 rows information in training my model. So my model learns from the 3 rows. And then I test my model on the last row. Now, say let us go back to the example, years of education. I have got years of education and professional expertise for 4 people. I have to determine what hourly payment I need to make to these employees. So years of education might be 16, 15, 20, and 16. Yeah. Professional expertise might be 1, means he has received professional training. 0 he did not receive, 1 he received, and 0 he did not receive. And then we have the hourly payment numbers too. See, $22 per hour. See, $25 per hour, $30 per hour, and we have $36 per hour. Okay, this is the data set. I'm splitting it up into 2 parts. So the machine is learning from the first 3 rows, and the last row I'm reserving. I'm not using it in the learning phase. See, now you have your course and projects, right? When we'll be doing several use cases. From today itself, we'll start. Maybe tomorrow also we'll continue. You'll have several use cases. Now you'll have a problem statement, right, which you have to solve. Now, when you go with the problem statement, now whatever problem statement we'll do, whatever business problems we'll solve in these 13 sessions, it will not be a business problem from a course and project. It will be Your course and project will have a totally different business problem. Then only we'll be able to test you, right? If I give you the same business problem in the session, then I'll be giving you the solution to. We'll be solving it alongside you, right? So you'll already know the answers. There is no point of testing you on something which you already know. So the business problem which you'll solve at the end will be very different from the business problems we'll solve in all these 13 sessions, right? It will be new to you. It should not be known to you on what you are tested. So similarly, when I say I'll reserve the last row for testing, I'm saying this last row data or information will not be used up by the machine in its learning. The machine will not learn from the last. The machine will learn from the previous 3 rows, right? Now say, in training and testing, let us understand this, the first 3 rows information. So we are saying that a person has 16 years of education, has received a professional training, and he earns $22 per hour. The second employee has 15 years of education, no professional training, earns $25 per hour. Third person is 20 years of education, 1 year of, and has professional training and earns $30 per hour. So the machine is learning from all these 3 rows, and last row it does not learn at all because we do not provide the last row information to the model machine. Okay. Now, when we get this, when we know the business problem, so what will the business problem be? Create a model which will automatically predict the hourly payment to an employee based on the information about his years of education and whether he received a professional training or not. Based on these two information, try to predict what will be the hourly payment which will provide to the employee. That will be one kind of business problem, at least suited in this scenario. So what is that which I have to find a value of the hourly payment? That is what I have to find out. So which is my outcome variable? My outcome variable is definitely hourly payment. This is my outcome variable. What is the information that I need to find Y? I need the information of X1 and X2. These are my features. X's. Correct. Because once I know the years of education and whether the employee received a professional training or not, then only I can predict what hourly payment he'll get. So I need these two information. Like if I'm predicting the weight changes over the next 1 week, then I have to know how much calories you consume and what are your activity levels, right? Then only I can make an idea of what amount of weight you'll gain or lose. Similarly, if I want to know how much payment a person will get per hour, I need to know about the hours of about the years of education and the professional expertise. So these two are X's. This is my Y, right? Now let us understand this. Now we are first identify what you need to predict. That is the first step. So first thing is understand the business problem. So here, what is the business problem? Predict the hourly rate of a new employee given his years of education and his professional expertise. This will be a business problem. So reading the business problem in only you know what information is given to me, the years of education and the professional experience. What do I have to find out? The hourly rate for a new employee. So I'm predicting something for an employee who is not present right now, in future. So I'm building a predictive model, supervised learning. Supervised learning requires past information, and we already have that. This is the dataset which is giving past information, right? So reading the problem statement, I know what is my outcome variable, that is the hourly rate. What are my feature variables? What is the information given to me? Years of education, professional. Now, once I've identified what is my outcome and what are my features, then I'll split it into 2 parts. One I'll reserve for training, one I'll reserve for test. Now, how will the model learn? How is it different from traditional programming? In traditional programming, we'll just give the input, right, to the algorithm, and the algorithm gives me the output. So input is fed and output is achieved. And this goes through the program and we get an output. In machine learning, what happens? When a machine learns, then it works in a different way. This is the algorithm. I not only give the input, I give the output. This is how the machine learns. So the machine learns this way. If 16 years is the education, 1 year of professional expertise, the person earns $22. 15 years of experience, no professional expertise, the person earns $25 per hour. 20 years of education and professional expertise, the person earns $30 per year. Okay. the machine learns this way, not only from 3 rows, but several rows. Now the machine forms an idea, okay, if this is the years of education and this is the professional expertise, then what can a person earn? That idea it has from the learning it that happens in the training phase. So machine has learned to correlate what might be the earnings if this is the years of education and this is the professional training expertise. It is formed an idea on how to figure out on the RD payment. Okay, the training is done. Then we'll test the machine. Now we'll tell the machine, okay, see, the person has 16 years of education, no professional expertise. Tell me, how much should I offer this employee per hour? The machine will come up with some kind of prediction because it has learned from many employees' information. Now it has formed an idea about what the hourly payment might be. So the machine tells, okay, the hourly payment will be $35 per hour. But what was actually paid to the employee? $36. So the machine is going with the accurate prediction, but okay, there is a slight mismatch. It was actually 36, but the machine predicts a 35, but still close, right? There will be some amount of error. So what is this? This is my machine's prediction. And what is this? This is my actual value, right? Now say whenever we see we are predicting something in the future, we cannot be 100% correct, right? Even when the astrologer says that, okay, 10 years down the line, this is what will happen to you. Or, okay, in your appraisal, this is the increment which you get. The astrologer will specify a range between this percent, between 8% to 12%. But he will not give you an exact answer. Say you will get 10% raise. He'll give you an approximation. You'll get within this range to this range. And it clicks most of the time. Now, it might also happen that it might not click, but it might be close. Say the astrologer says, oh, you'll get an 8% increment, and you end up getting an increment of, say, 7%. You still feel, okay, the astrologer was partially right. So you cannot predict the future of something which has not happened with 100% certainty. There is always a scope of an error. So when we build these models, when we build the probabilistic models, there is always some scope for error, which we keep. Because a machine cannot be 100%. In predicting something which has not yet happened, we leave a scope of error. And that is due to several reasons. The market conditions at that point of time, the environmental conditions, the human conditions, human error conditions. So there are various factors which contribute to it. So I can never say a machine will give me 100% accuracy. See, even an astrologer will never be 100% accurate. He'll be close to the right, but it will not be exactly right. Similarly, when a machine predicts, that it will be a good model will give you accurate predictions, but it might not be 100% accurate. Okay. Oh, so now we know how the machine learns. And when we test the machine, then what do we do? What do we do? We just give the input. The output the machine has to. So this is when I'm drawing this is my training. Now, what happens in the testing phase then? In the testing phase, say this is your testing phase. What do you give? You give the input. Do you give the output? No. You just say 16 years of education and zero professional expertise. You tell me what will be the output. Because you have learned, right? Like the course and projects. We'll give you the problem statement and tell you now you solve. We'll not give you the answer. So similarly, I'll not give the answer to the machine. We'll give only the feature information. 16 years of zero professional. Now tell me what will be the answer. Now the machine, based on its learning, will give you an answer. The machine will give you an answer. And then you'll see whether the output is actually close to the correct output. Because you already have that. So this is your training phase and this is your test. Right? Let me do this you have an example in this deck itself. See, the problem statement will be generic, like hourly payment. That is what HRs do. What is HR analytics all about? You predict which employee is leaving, which employee is staying there. Either that is what you are predicting, or at times you might predict the like hourly payment, what salary I should be offering to a new employee. That is what HR analytics does, right? We talk about the employee payment, we talk about the employee's attrition. Those are real-time cases. Okay, now let us talk about weight changes. So weight change, we have seen that change in weight. So let us say weight is one variable. How much it will change, right? And next thing is what, which you all can identify with, say calorie intake and activity levels. Two major contributors of weight change, activity levels. Okay. Now say we'll create 1, 2, 3, 4, and 5. 5 rows of data I have. My weight is say 56. Calorie intake is 3000, and activity levels is 1 hour. Then we have say 65 for 4500 and say 20 minutes, and so on. Say 70, 4500 and 50, and say 62 and say 4200 and say 14, and say 58, 3200 and say 45. Okay. This is the data set which I have. What do I have to predict? Now say the problem statement is predict the weight of a customer who consumes 4000. Okay. Predict the weight changes of a customer given the calorie consumption and activity levels. So this is a problem statement. So you'll get problem statements like this. So you will be told what you are given. You will be told what you have to find. So what do we have to find out? Predict the weight of a customer. So I have to predict the weight. So which is the variable whose value I have to find out? Weight. See, if I'm given this data set, first only I'll mark it. I'll have another example in the table. Given, so what is given to you? What information is already provided? The calorie consumption. So that is my X feature. I have got 2 features here, say X1. And second is activity levels. This is my X. The time I spent working on. Relatable example, I have to find out the weight. Now this data is given to me. Now what will I build this model for? So that whenever I plug in the calorie intake and activity level, say now after building this model, I ask you, tell me what will be the weight of a person who consumes 4800 calories and works out for 40 minutes a day. Tell me what will be the weight. And the model should be able to predict the weight based on its learning and based on what it has learned in the training phase. It should be able to give me an answer. That is the purpose of building the model. Okay, now, so the first thing is identifying which is my dependent variable, which are my independent features. X1 and X2 are independent, and Y is my dependent variable. Next step is what? I'll be splitting this data set. First split is already done. Now see, my data set is in 2 parts. One is what I have to find out, and the second part is what? What is given to me. With the help of what I'm going to find out why, right? So with the help of X1 and X2 only, I can find out why. Otherwise, I cannot find out the value of y. So first thing is what? I'm dividing it into 2 parts, correct? Now let us go to the next step. Next step is what? Now you have this information, make the best use of it. Build a model, test the model. Before it answers this question, 4800 calories and 40 minutes. That is what the customer will ask. So you have given the model. Now the customer will, okay, I have it ready. Now I'll get ready answers. So plug in the data. So it will give 4800 calories, 40 minutes. Your model has to come up with an answer. That is in production. But this is the information I have, so I'll make best use of it. So split this data set into 2 parts. One I'll use for training my model. One I'll use in testing my model. So let me split it up into 2 parts. So the mode data say, now when I am explaining, when you're in the training phase, I'll give you more and more information, right? So that you learn more. So that when you are being tested, you can apply that information. But see, if I do not give you good information in your training phase, will you be able to perform in the testing phase? No. You'll not understand anything, what to do, how to do it. So I'll have to give you ample information in your training stage so that you can perform in the testing phase. So more information is required at the training phase. Less information is required at the testing phase, correct? So in this case, see, I have got all these rows of data, so I'll split it up into 2 parts. There's one part. And the second, I'm just keeping 1 row for testing the data. Okay. Now see the split, how it happens. Now this, if I separate Y, which is a single column, right? This single column is split into 2 parts. One is the red one. Okay, let me show it. This red one, and one is the green one. So this red one goes to the training phase, right? So what will this be called? This will be called Y train. Okay. And what is the other portion? This part called. It is in X, right? Feature set. So it will be called X train. Okay. Now, what is the one row which I have reserved at the end? This is also into two parts, this part and this part. So this part of Y will be called Y test. And this testing part of X will be called what? X test. Now say if I add Y train and Y test, just go with the what you see on screen. Y train and Y test, if I add it up, won't I get Y? Similarly, if I add up X train and X test, won't I get X? Yes, people. So if I add up Y train and Y test, I'll get Y, right? I'm just adding it up. And if I add X train and X test, I'll get the total X. X can be multiple. Here I've given 2. So total X I'll get if I just add X train and X test, and total Y I'll get if I add Y train and Y test, right? And if I add X train, X test, Y train and Y test, I'll get the entire data set. These are all parts of the data, right? If I add up all the parts, I'll get the whole. We'll start off with a business problem. These are examples which I'm giving you, but these are all relevant examples. The example which you have on the deck is also relevant. That is how HR, what is HR analytics? You are doing analytics for the HR domain. What does the HR deal with? Salaries, how many people are leaving, how many people are joining. They deal with all this human resources, right? They'll deal with their employment, they will deal with their exit, they will deal with their compensations. Whom do you speak to about your compensation? To the HR only, right? You do not speak to your interviewers for a compensation, do you? You speak to the HRs. So the example which you had in deck is a real-time example. It's very realistic. It's an HR analytics. This example is what? This is a self-created example. So that you understand the points. So you know weight changes, what is it impacted by? It is impacted by the calorie intake, it is impacted by the activity levels. Correct. It is impacted by both these features. That is what we know. So we are taking that kind of example. Now let me go back to the deck. I think that will be more relevant. Just remember what the steps which we did. Now, see this. What do you have to find out? I'll write down the problem statement. So this is again the same example which we talked about a while back. Now here what do we have? The hourly rate. So you have to predict the hourly rate, right? Based on what information do you have? Education, professional training, and ID of the employee. So you are talking about a company, say XYZ. There is a company XYZ whose how many employees information? 1, 2, 3, 4, 5, 6, 7, 8 employees information is given. Their IDs are given. Their educational years are given. Years of education are given. The professional training expertise is given. And what they get paid per hour is also given to you. Now, what does the HR want? The HR wants you to build a model by which the HR does not have to worry about what to offer that person. See, finding out the right compensation for an employee is very important. If you offer a compensation lower than what the candidate expects, the candidate will not join. If you offer a compensation higher than what is right, then the company will fire you, right? Because you're adding up to the cost. So offering the right compensation is a very crucial task. So I cannot give an hourly rate which is above what I should be offering. And I cannot give an hourly rate that is very low that the employee refuses to join my company. So as an HR, I have a tremendous task, a very important task of determining the actual compensation. That is why when you go for an interview, you discuss about your compensation with the HR only. You do not discuss it with anyone else. They are the responsible people. And it's a tedious task. On a compensation, you might join or you might not join. Okay, so here, what is the problem statement? Build a model. So the HR does not want to take up all this trouble. So it wants a ready-made algorithm where the HR will only give in the years of education and the professional training expertise information. And the model automatically by itself will predict the hourly rate. Okay. The model will itself give you the hourly rate. What the HR has to plug in? The education, the professional training experience, and the IT. So what are you predicting here, people? Okay, now tell me, when you're predicting hourly rate can be expressed in numbers, right? How many dollars do you want? Like, what is the payment? $90 you want, $80 you want, $70 you want. What is the payment you want? You can express it in numbers, right? Okay, now tell me one thing. Based on what learning we had till now? Is it a supervised learning approach or an unsupervised learning approach. Yes. Supervised learning or unsupervised? What does this problem statement fall in? What kind of problem? Supervised. Okay. Now, in supervised learning, we have got two problem types. There is something called regression. There is something called classification. Now, tell me, is it a regression problem or a classification? If you all have forgotten what is regression and classification, I'll tell you. Regression is when we are trying to find out something which can be expressed as a number. Hourly rate, my hourly payment can be expressed in number, right? I'm getting $100, $200, $50. I can express it in number. So it's a regression problem. If I'm trying to predict something which cannot be expressed as a number, how many people died in the Titanic disaster? Now all the passenger names are given. You have to say, did Kate die or survive? So what will your response be? Either yes, she died, or no, she survived. There can be no two. You cannot say that maybe she died or maybe she survived. That is not a response. Either yes, she died or she survived. So you can have only two responses and you cannot express it as a number. So what is that problem? That is a classification problem. Okay. So this problem statement is right now a regression problem. And yes, it's a supervised learning because you already have information. This is past information about 8 employees. Okay. So what is my first step in model building? When I start off with model building, what is the first step? We have already identified what we have to find out. That is not evident from the data set. That is evident from the business problem. When I give you the business problem, you'll automatically understand what you have to find out. So going by the business problem, which is my dependent variable, or what do I have to find out? Hourly rate. So that is my y, right? The unknown is y. So hourly rate is y, right? With the help of what? With the help of education and professional training expertise. These are the two inputs which I have. So without this information, can I predict y? Yes, people. If I do not have information about the education and professional training, can I find out the hourly payment? I need this information. If I give you an equation and do not give you the value of x1 and x2, will you be able to solve this the equation? Y equal to 2x1 plus 3x2 plus 4x3. Now I tell you to solve it. And I do not give you the values of x1, x2, x3. Can you solve the value of y? Never. You can have only one unknown in one equation, right? x1, x2, x3 should be known by, otherwise how will you find out the value? Not possible. Similarly, in this case, if I do not know the values of x1 and x2 or the x's, I'll never be able to find out the value of them. But that is what I have to do, right? I have to find out the value. In this case, how many x's do I have? x1, x2, x3. Here also I have x1, x2. Then instead of mentioning it separately, I'll say all the known features are labeled as x. Unknowns are labeled as y. This is how we mention it. Now tell me, I've got x1, x2, x3. Will I take all x1, x2, x3? Will I take all the variables here to predict y or to find out y? We talked a while back about feature elimination or say dimension reduction. What do we talk there? We said that we'll include only variables which are required to predict the unknown. If a variable has no relationship with the unknown, then why use it? Drop it. Do not use it. Do not make the model complicated. So if only x1 and x2 is helping me with the value of y, why do I need x3? I will not include x3. Similarly, in this case, the employee ID of the an employee has nothing to do with the salary he's getting. Can you predict the salary of a person by the employee ID? Never, right? If you do not know what is the performance or what is the rating, last appraisal rating, you can never figure out what is the salary. Difficult, right? Just by employee ID, you cannot find it. IDs are insignificant. They are not required to find out the unknown. So the first thing which we'll do is we'll eliminate it. Not required. We'll work with what? x1 and x2. x2 and x3. So now, the next thing is I have now, instead of mention x2 and x3 separately, these are my known features. So they will fall under x. There can be many x's. Now, hourly rate is not only determined by the number of years of education and whether you receive professional training. This is also dependent on many other factors. What is the past salary? That is also dependent on it. So, but we are including only two factors. Like when I am talking about weight changes, it's only activity levels and calorie intake important. Nothing else impacts your weight. Yes. Your water intake impacts your weight. But for simplicity, we are taking only two features. I can have multiple features. I will combine all of them into one particular subset called X. And what I have to find out that will be contained in a single subset called Y. Okay. So first partitioning done. X and Y, both are separated. All the X's will go to one subset, one part of your data set. which you call X, and then unknown will go to one part of the data set, which we'll call Y. Okay. First thing, which is important. Second step. Now I know my machine will learn from the data. Will learn from what employees of this organization have already got in the past. See, every organization will have a certain pay scale, right? All the companies will not pay you equally, right? MNCs will give you more salary. A startup will give you less salary. Understood, right? That is what is normal. So every company has got their own pay scale. So I cannot predict some salary which is not relevant to this company only. So I'm predicting the salary of an MNC in a startup firm. Obviously, I'll be wrong in predicting that. So first I have to know how does the company pay? What is the pay scale? Then only I can predict for a new employee, right? So how do I know about what is the pay scale of the company provides to its employees from the historical data? That is what is given to you. 8 employees information. So the model gets an idea of, okay, what is the payment this company offers to people, to its employees. Based on that learning, it will predict a certain salary for a new employee joining this company. Correct. So this is my historical data. I have split the entire data into two parts now. One is X and one is Y. Now first my model will learn, the machine will learn from this data, and then the machine will predict on new data. A new employee joins this company, what will be his hourly rate? That is the purpose for what I'm building this model. But first I have to build this model, ensure it learns. And I have to test it too. Before it goes to production, before I hand it over to the HR and tell, okay, deploy it. Before I do that, training is required, testing is required. So for training, what do? I'll split this data set into two parts, okay, which is already done. So you can see train set, test set, different shades, right? I'll tell you why it is different here. So train set, this is my training data. So what will I call this? Now, if I start labeling it, if I call this my training set, okay. So what will I call it? X-train. What is this called? X-train. What is this called? This is Y. So it is Y train. The yellow one, it is test, right? So what is this called? X-test. What is this called? X-test. What is this called? Y-test. The third one, training set, right? What is this called? Again, X-train. This is X-train. And this is Y. This again, test. So X-test. X-test and Y-test. Similarly, I can label all the rows, right? This is also X-test, X-test, Y-test. And what about these? These are all training, right? Training. So I'll write X-train, 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 and so on. This is my Y-train, Y-train, and so on, right? Now see, if I add all the X trains and Y trains, that is what we were saying, X train plus X test will give you the total of X, right? Think of this, if I add all these rows together, what do I get? Nothing but my X. If I add all of this Y trains and Y test here, what will I get? My entire Y, the entire column here. So that is what I said, X train plus X test will give me X, right? Like Y train plus Y test will give me Y. I'm just splitting Y into training and testing. Similarly, splitting X into training and testing into two divisions. So if I add up the divisions, I'll get the whole. This one is done. Now say I have what? X train, X test, Y train, Y test. If I add all this code together, then what will I get? The entire data, the entire historical data. I'm just splitting it up into parts. I'm having the entire data. I'm just splitting it up into. Now say, okay, till this, I hope it is clear. I'll delete all this. Now comes the main part. So training, from where did my model learn? My model learned from this row. My model learned from here, here. It learned this. It learned from this to learn this. It learned from this to learn this. This to learn this. This to learn. Learn from all this rules, right? It is learning 16 years of education, a year of professional training. Hourly rate the person got or that employee got is $90. Then it came to the next row. 12 years of education, 1 year of professional training, $70. 16 years of education, 1 year of professional training, $100. 15 years of education, 1 year of professional training, 105. 15 years of education, no professional training, 70. It is learning, right? From all this. Now I say the model, okay, you've learned a lot. Now it's time that I test you. How many rows did I give for training? 1, 2, 3, 4, 5, 5 rows. 5 rows go into training. Training means the model has access to the input, the model has access to the output. So when I train my model, I'll use what? X train, that is the input, as well as Y train, that is the output. Both are given to the model in the training phase. What happens in the testing phase? We give the input, we do not give the output. Remember. So in the testing phase, what happens in this is testing. I'll just give the input. What is the input in the testing phase? X test. Like I've created X train, I also have X test, right? So input will be X test. What is the output? The output is Y test. That is the right output. But will we tell it to the model? No. So what will we say? See, now I know that you have learned. Now tell me, I've got 15 years of education and 0 professional training. What will the salary of the employee be? Predict. Give me the answer. I have got 18 years of education and 1 year of professional training. What should be the salary? I have got 16 years of education and 0 professional training. What should be the answer? What should be the hourly payment? Do I know the answers? Yes, I know the answers because I have the data set with. But does the model know? No. Because when I trained the model, what did I use? X train and Y train only. The model only knows X train and Y train. It does not have an idea of X test and Y test. But suddenly, once the model's training is complete, I ask the model to see. Now I'll give you X test. That is 15.0, this input I'm giving. 18.1, this input I'm giving. 16.0 input I'm giving. I'm not giving the output. I'm saying now you give me the output. So the model has to give me an output, right? Now the model tells, okay, for the first row, okay, the first row, the salary will be for 15.0, the salary will be $62. For 18 and 1, 18 years of education and 1 year, the salary will be $130. And for 16 years of education and 0 professional training, the salary will be $108. That is the model's answer. So when you're given the course and project, you will give your answers, right? Will it be the exact match to the solution which we have? No, it will not be an exact. It will be close to it. How are you evaluated? How close you are to the correct answer? Whether you're giving the correct answer. It might not be a copy of the actual, but at least it should be right. That is how the evaluation is done there. So here the model is giving you the answers, 62. So the model is going through the course and project. It gives you 62. Then it gives you 130. Then it gives you 108. How will we evaluate the model? We'll compare the scores. The right value is what? 65, which we already know, but we just don't tell it to the model. Like your course and project solutions, we already know, but we just do not tell it to you. So 65, we already know. What does the model say? 62. Okay. 130, we already know. What does the model tell us? 130. It's correct here. 110, we already know. What does the model say? 100. So we'll capture the deviations. How wrong is the model? 65 minus 62. The model is wrong by $3. 130, the model is exactly bang on. Here, the model is wrong by $2. Right? But this amount of deviation is allowed. Then we give it a score. Okay, you are 80% right. 88% right, we tell. Then we give a evaluation score to the model. Right? And like I said, it will never be 100%. It will be 99% is still okay, but never 100%. Because it will never be able to give a exactly right answer of something which has not yet happened at all. So some amount of error is always allowed. Some amount of deviation from the right answer is always allowed. That is captured by the error count. Okay. Now let me have some questions, please. You'll always have to find out a single error. You cannot find out multiple errors. How will you find out multiple? Do you have an equation? See, it is not something which is out of the box here. Do you have this? You have also solved normal equations in mathematics, right? You have y1, y2, y3. Can you solve it that way? 3 unknowns together. I cannot have, right? I can have one unknown and several knowns. With the help of several knowns, I can predict the value of one unknown. But how multiple unknowns in one single equation? Not possible. How will you solve it? Did you understand this? Now you might say that y can have two values, like classification, which we are talking. Every passenger, either that passenger died or that passenger survived. So y can have what value? Right? Second value, survived. That can be y value. But every like passenger will take only one of the y values, not both. A person cannot die and survive at the same time, right? So one equation will give you one solution. A single equation cannot give you multiple solutions. Okay, let me have more questions, people. Let's do one thing. When we do the use case, then I'll re-explain this. So now quick questions which I'll ask. Y test, when I talk about Y test, is Y test known to us or not known to us? Okay, is Y test known to the model or not known to the model? When I'm talking about all the subdivisions to your main data, is Y test a value that is known to the model or not known to the model? So Omega says known to the model. Y test is not known to the model, right? Y test is what? The Y value at the testing phase, the output at the testing phase. the right value of the output at the testing phase is never known to the model. That is what the model has to come up with. So y-test is never known to the model. The model will predict the value of y-test. Y-test is what? The actual output. So when I'm saying about another new employee, then the model will predict the salary, right? It might be the right salary, it might not be the right salary. Y-test is the actual value. Okay. So X-train, X-test, Y-train, Y-test, we add all of it and we get the entire data set. Okay, we'll talk about it more. Ideally, if you are very new to this, when we create the subsets, then you can have a question here. So we'll try to re-explain this concept again when we are ideally splitting our data set into parts. Okay, now let us go to the next part, the first deck with which we can wrap this up. The entire life cycle, which we are talking about, this one. This is the main deck. So how does this machine learning process start off? First step is understand the problem. Like I always told, whenever you're solving a business problem, first understand what you're trying to solve. The moment that clarity is there, you know what you have to find out. Your dependent variable is very simple. Means you can understand it from the problem statement. For that, you have to understand what you are trying to do, what you have to find out, and with what, how do you find it out? With the help of what information? Everything will be a part of your problem statement. So whenever you solve any use case, any business problem, the most important step is to understand what you're supposed to do. Because like I'm explaining with 1-2 variables, you'll not have 1-2 variables. You'll have several variables, 10-15 variables. You'll have to identify which is the variable which you have to predict. So for that, understanding the problem statement is very crucial. First step. Second is, once you understand the problem statement, then once you understand the problem, like I said, the HR wants to predict what will be the salary of a person, hourly payment to a person, given the years of education and professional expertise. This is the problem statement. So just by understanding the problem statement, you know what? You have to predict the salary. In my data set, what did I have? Hourly rate, years of education and professional expertise. So immediately you'll go for hourly rate and tell this is my dependent variable. This is what I have to predict. Then what are the features? Extract the features. Features are what? Your independent variable. The inputs, which will help you find out the value of your dependent variable. What were our features in the example? Years of education, professional training. Those were the features. So extract the inputs from the data set. We're talking about supervised learning. What is the third step? Identify the problem type. Now, what does it mean? I am working with a supervised learning approach where I am predicting the future. Then what is important? What kind of problem is it? Is it a regression problem or a classification problem? What am I trying to find a value of? Can I express it as a number? Then it's a regression problem. If I cannot explain it as a number, and if it has got two outcomes, then it's a classification. Identify the problem. That is third step. Fourth step, choose the model. Now, here we'll talk about. When we are talking about regression, there are many regression, not only one. We have got ridge regression, elastic regression, lasso regression. We have got simple linear regression. We have got multiple linear regression, many regression models. So when I'm saying regression, which model do I want of it? There are options. Similarly, if I say classification, there are several classification algorithms. Which one do I want to use? We'll come to that later when we are working on it. Choose the right one. Then is train and test the model. That is very important. If I do not train, then the model will never learn. How will I test the model? So training and testing is equally important. Training the model so that the model learns, and testing the model so that before we deploy the model and we submit the model to the client, we know that we have submitted or we have given properly working model, not a model which will not be able to predict at all, right? So before you go to production, your score should be good. It is not that any score is given to you and you fail in production. That should not happen, right? Similarly, training and testing both are important. What is the last point? Strive for accuracy. I get a score. I get a score of 20%. You have a percent, you get a score of 20%. What will happen? You'll be asked, okay, you resubmit your project. Why are we doing that? So that you get a better score. Strive for accuracy. If the model is performing well, ensure the model performs better. Improve on the performance. So if I have a model which scores 70%, I'll try to enhance the model's performance. Get a better accuracy. Better the model. Okay, before we start off the coding part, let us understand a few things. Like we said that when a model has learned and when we have used the model, we have tested the model ideally, we get a score, right? Means we evaluate the model with the help of a score. Right? So for that, some metrics are used. What are metrics? Metrics are usually functions which will give you a evaluation score, like how well is the model performing. Okay. It is actual minus predictions, that is the error, by the actuals into 100. Okay, we'll get into that. Metrics, the main metrics is R square here. Okay, let us discuss this as we proceed. Now, what is Scikit-learn? Scikit-learn is the machine learning library. So all the models which we are talking about, say regression models, classification models, all these algorithms, we do not write the algorithms ourselves. They are already pre-stored and it is a part of the Scikit-learn package. So Scikit-learn is ideally a machine learning package. You can read it out later. So model selection, now when we are using an algorithm from Scikit-learn, it is basically the class information. It means it does not only have the data, it has a lot of information contained there. Okay. So we are basically importing the algorithm along with a lot of information. So ideally the class, that is model. So once you select a model, say you're selecting linear regression, right? So you will not only, so when you import it from Scikit-learn, you'll be importing the class information, not only the algorithm, not only the program, but a lot of other information there, okay, regarding any data, which is regarding the algorithm itself, like how does it function, etc. What task does it perform? So a lot of information comes along with the program, which is what is used, right, along with the algorithm. So basically you import a class, but we do not work with classes because classes are something which is ideally a picture, a blueprint or a design of the actual algorithm. It is not the actual algorithm, but a lot of information regarding the algorithm and how it works. So we do not need the extra information. Right? So classes are designed. And with the help of the design, what do? We create objects. The basic design based on which the objects are created. That is a class. But in Python, we always work with objects. So when we import the algorithm from Scikit-learn, we ideally import the class information. But we need only the algorithm to work. So we'll create an object from that class. So first step is import the algorithm. Second step is create a model object, because that object will ideally do the learning and ideally will be tested and ideally will be deployed. So when we are doing anything in Python, we do it with the help of objects, not classes. What are classes? Classes are a design based on which the objects are created. So when we import the class, and when we actually use it for real-time working, we create an object from that class. Third is model training. Now, what is model training ideally? Model training is I have created a model object, right? Now I'll have to train the model. How do I train the model? Based on the data which I have. So we discussed yesterday, we have historical data or past data. We are going to split the data into two parts. The first part we'll use for training the model. Few of the proportion of data is used for training the model, and whatever is left out, that is used for testing the model. Okay. Then once the training is completed, the model has been built, then we test the model to see how well it has learned. That gives us the predictions. The actual values are the y-test. We already have the actual answers. We just wait for the model's answers, which are termed as predictions. Now we'll match the actual answers with the model's answers. If the model is close to the actual values, we'll say the model is predicting very well. If the model's answers are not close to the actual answers, we'll say the model is not performing well. So, and that is how we evaluate. That is how we test the model. Then what happens if the model does not perform well? Then we have to tune the model. Tuning means optimizing the model's performance. We'll try to improve the model's performance. That is tuning. And finally, we arrive at the desired accuracy. Post-tuning, if the model gives us a decent accuracy or gives an increased accuracy, that is our final object, to get an increased accuracy or a better accuracy. For that, we optimize the model's performance. We'll do all this, which is called regularization in regression models. After we are done with simple linear, multiple linear regression models. Now, there is certain rules which we always follow whenever we are working with any model, not only regression models, any model. We create separate objects for features and response. That is what we discussed yesterday, right? I have my entire data. The first thing which I'm going to do is split the data into two parts. One is the features, those are the inputs, and second one is the output. Yesterday we separated the years of education and professional expertise. We clubbed it together into X, and we were predicting the hourly payment to be offered to a new employee. That was why. That was what we were trying to predict, outcome, or the dependent variable. But we were keeping the dependent variable separate because you only predict one value at a time. Like yesterday, who asked me that question? Asked me that question that can I have one y1, y2, y3? No, you cannot have y1, y2, y3. Whenever you are doing a regression model, you are predicting a single outcome. So there can be only one value of y. Okay. So when you get the data, the first step is split it into feature, which we label as x, and response, which we label as y. At times, I call it independent variables, the features. Why do we call it independent variables? And why do we call response the dependent variable? We'll come to that in a while. So the features are mapped as x, and the response is mapped as y. Now, independent variable, we call it the independent features or the independent set, because these x's do not depend on y. Y depends on x. So I can find out the value of y only with the help of the value of x. X does not depend on y. Y depends on x. That is why we call y at times as a dependent variable and x as the independent variable. It can be one variable, it can be multiple variables. Okay. That is the first rule. That is the first thing we do with the data. Second, features and response should only have numeric values. Now, any reason why? All the algorithms are based on mathematical and statistical concepts, right? So the data, the feature set and the dependent variable set, that is x and y, should have only numeric values. If there are string values or text values, ideally the machine will not be able to make sense of the data. Okay. Machine understands only numbers. They do not understand text. Text is ideally a high-level programming language which we understand, humans understand. But machines understand low-level programming language, that is binary language. Binary language we know as 0 and 1. So it will understand only numeric values. It does not understand non-numeric values. So if I want an algorithm to work on the data, my data should have only numeric values. And my data is what? My data is split it into two parts, x and y. So x should have only numeric values, y should have only numeric values. No string values there. Features and response should be in the form of a NumPy array. Now, why NumPy array? NumPy package is used for what? For performing numeric computations on your data. So if you want to perform basic numeric computations on your data, like subtracting, adding, multiplying, dividing values, then you have to store it in a different data structure. That is a NumPy array. You cannot keep it. Ideally, you can keep it in a data frame too. That is also a two-dimensional labeled array. But it has to be in an array format. If I keep the data into an array, it helps me with the numeric computations which I want to perform in the data. So ideally, features and response should be stored in a NumPy array. But even if we store it in a subset or in a data frame, it is not a problem because data frames are also labeled arrays. Okay. If we need the labels, now if the labels are not important, then we can keep it only in a form of an array. But there are cases where the labels are also important. Say the dependent variable. If I do not know the name of the dependent variable, then ideally I'll not be able to understand the results, right? So then we can keep it in a data frame format. Like I'll create a subset of my main data, store it as X. Another subset will be stored as Y. We can keep it as a subset of a data frame, right? But when I'm doing only numeric calculations and the labels do not have any value or any significance, then I will keep it only in a NumPy array. We'll do that when we are doing clustering. Now, since features and response would be in the form of arrays, they would have shapes and sizes. What are shapes and sizes? They are attributes of an array. They are the features of an array. Every array will have a shape. Every array will have a size. Shape is what? The number of rows, comma, the number of columns. And what is size? The total number of elements in that array. Features are always mapped as x and responses, which we did in the first case. So these are the basic rules which we follow when we are preparing our data into the final stage or we are inputting the data or splitting the data for the modeling, to train the algorithm. These are the basic steps which you have to put in there. Okay. Any questions till now, people? So the first model which we start off with is linear regression. Now there is a lot to know about linear regression, but we'll start off with the very basic part. Okay. Linear regression is what? Linear regression is it's a cause and effect relationship. It's one of the most widely used algorithm which you work on in your production. We always use regression models. The linear regression is widely used. Ideally, is a very strong model, so it does not require a lot of tuning, and it is very fast. It's more time and efficient. Okay, now what is linear regression? Ideally, it's a cause and effect relationship. Ideally, what we understand when we say that I am trying to find out the value of y with the help of x, y equal to mx plus c. So, okay, this is a straight line equation, right? Y equal to x1 plus 2x2 plus 3x3 plus 4x2. Then what am I trying to do? I'm finding out the value of y with the help of x1, x2, and x3, right? So, in the absence of x1, x2, x3, I cannot find out the value of y, right? So, I need x1, x2, x3 to get a value of y. So, this is the effect. Then what is the cause? These are the causes. It means these causes produce the effect. So when we talk about linear regression, like we talked about weight change, we talked about calorie intake, we talked about, so what was calorie intake? It impacts the weight. What is activity levels? It impacts the weight. So calorie intake is independent of the weight, right? You can eat as much as you want. You will not think about your weight before you eat. So calorie intake is independent. We talked about activity levels. So how much you work out will not be dependent on your weight. It will be dependent on how much you want to work out. So activity levels, calorie intake, they do not depend on your weight, right? So they are called the independent variables. Those are what the causes. But weight is dependent on the calorie intake, right? Weight is also dependent on how active you are. So that is the effect, the dependent variable. Why? So it's linear regression is nothing but a cause and effect relationship. We have multiple causes producing a single effect. Now we have information about the causes, means x1, x2. These are the input. These are the endogenous variables, which is this information is already given to us. We have to find out why, which is an endogenous variable. So y is endogenous, internally computed. And what are x's? Exogenous. Means this is the value which is given to us. Then only we can find out the value of y, which is internally computed with the help of x1, x2, and x3. So basically, it is a cause and effect relationship. Now you all know this line, right? Y equal to mx. So we are discussing simple linear regression today. So y is equal to mx plus c. This is a straight line equation. We all know this straight line equation. So simple linear regression model is a straight line. It's always a straight line model. And the dependent variable and the independent variable have a linear relationship. What do we mean by linear relationship, people? Anyone understand? The first assumption of regression says the dependent variable and the independent variable should be linearly related at a fixed radius. Right? So y cannot happen without x, right? So in other words, we can say when x changes, y will also change. They have a relationship. That is called, it might not be a perfect straight line, but it will indicate, the trend will indicate a relationship. If there is no relationship, then ideally I cannot find y with the help of x. There has to be a relationship, and the relationship has to be linear. That is the answer. When x changes, y changes at a fixed rate. What is that fixed rate called? Fixed rate is called the slope. How do we find the slope? Now we have done all this, right? What is the slope? This is x1, this is y1. This is x2, this is y2. So when x changes from x1 to x2, y changes from y1 to y2. Okay? So when x changes from x1 to x2, y changes from y1 to y2. This change is captured by the slope. So this is your slope. So how do we measure the slope? y2 minus y1 by x2 minus x1. So what is the change in y due to a change in x? That is captured by the slope. And slope has a very important role to play when we are selecting features or independent variables to predict our dependent variable. Ideally, that will be more specific when we are talking about multiple linear regression. Y2 minus y1 by x2 minus x1. It is always fixed. For a single line, it is fixed. If I have got another line here, then it will change, obviously. If I have third line here, it will be something else. But for a single line, it will always increase at a fixed rate. That is captured by the slope. Now, why is the slope important? We'll discuss when we are doing multiple linear regression. Remember, the slope is the most important parameter of a regression model. So now if I replicate the straight line equation into a normal regression equation, then y is y same. What is m? M is the slope. That is given by beta 1. Beta 1 is called the coefficient. Okay. That means the weightage of x. You can also say how much weightage x has. Or I can also say if x changes by 1 unit, how much does y change? So if I say that, that is a slope. So beta 1 indicates how much does y change, increase or decrease, when x changes by a unit. That is del y by del x. Del means a small change, that is equal to beta 1. It's same as this. I'm just capturing this change with a delta. So that is beta 1. So why is it important? It says how sensitive y is to a unit change in the x, in the independent variable. If this value is higher, that means y is very sensitive to a change in x. Okay. If I talk about the weight example, then we talked about two variables, right? One is calorie intake and one is activity levels. So if I take calorie intake as x1, calorie, and activity levels as x2, right? Which variable will have more influence on your weight, x1 or x2? x1. So x1 will have a higher coefficient. So if the coefficient is, if I frame this equation, then how will it look? Y equal to beta naught. I'll come to beta naught. Beta 1 calorie plus beta 2 activity. So right now we said that calorie has more impact on weight. So beta 1 will always be higher. Beta 1 tells what? How much does y change when the calorie intake changes by 1 unit. So it is highly sensitive to the amount of calories consumed. So when I have several, now you told me calorie because you know it is a common thing, like we all know it. That is why it's easy to tell calorie here. But you might have variables where you do not know which variable have the maximum impact on y. Then how will you choose the most important variable? You'll go with the value of the coefficients, betas. Okay. Address this when we are doing multiple linear regression. Right now, we'll work with a single variable. Okay, so beta 1 is m. M is the slope of a straight line, right? So when we write a simple linear, now remember, this is a simple linear regression equation. The equation which you see here is a simple linear regression. Why do we call it simple? Because there is one dependent variable and only one independent variable. That is why it's called simple linear regression equation. What is beta 1? Beta 1 is equal to m. That is the slope or the sensitivity of y to x. So beta 1 is called the coefficient. What is beta naught? Now if I put x is equal to 0, what will the equation turn to? Y is equal to beta naught. Right? Say x is equal to 0, then y equal to beta naught. That means what is the value of y in the absence of x? So if I draw a straight line this way, this is y, this is x. What is the value here? 0, 1. This distance is beta naught or the intercept. Okay, that is c. C in a straight line equation is equal to beta naught in a simple linear regression. So simple linear regression model, now you know, it's nothing but a straight line equation. Okay, where we assume there is a relationship, and that is one of the main assumptions, that there is a linear relationship between y and x. Done, people? So I'll not get into more theory right now because we are supposed to do hands-on, and slowly we learn all this. Now, okay, this is also with simple linear regression. Okay, one thing which we discussed yesterday, we said that there is always some error component, right? Whenever I'm saying the model is giving me an answer, I will never say the model is 100% accurate. The model cannot be 100% accurate. Right? There will be some deviation in the right value and the value the model predicts. There will be a slight deviation. Correct. Now, a difference. That difference is termed as the error. Okay. We also call it the residue. That is a part of every model. We always have something called an error. Okay. We a provision for error because we do not think 100% accuracy is realistic. Okay. Now, what is error then? The actual value minus the predicted value. What is the actual value? Y test. What is the predicted value? That will get the answers from the model when we feed in the test data. When I give in X test values, so I give in the data set, we reserve one row for test set, right? That is my test set data. So I give only the X values and I do not give the Y values. That is Y test I do not give, I give only X test. Then the model will come up with a prediction for Y. That is the predicted value. See, Y pred. How do we denote it? Y test, which is the actual value, is always denoted by yi or simply y. Y pred is what the model thinks the actual answer is. That is always denoted by y hat. If the green line is a regression line, a regression model, then what are the actual values? The blue parts. Okay. What does the model predict? If the model is predicting the value of these blue points, the prediction is made by the model. So where will the predictions lie? On the model. Here. So on the line, we'll have y pred, the predicted values. What are the blue points? Those are the actual values. That might lie on the line, that might not lie on the line. So if the model is 100% correct, so actual is equal to predict. The model is predicting accurately, 100% correct. Then it will lie on the green line. But it can be A is greater than B. Say the right value is 50. The model predicts the value as 30. Then this is true. The model can also overestimate. Say the actual value is 60, actual, and the model says no, the value is 100. Then what happens? Predicted is greater than actual, right? So where do the predictions lie? On the green line. Where do the actuals lie? Above the green line or below the green line? If it is below the green line, then what happens? Predicted value is greater than the actual value. This is the distance. In this case, what happens? The predicted value is greater than the actual value. If the points lie above the green line, say this point, in this case, what happens? Actual value is greater than the predicted value. So this difference is required because we do not expect 100% accuracy. Remaining beta naught, you all know. What is beta 1? Del y by del x, which I said. Y2 minus y1 by x2 minus x1. What is residual? The error. Now, if I say this is my predicted value and this is my actual value, what is the difference? This is the difference. This is what? This is the error, which you also call the residual. Till here we'll do. And then we'll go to the metrics. So we have the problem statement which we had yesterday and the basic assumptions of classical linear regression model, but we'll go through the assumptions one by one. For now, we'll just, okay. The second assumption says the independent variables should not have, there are several, but these are the main three assumptions. The independent variables should not have a mutual correlation among each other. This is one of the problems of multicollinearity, which he said we'll discuss later. Error terms should be uncorrelated and follow normal distributions. The error component are what? The residuals. So errors of one time period is not dependent on the other time period. The data of every time period is independent. So what happens in January, we do not expect the same thing to happen in February. The market situation might change. The environmental conditions might change. The data might change. So the error will also change. That is why we say error terms should be uncorrelated. Okay. We'll discuss this again. Okay, for now, for this use case, let us first now, before we start working in this use case, we'll load the basic packages. The 4 packages which we always do. Import Pandas as PD. That is all importing we need to do before we start working on any use case. Now, the next thing is what? Getting the data into the Python environment. So data is ideally in a local system. So we load the data in a data frame. Two-dimensional data. So we'll have to load it in a data frame only. Now let us say I'll call this data set data frame data. How do I read it? It's a CSV file. That is the most common format in which you'll get your data. Read CSV. And then the name of the file is salary data. And we'll use a head function. People, I'm doing it a bit fast so that we can complete and you have time to revise before you solve the next problem statement. So you can see the file later. All the codes are easy. Okay, so what do we have? Two variables, and we all said X is my independent variable and Y is my dependent variable. That is what we discussed yesterday, right? So here there are two variables only, one independent and one dependent will be one, but we have one independent variable. Because we have one independent variable, this is called the simple linear regression. Okay. Now let us go to the next step. Now I'll just test the first assumption. What does the first assumption say? Y and X should have a linear relationship. That is the first assumption. So let us test only the first assumption. Checking the linearity. And so both of them should have a linear relationship, right? So if we check for linearity first is, we'll go for a scatter plot. Because we have got two variables and for bivariate analysis, what do we go? We go for a scatter plot. Now, what do you want to plot and what is my dependent variable here? Dependent variable is salary. Independent variable is years of experience. So along the x-axis, I'll plot years of experience. So I'll say data dot years of experience. Somewhere I'm writing it. Make sure you always copy the variable names. Otherwise, because Python is case sensitive, you'll get an error. In the y-axis, that is the variable I mentioned next, salary. Okay, now we are being able to do this because we have got only two features. The moment we have multiple features and we are proceeding to multiple linear regression, we will not be able to check the linearity this way, the way I'm checking now. No problem, Rashmi. We have just started off. We are doing yesterday's problem still. Okay. So data was salary, and then now this is only for simple linear regression. Color is optional. You can give a color. I'll give a color here. Okay. You can even give markers. You can even give size. So let me give all of this. Marker is equal to just making the plots look better. Size also I can give say optional. Now we'll have to label the x-axis. That is experience. That is my independent variable ideally. Okay. And what is my dependent variable? That is salary. So I'll write y label. Okay. And then nothing else. We'll just go for plot.show. And we can give a title, that is, so that we know why we created this plot. Linearity assumption. And this is one of the most important assumptions. Without this, so this comes from the relationship, right? Cause and effect should have a relationship. This assumption is most important. If we do not have this relationship, we cannot build a linear model, a linear regression model. Okay. And then we go for plot.show for a global display of the plot and execute. So this shows an upward trend. So there is a relationship. When I see experience changes, salary is also changing. So they have a relationship, which is linear. Okay, now let us go to the next step. So first is the basic checks which you do on your data. So if I've imported the data into a data frame called data, I'll go for the basic checks. What are the basic checks? Like we have seen some rules. I'll go for data.info because it is a summary of the entire data set. I do not have to check the size, the data types separate. It will give summarize the entire information. So this object is what? It's a data frame. Okay. Then how many rows? How many rows do I have in this data set? 30. That gives me the shape, right? How many columns do I have? 2. So 30 by 2 is the shape. Next is what? The index positions. So what are the indexes? Row indexes. In total, if I have got 30 rows, I'll start from 0. And what is the last row index? I'll have 29. If I go for columns, then what are the 2 columns? The first column will have an index position of 0. Second column will have an index position of 1. Now what is non-null? Non-null is how many non-missing values are there in each variable. So I do not have to go for a missing value check if I can understand the output of the info function. So I've got 30 rows, out of which each variable has 30 non-missing values. So 30, if 30 are the non-missing values, then do I have missing values here? No, no missing values here. So this directly gives me an idea that there are no missing values, neither for years of experience nor for SAP. The third thing what we have to check is the data type, which was important. Like we said, X and Y should have only numeric variables. It should not have categorical values. If it has, we'll have to go for an anecdotal. We'll have to convert it to numerical. So here, what are the 2 data types? Float. So numerical. So nothing, no work to be done here. But yes, you can still go for a missing value check if this is not sufficient. Or we can go for not an A or is an A. Let us go for is an A. Not an A will give you what? The non-missing values in each variable. Sum, and it will return a 0. Now let us create the first thing. Now our data is clean and it's a very simple data set. Just the first use case we do with a very simple data set. Now the second thing what we'll do here is, now we'll have to split the data. Now we have already identified which is a dependent variable and which is an independent variable. So the second step is what? I'll create a separate subset for my independent variable and a separate subset for my dependent variable. And here I need the labels, right? What am I predicting? I'm predicting the salary. So I need the label. So it is required that I store it in a data frame. And arrays are not required. I can just create a subset. So creating the feature set. Feature set, how do we label it? We always label it as X. Now you can keep it as a lowercase x2 and dependent variable set or outcome set. That is Y. The X is what? From my data, which is the variable in question. So X is my years of experience, right? So I'll take all the rows and instead of writing 0 as the index position, because years of experience, what is the positive index is 0. What is the negative index? -2. I can write -2 too. So what will I do here? I'll say take all the rows using an ilog function. If I want to split this data, I'll say ilog, that is slice the data frame using the ilog function. What are the row arguments? I need information about all the 30 employees, right? So I'll give a colon. But do I need all the column information? No, because I'm creating my feature set. So which columns will I choose here? I'll choose only years of experience. If I go with the negative index, I can do that. So what will I do? -2. And that is a for the dependent variables, what do we do? Data.ilog. Okay. Now I'll go with all the rows. I need all the employee information, but I need only the salary variable. So what will I do here? If I go with the negative index, then it's -5. So both my subsets are created. Now see if you have got it right. X.head. Print out the top 5 rows of the data, and that is 1.1. So these are the experiences. Now, if I wanted a 2-dimensional format, 1 second. These are just giving you the values, not the labels. So these are the salary. These are the years of experience. So 1.1, 1.3, 1.5, and so on. And if I go for Y, it will give me the salaries. So we've created the feature set and the dependent variable set. X plus Y will give me what? The total data set. But once we split the data into a feature set, now remember, if I'm just slicing the data with the help of the log, without the log function, say, I'm just slicing, remember the feature set always has to be 2-dimensional. Okay, but because we are using an ilog function, and ilog function specifically is used when you're creating a subset of a data frame. So the resultant object is a data frame. X is also a data frame. How do you know? It is just a series of values. That is the reason you're not getting it in here. You're not getting the labels here. Okay, let us split it a bit differently. Need not store at least X, you have to store it in a two-dimensional format. These are CDs. That is why we are not getting the labels. So we can split it a bit differently. Say data, and what do I slice from here? Dialog how to make it work. So it is all the rows. Okay. All the columns excepting the last column. What did I do? I said all the rows, all the columns excepting the last column. Means I am pointing to which variable here. The last column will have an index of -1, right? So I said choose all the columns, but leave out the last column. So how many columns are left? Only one column is left. So it will take up. Why did I do that? I could have simply worked with a series of values. But when you're going for the feature set, it has to be two-dimensional always. Y can be one-dimensional. Now, when I check with the type or the data type, it is a data frame. That is what we want. It's two-dimensional. Now, if I print out X now, Y can be one-dimensional. No problems with Y. Two-dimensional, that is when you have the labels and the index positions. Okay. Now, Y is a series, and that is okay. Y, you can keep it as a series. Okay. So, first split is done. What is the second split which we are going to do? We are saying the second split. Now, X is created from the data. Now, further, we'll split X now. This is my data. Correct. I split it into two parts, X, and I split it into Y. This I'll further split, right? One part will be called X train, and the second part will be called X test. Similarly, I'll split Y into two parts. One part will be called Y train, and one part will be called Y test. And eventually, if I add all the four subsets, I'll get back the main data. If I add all of this, I'll get the main data back. Right? It's just I'm further subsetting X and Y. Correct? Okay, let us do that then. Okay. So who does this splitting? Now yesterday we said that we'll be splitting the data set in the training set and testing set. But in what proportion? Now when we were doing the example, we saw that the rows were not chosen sequentially. It is not that I'm saying that I've got 8 rows. I want to use 6 rows for training the model and 2 rows I want to reserve for testing the model. So how will you choose the 6 rows? I can choose 1, 2, 3, 4, 5. First 6 goes to training set. Last 2 goes to testing set. It is not chosen that. Why? Because we build probabilistic models. In this case, the selection is done randomly. Okay. So when we say that I want to choose, say 80% of the data as my training set. Now there are 3 thresholds. When I'm going for a partitioning of my data set into training and testing, there are 3 proportions which we go by. First is 80-20. Obviously, more proportion will go for training the data, training the model, sorry. And less proportion will reserve for testing the model. Okay. Say 80-20, 70-30, or 75-25. But you can go with your choice of the splitting ratio. These are the standards which we use. So 80% of the data is used for like creating your training set. What is the training set? X train, Y train. What is the testing set? X test, Y test. So larger proportion we use for training the model, that is 80%. In this case, you can go for 70%, you can go for 75%. Yeah. These are the 3 thresholds. But again, though you can change the splitting ratios, there are 2 things here. If I choose 90% of my data, say you do not agree with 80%, say 90% I'll choose 10% for testing. Now there is a difference in opinion. We say that if you just reserve 10% of your data for testing, you are not evaluating properly. Your model's evaluation is not sound. Say you are having 3 questions. But say out of 10 questions, I ask you to answer only 1 should be correct, then you are passing, right? So only 1 out of 10 you'll have to attempt, you'll have to be right to pass. That is, we are not evaluating you very properly. So ideally, we should make it much more stricter. We should regulate it more. So out of 10 questions, you'll pass only when you are correct 8 times. So I give more information. I tell the model to predict on more information. Means I am evaluating the model more efficiently. But if out of the total data, 90% I reserve for training and only 10% of the data is reserved for testing, then ideally I am not evaluating the model well. Now I can decrease this. So you can say, why not 60/40? 60% is the information you give to training. 40% I will say that yes, that is right. So I should give more information. I should reserve more information so that I can test the model well, whether it's working or not, or whether it's making accurate predictions or not. So I said we should reserve more data for testing my model. And we go for a 60/40 split. Then there is another problem. That was I'm giving very less information to the model to learn from. And if the model is not learning well, how will it predict well? So increase the training set proportion. So there is always a trade-off here. That is why the standards are, give me a moment, people. So because there was always this trade-off, that is why we go for standard splitting ratios, 80%, 20%. Now when I say 80%, say I've got 10 rows of data. And I choose 8 rows as my data. I will not let it sequentially because at the end of it all, we are always leaving a scope for error. So we are building probabilistic models. We are not claiming that the model will be 100% accurate. So to remove any bias in our selection or in the learning, in the model's learning or the model's performance, to avoid any bias, we do the selection random. Okay. So when I say out of 10 rows, 80% of the data should go for training the model. I will not choose row 1, row 2, row 3, row 4, row 5, row 6, row 7, row 8. I will not choose any sequence. If I choose in a sequence, then I'm being biased. Okay. I will always go for a random selection. Random selection is what? Any row can go to the training set and any row can go to the testing set. And the model has to perform well because the model will be facing changing data, right? At the end of it all, when it's deployed in production, we do not expect the same data. The model will face the same data only. So it will have different data. The data is something which never is constant. It's always changing. So when you're training the model, ideally the choice of the data which from which the model learns from should also be randomly selected. There should be no rule or bias when the model is learning from a set of information. It can be any. Okay. So the choice of the training set and the testing set in the required proportion is done randomly. So if I say out of 10 rows, 8 rows will go to the training set. Any of the 8 rows can be a part of this 80%. So it is random. Okay. Now let us do this. But who does this selection? Out of 30 rows, if say I want to go for 80/20 split. Now who will choose this like 80% of data? I'll not manually choose. So we again have a method to do that. Okay. What is that method? So we'll have to import that method from the package itself, from Scikit-learn. So Scikit-learn is referred to as sklearn. From Scikit-learn, from Scikit-learn.model selection. That is the module name. Scikit-learn is the package name. Okay. From Scikit-learn model selection, we will import the function. What is the function called? Train, test, split. Okay. And this function will help me split the data in the desired proportion. Like if I want to go for 80/20, it will split it accordingly. It will do a random selection of 80% of the data and assign it to a testing set. Okay. The leftover, whatever rows we have, that will go to the testing. That will go to the testing set. Okay. So I'll have to specify the proportion. But what do I get post this selection, post this random selection? I'll get my 4 subsets, right? First is X train. First, we'll always specify the subsets which form the feature set. That is X. So what are the 2 subsets? X train, X test. Okay. Then the dependent variable set. Y train, Y test. The selection, these are the 4 subsets I'm going to get. Equal to. Which method will do the selection? This method or this function. Where will this method work? On the entire data. But I have already separated it into feature set and dependent variables. Now to specify the proportion, what proportion do I choose to split the data? Either the training set proportion I have to specify or the testing set proportion I have to specify. So let me specify the training set proportion. And let us go for 80-20, the first one. Okay. Now I'll say random state. Now I want someone to tell me what is random state. Now this is where I have got the maximum questions. I want everyone to tell me in a very simple way what is random state. Anyone aware of random state? Can I get a very basic idea of what is random state? First is fixing split data. Idly close. So random state is used to fix the selection of data. Means when I'm saying the train test split method will randomly select the data. Say, what did I say? 10 rows, right? In 10 rows, it is going to select. I'm saying that I have got 10 rows of data. 80% will go to training set. So any row can be selected in those 8. Right? I say 8 rows will go for training set. And the remaining, what is left over, 2 rows. That will go to testing set. So which rows will be a part of this 8 rows? Any row. It can be row 1, row 5, row 7, row 6, row 2, row. And any 2 rows can be a part of the testing because it is a random selection. But if I do not fix this, so this is my say 1, 2, 3, 4, 5, 6. And what else do we have? Let's keep 9 and 10 here. Okay. So 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, and 8. Right. Yeah. This is my training set and this is my test set. Who did this selection? This method did this selection. Now say if I do not fix this and I run this method again, I tell this method. So I stop this here, I execute this, and then I close this session. And tomorrow again I open this file. And again I'll have to run all the codes. All the variables will be lost when you close the session. So to again rerun it, recreate the objects again. Now when I come to this point, again I use this function. Again I say this function, let's say I'm giving you the data x and y. The training set size will be 80%. Now split the data. Do you think it will keep the same rows? 1, 5, 7, 6, 2, 4, 3, 8, 9. It will go for a different selection. A different selection of 8 rows. Okay. So this training data will keep on changing no matter how many times I execute the code. And I can execute the code multiple times because every time I close the session, all the variables are lost. Again, I re-execute, right? So every time I re-execute, I'm going to get a different training set. I'm going to get a different testing set. But if that happens, if I get a training set different and a testing set different every time, then what is the challenge which I'll face? The model will always keep on learning from different information each time. Every time it's going to learn from a different set of information. And if the model keeps on learning differently, it will perform differently. Because once the model has learned, I will be testing the model. The testing set is also changing, right, every time. The model will give me different performances each time. But how do I evaluate the model? By the score, right? So the score will also keep on changing. But I have to give a fixed score to the model, right? I cannot say that today the model is working with 80% accuracy. Tomorrow it's working with 60%. Third day is working with 90%. Fourth day is working with 70%. I cannot keep on changing the accuracy. It should have a fixed accuracy. So to have a fixed accuracy, I have to fix the data from which it is learning. How do I fix it? I fix it with the help of random state. There is the argument which you use within the function so that the selection is fixed by a number. Okay. What is the number? The number is 42. Okay. I can go for a different selection with some other number. So random state, though we usually use 0 and 42, those are not the standards. I can use any positive integer value. Any positive integer value will be able to fix the data. But for simplicity, because there can be many values possible, it cannot be a float value, it cannot be a negative value. It has to be a positive integer value. Okay. But there are so many combinations possible. Which number will you choose? That is for simplicity, we use 0 and 42. Now say to demonstrate that, say I remove this random state. So I just removed this entire argument, random state equal to 40. This was what I did, right? So let me re-execute this. Run on source. Now let us see the first 5 rows or first 2 rows of X string. Note the index position, first 2 rows, right? 2 rows of X string. What are the 8 and 20? Now what happens? I re-execute this again. And now I see the top 2 rows of X string subset. 8 and 22, it was 4 and 9. Again I execute this. Again I display the first 2 rows of X string. Changes. So what happens is my training set constantly changes. So the subject from which the information from which the model is learning is also changing. If the information changes, the model's learning changes. If the model's learning changes, the model's performance changes. And every day I'll come up with a new evaluation score for the model. That can be very confusing. Right? That is why we have to fix it. Now say I fix it with the random state. Positive. Now let me execute this. Now let us display the top 2 rows, 28 and 25. Now again I close the session, tomorrow again I open the session, again I run this code. Now again I try to display the top 2 rows. Same, 28. Again I run this, again I run this, 28, 25. So it is fixed now. Now it will not change anything. Okay. And obviously if the information from which the model learns does not change, the model's performance will also not change. If the model's performance does not change, the evaluation score will be the same, no matter how many times you open up, close the session, and how many times you open. So what is the significance of 42 and 0? We use it to make the thing simpler. Because now you can think of some other value. I can think of some other value. But our results will not match. Say I am thinking of 42 and some person in this session, she thinks of 24. What is going to happen then? There is no problem. 24 is also good. Or say 240. That is also right. It's a positive integer now. What is extreme now? 28 and 24. These 2 rows are selected as my training data. What will happen for this participant? 17 and 3 is the data chosen for this random state 240. It is getting fixed because if I execute this again and execute this again, see, it does not change. 17 and 3 is fixed. But the data from which the other participant, the training data and my training data is different. But the model is same, the data is same. So we both will come up with different results. So when you're working as a team, it is recommended that all of us keep the same random state. But all of you can come with different numbers. Like I'm thinking of 240. Someone might be thinking of 200. Someone might be thinking of 2400. Anything. So that is why we keep a basic one. 0 and 42. Okay. Purpose is just to fix the selection. Nothing else. So we keep it as 0. Everyone understood this? People who are doing it for the first time. Laksha, again, you are late today. Okay, so we had this train display. So what did we do with random state? Random state ensures reproducibility of the output. So whatever output you get, you can reproduce it. You can regenerate it. That is what random state is used for, to get the same output every time. Okay. So here we can fix it with any number. You can use any positive integer value. For simplicity purposes, we use 0 and 42 as the random states. Okay. So it ensures the training set from which the model learns is fixed. Okay. And because the training set is fixed, or the information from which the model learns is fixed, the model's performance will also be fixed. It will not change with repeated executions of your code. Okay. So we have split our training set and testing set. What is the next step? We'll import the algorithm from Scikit-learn. Okay. So from Scikit-learn, the module name is linear module. Okay. This module stores all the linear models, the models which work on linearly separable data. It contains all the algorithms which are fit on linearly separable data. Okay. So from scalar linear model, which is the module name, we will import linear regression. But this is a class, right? We cannot work with classes. We ideally have to have an object which will do the learning and give us the output. So we'll create a model object from this class. Let us call this model object simple linear regression, SLR. So this object is an instance of this class. Now the model will learn from the training data, right? So we have to fit the training data to this model. So we call this training the model. SLR. Using the fit method, we will be fitting the training data. So X train, comma, Y train. Okay. So my model is built. It has learned from the training data. Now what is the next step? We'll try to. Now my model has learned from the training data. So now I'll test the model. Okay. So we'll go to testing phase. Okay. Now the model has to, now we'll give just the X test. That is the input to the model. That is the years of experience. And the model has to come up with this prediction on the salary given the years of experience, right? So we'll store the model's responses in another object. We'll call it pred. Okay. The model predicts. How does it predict? It predicts using a predict function. On what does it predict? It predicts on the input, right? What is the input in this case? X test. Okay. So it predicts on all the years of experience which is there in X test. Ideally 6 if we go for a 80-20 split of 30 rows, 80% means 24 rows, right? And the remaining 20% means 6 rows. So it generates predictions of the salary on 6 years of experience, which has been randomly selected. Now is the time when we'll try to evaluate the model, how well the model performs. For this, one of the main metrics, there are several metrics which we use to evaluate the performance of a regression model. One of the primary is R-square. It usually tells us how well the model fits the actual data. Means what? If this is your actual data, this is your model. If your actual data is this, then the predictions are very close to the actuals. It is a good fit. Now, if I have the model as such and the actual observations in this fashion, this is case 1, this is case 2. In case 1, the predicted values are very close to the actual values. So the model is a good fit to the actual observations. In case 2, the model is not a good fit to the actual values because the actual values are very far off from the predicted values. Where do the predicted values lie? On the slide. The actual values are very far off. Right? There's a huge deviation. Deviation means error is more. So in this case, the model is not a good fit to the actual values. So we'll go with 1 as the better model. Now, what is the range of R-square? The R-square ranges from 0 to 1. So closer it is to 1, it is better the fit. Okay. So a model which has an R-square closer to 1 is a good fit. If it's closer to 0, that means it's a bad fit. Or the actual values are very far off or has a huge deviation from the predicted values. If there's a huge deviation, means there's the actual value say the predictions will lie on the model. There's the error, right? So if the model is a bad fit to the actual values, I'm ideally having a huge error. Means the model is not being able to predict the actual values well enough. So the error component increases. In this case, look at the error component. It is much lesser. So R-square is also called the goodness of fit. This is a standard metric by which we evaluate the performance of a regression model. Okay. Now there are other metrics too, like mean, squared, error. Okay. Now if I just go with the name, mean, squared, error. Okay. What is error? How do we measure error? The actual value minus the predicted value. So this is step. Next come to this squared. Squaring it. So why do we have to square the error component always? Because when we are finding out the error, it is A minus B, right? Actual minus predicted values. Now, sometimes the model might overestimate. Sometimes the model might underestimate. If it overestimates the salary, then what happens? The predicted value is greater than the actual value. If it underestimates the salary, then predicted value is less than the actual value. So this value might be positive, it might be negative. But I cannot have a negative error, right? I have to have an error, and that has to be positive. So that is the reason we square it up. Why do we square it up? So that we end up with a positive value. Squared is squaring it. And then mean. How do we find out the mean? The mean is, how do we find out the mean? 1 by x summation of a minus b whole square. This gives us the mean squared error. Now there is one more metric which is called root mean squared error. Now these three things are already there. What is missing? Root. So I'll just do a square. This will give me the formula of root mean squared error. Now, when I talk about mean squared error, root mean squared error, what are these? These are error components, right? So this should be as low as possible. These are also metrics by which we judge the performance of a regression model, but they do not have a threshold. So we cannot say that this error, if the mean square error is this, then the model is good. There is no standard threshold. Like R square has a threshold, right? It should be greater than 0, less than 1. If it's closer to 0, we say the model is not performing well. If it's closer to 1, then we say the model is performing very well. So we have a threshold range within which R square should lie, and referring to which we can say whether the model is performing well or the model is not performing well. But for mean square error and root mean square error, the lower it is, the better it is. But there is no standard threshold. That is why we do not go with root mean square error or mean square error. At times, we might have to go for both. Then what will we say? If the mean square error is, say, around 23%, if this is the mean square error, 23.06, then how do we say whether the model is performing well or not? We'll say the model's accuracy is approximately 80%. So out of 100% accuracy, if this is the error component, then the model's accuracy is nearly 80. We cannot say exactly, but we say nearly 80%. So the model is performing well. That is how we conclude. In case we use mean square error or root mean square error. But the standard metric is always R square for evaluating a regressor's performance. Okay. So we'll go with all these metrics, but ideally we'll not be able to give a definite answer on the model's performance. So we generally go for R square. Now, like I'm always saying that it's a metric. Metric is what? A tool to evaluate the model's performance. That is what we call a metric. Every type of model, be it regressors, be it classifiers, has some standard metrics. What do the metrics do? They're nothing but a function, which will help you for calculate the model's accuracy, how accurate the model is. Usually, how do you find it? A minus B, that is the error, by the actual. But I will not do this calculation for every value, right? Now, this is just 30 rows, but you can have millions and millions of records. So you'll have to do all this for each record, and then you have to sum it up. So that is a huge task. So that is why we use certain functions which will do this computation and give you the overall accuracy. So those functions are called the metrics. So from Scikit-learn, metrics will import the R2 score. Okay. But again, I am importing the class. So what do I have to do? I have to create an object, R square. Now, R square is an instance of which class? R2. And how is it computed? It is computed by plugging in the actual value, y test, and there is the actual answers, right answers, and the wrong and the answers given by the model. Those are stored in that. Now, what do? We print out the value of R square. And that gives us an accuracy of 90%. So 90% of the what did we say? What did we assume in the beginning itself? The salary will be dependent on years of experience. If the years of experience changes, the salary will also change. So my dependent variable will vary with the change in my independent variable. That is what we know till now. So 90% of the variation in salary is due to the change in the years of experience. That is what it tells. Though in simple terms, we would say the model has an accuracy of 90%. What is the 10%? 10% error. Why is the model not being able to predict the salary by 100% accuracy? This 10% gap is due to other factors, other errors, which the model is not accountable of. So what kind of other errors? Those will read when we are going through the R-square metric in detail. The total variation in the y value is captured with, is called total sum of squares. Total sum of squares. What does it measure? The total variation or the total change in the dependent variable. It's called TSS. It is the sum of RSS plus ESS. What is ESS? Explained sum of squares. What is sum of squares? Every time I'm saying sum of squares, sum of squares. Sum of squares is what? Sum of squares is right now the error component. We are always squaring it up, right? And we are not computing the error for a single observation. We are computing the error for all the rows. So we'll have to sum up all the error to get the total error, right? And why squares? Because we want to end up with a positive value, then a negative value. The error component is called the sum of squares. We usually refer to it that way. Square because we want a positive quantity, and sum because for every record, for every value, there will be an error, right? Every prediction and every value in X test, there will be, if I compare Y test and pred, there will be an error for each value. In this case, we'll have 6 such errors, right? We'll have to sum them up to get the total error, right? That is why sum, and squares we know why. So explain sum of squares is what? The error which is due to the model. Error due to the model. Or variation in Y which is due to the model. What variation? Variation from the actual value. The model's prediction, how different it is from the actual value of Y. That is the variation we are talking about. That is called the error, the difference between the actual and the predicted value. So the variation due to the model is called explained sum of squares. Means when the salary is changing, okay, it is not only due to the years of experience, it is due to other factors too. Okay, we'll talk about what are the other factors. This is the change in the salary due to other factors and not due to salary, and not due to experience, that is X, is captured by RSS, which is called residual sum of squares. This is the change in the dependent variable due to other factors, not due to the model. Factors which we cannot control. Now, what can those factors be? External factors. Like I said, data will always change. It is never constant. Why does it always change? Because there are several other factors, the market conditions. Now, let's talk about salary. The salary might change due to several reasons, not only due to years of experience. It can be that the current market rate for a particular designation is this. It has increased. So then all the companies will have to offer a competitive salary. They'll have to abide by that prevailing market rate. So in January, it was something else. In February, it might increase or decrease, depending on the demand for that particular expertise. So if it decreases, then naturally, it will not be, the model will not be trained on that, the market conditions. Right? So the model will work on the data which you have given. There's no idea of how the market is functioning or what market rate for a particular expertise is at that point of time. It is working on historical data. So the prevailing market conditions is one of the factors that the model does not learn about it, or it cannot learn about it. Second thing is what? There are other factors like the environmental factors. Okay. Environmental factors are what? Like, say there is a natural calamity or there is a lockdown. Okay. And then most of the people are losing their jobs. So demand for that particular expertise is dropping. Rate or the salary compensation will also have a change. Also, there is an environmental condition. It means you do not have a control over it. The pandemics, there is environmental condition, which we cannot detect from beforehand, or we cannot track beforehand. So there are environmental conditions, there are market conditions, and there are human errors. Now, say someone has created this data set, right, which we are using right now, salary data. They have inputted this data. So if this was the years of experience, this was the salary. Someone has done the manual entry, right? Now, say that person makes a mistake. Instead of writing 10.3, the person is thinking about something else. And he writes 3.10, 3 years and 10 months. And he has given the salary alongside. So that is a manual error. Even errors cannot be accounted because people do not do it intentionally, right? It's by mistake. So those kind of errors will also have an impact on the final predictions made by the model on the salary, right? The predictions will get impacted and the deviation will increase. That will increase what? That will increase the total sum of squares. Or the total sum of squares is ideally the total error. The error is due to the model when the model has not learned well. And it can be also due to external factors which the model is not responsible for. Both of them contribute to the total error or the total deviation in the y-values. Now, but we are not concerned about the external factors. How do we know the external factors? How is it going to change? We are concerned about the model's performance. So if I express R square in terms of the errors, then what is it? ESS by TS. That is out of the total error, how much is the model explaining? How much of it is due to the model? That is why when we say 90%, we directly do not say the accuracy of the model is 90%, though we refer to it in simple terms, we talk about it this way. But in reality, how would we explain this 90? It is the variation in the y values that is explained by the model. So the model can explain 90% of the variation in the salary. So it's that efficient. It can capture most of the changes which is happening in the salary. The model can capture most of the changes. That means it has learned that much of information. It has learned well. So it is being able to track the changes in y well. The remaining 10% is due to factors which the model is not responsible for. Like I said, market conditions, manual entry errors, environmental conditions. That that can explain the remaining 10% variation in the values of y. Okay? So that is also there in your document. So it is good to know it. Like you'll explain R square in this terms. Now R square will lie between 0 and 1. So now, right now 0.9 is closer to 1, right? So what did we do? We have built a very good model. A model which can explain the changes in the salary. It has learned well to explain the changes which are happening in the dependent variable. Okay. Now, if I give you the like content, it will be ideally it's not explained that elaborately, so it might be a challenge understanding. Download this document, people. It has all the algorithms explanation. What is linear regression? What are the assumptions? It's explained in very simple terms. Okay. Now that is all. We have found out the final equation. Now you can predict on new data. You can visualize. So what is left here? So we'll take a break. Means I'll stop. You'll go through it. What is left here? Visualizing the model. Now remember, you can visualize only a simple linear regression model because we have got 2 dimensions, right? One is my dependent variable, one is my independent variable. If you have several independent variables, then you will not be able to visualize it the way we can in this case. Because what we can visualize is only 2 dimensions. We cannot visualize multiple dimensions. So visualizing the model, that is left. What else? Prediction on new data. That's it. So we'll do both once it's through with this. Now let us go with the next step. Visualization of the model is done and prediction on new data is left. Okay. Now see, we'll try to frame the equation, right? Now we know what is the equation. The equation is what? Y equal to beta naught plus beta 1x. That is the equation of a simple linear regression model where y is a dependent variable, beta naught is the intercept. Beta 1 is the coefficient, right? When the model is built, right, then we will not get what we'll get? The predicted value of y equal to the predicted value of the intercept plus When we go for predicted values, we have a hat on top. That is how we denote predicted values. Okay, into X. Now this will not be predicted, right? Because this is given. This is external. What will be predicted? The value of Y will be predicted by the model. Beta naught is the intercept which will be predicted by the model. So there will be beta 1. There is a coefficient value which will be predicted by the model. And what is X? X is the input. Right? So we can easily frame this equation. How? Let us do that. That is actually what the predict function does. Let us see this. See, if I want to find out, so predicted value of Y is what we want. Say I plug in any years of experience and I want the salary estimation. That will be Y hat, means predicted value of Y, or predicted salary given the years of experience. But to create this equation, what do I need? I need the predicted value of the intercept term value which has been predicted by the model, and the coefficient term value which is predicted by the model, right? So if I try to write this equation, it is Y hat, I'll write it this way, is equal to beta naught plus beta 1, that is your intercept. Hat means what? The predicted value, or you can write pred, into X. X is external, right? So that is what we are going to do. Input the value, and we want the model to predict the outcome. Okay, now if I want to give the values and if I want to frame the equation, how will it look? So first I'll have to get the predicted value of the intercept, predicted value of the coefficient. From where will I get the value? From the model itself. So what will I do? I'll give the name of the model to get the predicted intercept. Yes, okay, one second. Sorry. So what is the final equation once your model is full? We know the initial equation, right? That is Y equal to beta naught plus beta 1. Where what is beta naught? The actual intercept. What is beta 1? That is the actual coefficient. But the model has been built, right? For the final model, this is the actual value of phi. Now I'm building the model which will be doing the prediction. So this equation, post prediction, will look what? Y hat equal to beta naught hat plus beta 1 hat into X. X I cannot predict because X is the input, right? So this all will be predicted. Now this will be my final equation. So let us try to create the final equation. So to get the predicted intercept, what will I do? This will be given by the model itself, right? So I'll say, what is the model name? SLR dot. We call this beta naught as the intercept, right? So SLR dot intercept underscore. Underscore why? Because it has a private scope. Means it is specific to this model. I will get some other value for the intercept by some other model. For this specific model, this is the value of the intercept. So it's private in scope to this model. So what is the value? 25321. That is the predicted value of the intercept term. Now I also have to find out the predicted coefficient value to get the predicted coefficient. So what do we do? SLR dot coefficient, COEF. Okay. Underscore again because it's private. It is specific to this model object, that is SLR. And I get the value 9423 something. Now I can frame the equation. What is the equation now? So this is my equation, right? The beta naught hat, I already have the value. So I'll replace this. So this is my equation. Now beta naught hat, I have the value. There is the predicted value of beta naught. What is the predicted value? 253. This is the value. Right? Beta 1 is the coefficient term. What is the predicted value of the coefficient? This is the value. So I'll just copy this and replace beta 1 hat with this value into X. Now we use the model for prediction purposes, right? Ideally, what is the final usage of this model? I'll use this model to predict the value of a new input. Say the HR wants to find the salary to be offered to a person with say 13.5 years of experience, and it wants the model to come up with a prediction. What should be offered as the compensation? So The model has to find out this one, the predicted salary. But input is already given, right? 13.5 years. So what will be the salary of an employee with, you can take up any value. I'm taking 30.5 years of experience. Right? So now I'll plug in the value. Everything is there. I just have to plug in the value of the input. So into 13.5. Now work it out. It is 15243. The model says if a person has 13 years of experience, this should be the salary. 152543. This should be offered. Now, are we doing it right? Now say I can use the model for prediction with the predict function. The model has already been predicting salaries, right? For X test. I can use the same method, right? So I'll say prediction, predicted salary with the method new. Okay. Who will predict? The model will predict. How will it predict? Using the predict function. But on what? Now we have a new data point. What is the new years of experience? It is 30.5. I'll keep it 2-dimensional. Now run this and print this out. What does it say? 152543. An exact match. So this is, how do we get this value? By plugging all the values to the main equation of the regression model. What is this? This is the equation of the regression model. Of the linear regression model. Now I can have multiple inputs. So every time I do not have to do this computation. What makes my job easier? The predict function. Use the predict function, tell this model has to predict the outcome given the value of X. What is the value of X? 13.5. I did the exact same thing. I've just plugged in the value of X. The model equation remains the same. What do I want to get? The predicted salary or Y predicted, which is represented by a hat. That is a standard way of representation. So what is this point? There's a perfect match with the salary. So either you can plug in the value in the equation itself, or you can use the predict function to predict the outcome of a new input, because that is why we are building the model, right? At the end of it all, it will be deployed in production. When it is deployed in production, there will be different inputs plugged in, and the model has to come up with a salary given the inputs, right? So we just thought about 13.5 and this is the practice. Makes sense, people? Okay, now let us go for the visualization. So I want to visualize the model too, right? I've built the model, I have generated the predictions, I know how to predict using the model. So that now what will the, when the final model will be deployed in production, then what will happen? The HR will do exactly this. The HR will just give in the years of experience, and the model has to come up with a prediction of the salary that is to be offered to an employee with this much years of experience. So input will be given. The model has to come up with the output. And that is the entire purpose of building the predictive model, right? Okay. Now, if I want to visualize the model, I know it's a straight line model, right? Linear model, a straight line model. So visualizing the model. Let us visualizing the model. Remember, this visualization is possible because we are having only two variables here. Multiple linear regression, we will not be able to visualize the model. Now let us do that. First, I'll just increase the figure size. Figure and changing it from the default size of 6 and 4.2. Default size of 6 and 4.2. 6 is the length, 4.8 is the height in inches. Now I'm going to change that figure size, default one. I want to make it bigger. So I'll go for 10 and 6. 10 is the length, 6 is the height. The default size is 6.4 and 4.8. 6.4 is the length, 4.8 is the height. Okay, now let us go for this. So if I want to plot the actual values, which you have seen in the PDF, the actual values were just data points, right? Single observations. So let us plot the actual data points. What are the actual values? X test, Y test. The testing data is the actual data on which we are evaluating the model. Right? So we'll go for the testing data. Scatter, which will give us a scatter plot. What do we have in the x-axis? X test. Okay. What do we plot on the y-axis? Y test. Okay. And now let us give it a color. So let the color be blue. So blue was the color in the PDF too. And let us label it. Let us label this. Label it as the actual test data. Right? Now we'll plot the model. The model is a straight line. So what kind of plot? From Matplotlib, if I want to go for a line plot, I'll use the plot function. So plot and then x test on the x-axis. In the y, so what are the predictions? In the y-axis, I'll plot the predictions. So how did we store the predictions? With pred, right? So we'll go for pred. Color. Let us give it what was the color in the deck? Green. So we'll give green. Then this is a straight line, so I can give a line width. Line width is what? How thick the line will be. So this is how you customize your line plots. I hope you all know this from Matplotlib. So I can give any line width. Let me give it a 2. Line style also I can give, but let it be a solid line. And we'll label this, right? I'll label this and give it a name. Label this as the regression model. Correct? Now next is what? Now we'll go for the X label, Y label, so that the plot is understandable. So we'll say in x-axis what do we have? Experience, right? We'll plot the y-axis to PLT, Y label. That is my salary. Right. And then we can give a plot title. That is experience versus self. Or we can say, let's keep it simple, experience versus self. So how much does experience impact the salary? Now, I can also give, okay, let me put the value of R square, which is again a standard question which I get asked every time. Why can't we plot the value of R square? So let us do that. Okay, now let us give a name, that is experience versus salary. Okay, and let us go for the R square value. R square is square. Give it in caps. R square is equal to R2. And if you do it right or there's something wrong, square R2 square R2 R2 to 3 places of float. I think that is all. Let me see. Get an error, we'll have to fix it. And then what else? PLT.legend. Why do we have to give the legend? Because we have given labels. And then finally display the So in testing data, how many observations we had? We had only 6 observations, right? So 20% of 30 rows, that is 6. And we have done a split of 80-20. 80% is for 24. We usually visualize the test set results because the test set is ideally unseen data for the model, right? So we can understand the model's performance of the test set. Training data is the data from which the model learns. So we usually do not go for the training set accuracy or the training set visualization. We always go for that. Okay, I will keep the people. What did we do? 2 things we did. Visualizing the model, visualizations of the model, and prediction and new data. So simple linear regression, what was the equation of simple linear regression? It was similar to a straight line equation, right? Y is the dependent variable, which we are trying to predict, right? That's equal to beta naught, which is the intercept term. or the value of y in the absence of x. When you do not have any independent variable, then what is the value of y? Or if there is, what is the starting value of y? So then we have beta 1, which is the coefficient to x. X is what? The independent variable, which is the ideally the cause producing the effect y. This was simple linear regression. Now, when we talk about multiple x's or multiple independent variables producing the same impact, then we talk about multiple linear regression. Multiple independent variables will give us multiple linear regression. So usually most common is multiple linear regression, not simple linear regression. So what is the equation of multiple linear regression? It's y equal to beta naught plus beta 1 x1 plus beta 2 x2 and so on. Now there can be n number of independent variables. So it will continue till beta n xn. So this is the generic, and there will always be an error term, which is always there. So this is the generic equation of multiple linear regression. Okay, so in this case, the only difference is many independent variables instead of one. Everything else remains the same. Now in this problem statement, what is the dependent variable as per what you read from the problem statement? We have an e-commerce data set. So ideally we have this problem, the domain is e-commerce or retail, where we are trying to, so we have a data set, we have a historical data which is provided by them, where we have the customer details like email address, average session length, time on app, yearly amount spent, right? All the details of each of the customers. We will have to build a predictive model which will predict the yearly amount spent by each customer, or say of each customer. So how much does a customer spend over an entire year, okay, on this e-commerce website, given the customer information? This information can be used to give customers personalized offers or loyalty memberships, etc. So there can be different strategies taken up benefit such customers who have a higher. So what we are trying to predict is the year. Right now, what we are trying to predict is how much will a new customer spend over an entire year, and how do we come up with that? So when we are building a predictive model, ideally we'll predict for a new customer. What we have is the existing customer information. Okay, so we'll have a new customer and we'll have to predict how much the new customer will spend over an entire year, right? That is the problem statement. So we are predicting what? The spend of the customer. How much the customer will spend. Ideally measure it, say dollars. So it's a quantitative value. How much each customer will spend will be a quantitative value. So when we are predicting something which is quantitative, which can be expressed as a number, we are dealing with the regression problem. Okay. Where the dependent variable is something which we can quantify or we can measure in numbers. So it's a regression problem, first of all. That is the second step which you have to do. After reading the problem statement, understand what you have to predict. Then zero in on the problem type, whether it's a regression problem or a classification problem. Okay, and then proceed. So we have all this sorted. We know what to predict, what we are trying to do here, what kind of problem it is. Now, what kind of model will fit here? So we have learned about simple linear regression will not work because we have got different, what we see from the problem statement, the customer likes address, average session length, time on app. So there are different variables which along with the dependent variable. So we have multiple variables here. So multiple variables can have an impact on my dependent variable. So it will not be a simple linear regression. In case of simple linear regression, we'll have a single variable and we'll have a dependent variable. So this is a multiple linear regression model. So identify the problem type, select the model if it's a regression problem. So you select multiple linear regression. Now let us proceed with the solution. So first step is always importing all the packages, which will be as the first step. NumPy is into import Pandas, the basic 4 packages which you always have, ed, import pyplot as PLT, and finally import C1 as SNS. We will suppress the warnings in case we use a method which has been revised. So you'll get a lot of warnings. Warnings are nothing but messages. So we'll suppress the messages as well. Now let us import the data set and see what the data looks like. So I'll import the information and store it in a data frame. So pd.read CSV, file name, the first 5 rows of the data set, where you get an idea of how the data looks like. So as mentioned in the problem statement, we have got email address, avatar, average session length, time on app, time on website, length of membership, and yearly amount spent. Now we have already seen the problem statement, right? What we are trying to, so first step is what? Once I get the data set, understand the data. So here we have email address and avatar, which we know of every customer. We have the email, the contact information ID. Okay, so personalization of that. So all this are specific to each customer. Then we have average session length. What is a session? Session is the time spent when you come online till the time you log out. See, you log in and till the time you log out. That entire time you spend online is counted as one session. Average session length in generic we'll say the time a person spends online connected to the internet. That is the on an average. That is the average session length. On an average, how long does a person stay online? And this is over an entire year. Now, time on app is how much time a person spends, a customer spends on the e-commerce app. Okay. Time on website is visits the e-commerce website, e-commerce site's website, not purchasing through the app. Length of membership is how long the customer has been associated with this e-commerce firm, the length, duration. And finally, we have yearly amount spent. So from the problem statement, we know that this is our Y. Now we have to choose our excess. So it should, the excess we choose should give us, help us find out the value of Y, or say help us predict Y. So you've got many excess here. So if I identify Y, then remaining everything is my X. So there is email address, avatar, average session length, time on app, time on website, length of membership. Now going by all this, now you know the meaning, right? Length of membership, how long? So if you're using Amazon, you know what is the length of membership. Prime customers are people who pay a membership fee every year. So ideally, they have a long-term relationship with the e-commerce. They always purchase from the e-commerce. Some people are new customers, some people are old customers. So we know the meanings. Now tell me, which are the variables you feel we need to predict Y? So I've got many X's. Do I take all the X's? In the beginning, we said we do not work with too many variables at the same time. So if I have got 5 variables, I'll not take all 5. I'll take only the relevant ones, which will help me predict the dependent variable Y. Not be always taking all the variables at the same time. We might choose the number of variables we need to predict Y. In this case, what are the variables you think we need to predict the dependent variable, that is yearly amount spent? Can I have some responses here? Which are the variables you feel we need to predict yearly amount spent out of the variables we have here in the data set? Yes, people, quick responses here. Time on app, time on website, length and average session, length and average session length. Okay. So we are snipping off avatar, address, and email. Ideally, because these are customer identifiers about the customer, shares the identifiers for each customer. Now, identifiers will not help us understand how much the customer will spend. Yes, income can help us understand how much the customer will spend. But identifiers ideally have nothing to do. So we will not use email, address, and avatar. What are the variables which we have left? Average session length, time on app, time on website, and length of conversion. All of this will impact the yearly amount spent. First choice which you do of the how you select the variables, if you understand the data set. So you have to understand the variables in your data set to make a choice. Now I can Now, I do not need the entire data set. I need to drop all these variables if I want to proceed with the data set, right? So what I'll do is I'll update this data frame with the relevant variables which I need. Okay. So the first one is average session length. Second one, what we need is time on app. Last one is length of membership, right? Right. And these are the variables which we have. We are subsetting it from the main data frame and updating the data set. So now data will contain only this. Okay, we missed out the dependent variable. So yearly amount spent. Variables I need. So I am subsetting it from my main data set and updating the data set accordingly, creating a copy. Now we have this data set. Now let us go with the data, simple data checks, which we usually do. So we can just do info, and that will give us an idea of. Okay, so we have the information about 500 customers. Okay, and what are the variables? We have average session length, time on app, time on website, length of membership, yearly amount spent. All 500. So we expect 500 values for each variable here. 500 customers. So we have 500 non-missing values. So if we have 500 non-missing values, ideally we do not have any missing values. That means so non-missing values are 500, so no missing values. Then we have the data type. Right? Data type is float in each case. Float means all the data types are numeric. So we have all the numeric data types here. So no question of encoding here, no question of missing values here. And we have all the variable names. Now it is irrelevant doing a missing value check, but we'll still do it, isn't it? It will give us all zeros, no missing values in any data. Now the next thing, encoding is not required, as we see, all are numeric. Now the next thing what we can do is check for duplicated rows, right? So if there is any row which has a duplicate value, no duplicate rows present in the data set is very clean. Now we have got so many variables, right? 4, ideally. So the next step is when you're working with multiple variables, you need to find out the most important variable. That is always important. So the feature which is most important, or the feature which has the maximum impact on the dependent variable, that is very important. So which feature out of average session length, time on app, time on website, length of membership is most important or most relevant in predicting the dependent variable? That we try to find out always. Now, how do we understand which variable is most important? Give me a while, people. Now, out of these 4 variables, we need to determine which variable is most relevant. So, how do we understand that? Which variable will be most important in predicting, right? Now, for the first assumption is very clear, right? It should have a linear relationship. And when can there be it should have a relationship. That is what the first assumption says. The basic assumption that there should be a linear relationship between the dependent variable and the independent variable. So the relationship is very important here, correct? Now, if the relationship is strong, if the relationship is weak, that means even if I change the independent variable, it does not have much of an impact on the dependent variable. That is what we understand here. So here the relationship between the dependent and the independent variable will determine which independent variable is more important or more relevant. So where the relationship is very strong, I'll say that independent variable has a high impact or high influence on the dependent variable because they have a very strong relationship. So that the independent variable will be very important in predicting the value of the dependent variable in that. So the mutual relationship between the independent variable and each of the independent variables with the dependent variable will give us an idea of which independent variable is most important. So I'll take the relationship between average session length and yearly amount spent. I'll check the relationship strength between time on app and yearly amount spent, time on website and yearly amount spent, length of membership and yearly amount spent. So I'll see the relationship strength between each of these variables and my dependent variable. Where the relationship is strongest, that means that variable is highly related to the dependent variable. So that will be the most. If I'm talking about relationship strength, we'll talk about correlation. So what is correlation? the relationship between a pair of variables. And here, the one variable which is important here is a dependent variable. So I'll check the mutual relationship with the correlation function. So if I do that, data.correlation, all the variables are numeric. So we can directly run the correlation function here. Okay. Now, what am I interested? Not interested in finding out the mutual relationship between each of the variables. So this, we get a correlation matrix here. In the correlation matrix, what do we get? All the correlation strengths. The diagonal elements will always be 1, because the diagonal elements give us the relationship strength between one variable to itself. So what is this? This is the relationship strength between average session and the average session. If I go with this value, relationship strength between time on app and time on app. This is time on website and time on website. So it will always have 100% relationship. A variable with itself will always have a 100% relationship. Now the non-diagonal values will be of importance. This is the relationship strength between time on website and time on app. How close they are, or how closely related they are. What is the relationship strength? Now, we have two things. One is covariance and one is correlation. Now, covariance usually tells us about the direction of the relationship, does not specify the strength. So if I talk about two variables, it will tell me the direction of the relationship, whether they are positively related to each other or negatively related to each other. That is what covariance gives us an idea of. But what is correlation then? Correlation not only gives an idea on the direction of the relationship, but also on the strength of the relationship, whether they move together or whether they move opposite to each other. Okay, that is the direction. But how strongly they are dependent on each other is what correlation tells us. So what is correlation? It is covariance of x comma y, when x is one variable and the y is the second variable, by standard deviation of x into standard deviation of y. We use correlation why? Because we are not interested in finding the direction. We are more interested in finding the strength. And the strength determines which variable has a stronger or more stronger relationship with the dependent variable. And that way we can identify the most important features, which will help us predict why. So here what we'll check, this is my dependent variable. So I'll check the relationship of the dependent variable with either of the independent variables. So I'm interested only in this row. Now you might say, okay, that is what I'll ask you. Okay, so I'm just interested in this row. So what is the relationship strength? What is the correlation coefficient? Okay, this correlation coefficient is called the Spearman's correlation. Sorry, this is called the Pearson's correlation coefficient, denoted by a lowercase r. And what is the threshold value? R will lie between 0 and 1. Okay, closer it is to 0, weaker is the relationship. Closer it is to 1, stronger is the relationship. Okay. So R between length of membership by average session length is 6%, mentioned in absolute terms. This is 2.9%, 2.9%. Okay. This is ideally 6%. This is a negative relationship. This is 1. This 80% yearly amount spent. I am highlighting the wrong one. Wrong row. Sorry. We are us on the last row, right? This is the one. The relationship between yearly amount spent and average session length is 35%. Relationship between yearly amount spent and dependent variable here. Yearly amount spent and time on app is 50%. Time on website and yearly amount spent nearly 0. Length of membership and yearly amount spent 81%. So we have got the relationship strengths here. Now the relationship strengths will help us understand which is the most important variable here. Correct. And finally, we have 100% that is there. So going by the relationship strengths, what can I identify? Length of membership should be my most important variable because the relationship strength is quite high, 81%. So this should be my most important variable. Followed by which one? This should be number 1. Second is time on app. Okay. And third is average session length. Going by the correlation values, 81%, 50%, and 35%. Okay. Time on website has negligible impact. So 1, 2, 3, we have already ranked it. Now, what about the other variables here in the matrix people? Are these important? Say, take up the value of, what about all these values? this one, and say this one, the other values I think. Are these important? Should we consider this? What is 0.6? Relationship between length of membership and average session length. That is, now are these values important, people? Are these values important here? Why do you feel it's not very important? If you feel important, why do you feel it's important? If you feel it's not important, why do you feel it's not important? This is ideally telling me the relationship between a pair of variables, right? It can be average session length and length of membership, anything like between two variables. Why do you feel it's not important to you? When we are talking about multiple linear regression, another very yes, do we have a response? Correlation rather than it has 8 as strength or so, whereas others have 32. Talking about the values which I've highlighted in green, the correlation among the independent variables. So last row which I've highlighted is the relationship strength of the independent variables with each of the dependent variable with each of the independent. So I'm focusing only on the last row. What about the rows above that? Are the values important here? Values which you have? Okay, see. Now, okay, I did not explain this too. So now we come to the next assumption of classical linear regression. So I'll put down all the assumptions here. I have put down in simple linear regression. The second most important assumption is the independent variables should not have a mutual correlation. They should not have a mutual relationship among themselves. Like when we're talking about the example of, say, weight gain. Then we said that, okay, the weight changes depends on the number of calories, the amount of calories one consumes, the activity levels, the intake of the calorie intake, the activity levels, the amount of water a person has in a day, the number of hours a person sleeps in a day. So all these 4 variables have a direct impact on weight. But are these 4 variables related to each other? Maybe yes, maybe no. But here the assumption in linear is, so you might say that, okay, if a person sleeps for less time, ideally he'll consume more calories. So calorie intake and number of hours of sleep, or say water intake and calorie intake is also related. If your water intake is less, ideally the person consumes more calories. So there is a relationship. That is why what we do not want in a multiple linear regression. So one of the standard assumptions are that the independent variables should not have a relationship here. They might have a relationship, but that should be very, very insignificant. That should not impact. You should not have a very strong relationship. So in this case, what do we see? 0.6, very less, 6%, 2.9% negative. And then all the values which you see are 8%, negative again, negative 3.4. So all the values are very insignificant here. If I talk about the values in the upper 4 rows, not the last row, the remaining rows, apart from the ones, like the 100% correlations, the other values are very, very low among the independent variables. So what do we understand from this table is the independent variables do not have a good relationship. Like they are not dependent on each other. Very less, very low strength. Means even if they are related, the relationship strength is very low. So we can call them nearly independent. One variable does not depend on the other variable at all. So your time you spend on the website is not dependent on the time you spend on the app. So if I go by this, it is 8.2% is the relationship strength, this value, right? The value which we have highlighted here. That is the relationship strength between time on website and time on app, and that is very, very low, 8.2. So there is no relationship, you can say that. It's very insignificant. So how much time you spend on the website is independent of how much time you spend on the app. No relationship here. Okay. And that is what we want. We do not want a relationship to exist between the independent variables. Now, if we have that, then we have the problem of multi-coordinating, which significantly decreases the effectiveness of a regression model. Performance declines if there is and that is why it is one of important assumptions. When we are going for regulated models, then we speak more about it. So that is why we are not considering the other values in the code, because we assume when we build a regression model, the standard assumption is there should not be any relationship between the independent variables. So we have ranked the variables, right? 1, 2, 3, 4 as per importance. Now let us go with the next part. Now we'll see now we said that length of membership most important, followed by time on app, and then with average session length. 1, 2, 3. If the relationship is strong, it should be indicated by the scatter plot. So if I try to plot the relationship, it should display the results. What do you think? The relationship, it should be very, very strong. Now let us see. So we'll go for scatter plot. So scatter plot. Okay. In the x-axis, let us put the dependent. Let us put any of the variables here. Average session length. Independent variable, the first one. And what is my dependent variable? The dependent variable is yearly amount spent. And then let us give the source of the data. So average session length comes third, right? In terms of importance, in terms of the relationship strength. Okay, now let us go for plot.show. There is a positive trend here. We can see a positive relationship, but yes, it is not a very strong positive relationship, a strong linear trend. There is a upward trend, but not a very strong linear trend, or not a very sharp movement. There is upward movement, but not a very sharp movement. Means there is a relationship, but not very strong. So average session length, if it increases the yearly amount spent of the customer. So more time a customer spends online eventually leads to a higher spend by the customer. But that impact is not very, very high. Okay. That is given by 35%. Now I'll just repeat it for the remaining two. So this comes in number 3, 35%. Second is what? Second is time on app. Okay. So if I go with time on app, that comes second. The relationship strength is 50% here. So greater than average session length. So if I just plot this, yearly amount spent, right? I think. Now see, now the relationship depicts what? There is a relationship and there is a positive relation, which we have already seen. Positive relationship and the relationship is stronger. That is why we have got a sharp trend. Upward trend is there, and there's a sharp linear trend. Sharp linear upward trend. So okay, here the relationship strength is strong enough. Okay. Better than average session. Now the third one. So the most important relationship, right? The third variable is what? So we have average session time. Time on website has an insignificant. You can plot it, but again, if I plot this variable, what should I get? It says that there is no relationship, right? Zero. No relationship at all. Now let us see. So if I plot this variable around the x-axis and then print it out, it does not follow a trend at all. The points are all scattered. It does not have a steady upward or a downward movement. It does not show a movement ideally. Okay. That says what? There is no relationship at all. Why do we say that when it does not follow an upward movement? If I take a yearly amount spent of 500, right? Say I fix it at 500. Then if the time on website is 36, then the yearly amount spent is 500. If the time on website is say 38.5, it's the same yearly amount spent, relatively same. That means that if I increase the time on website, it does not have an impact on the dependent variable. So ideally, this independent variable has negligible impact on my dependent variable. So what is best? I'll not use it as a independent variable or a feature variable to predict yearly amount spent. Correct. Now the last one, the first one, which we said is most important, is what? That was length of membership, right? Length of membership. So I'll just copy this once more, paste it here. And we had an 81% relationship with length of membership. So this was what we ranked as 1, the most important variable. We've explored the remaining. Now let us now see the trend of movement here. It says 81%. So it has the strongest relationship, right? Length of membership and yearly amount spent has the strongest relationship. Sharp linear trend, right? So here it is a positive relationship with a very strong positive relationship. And that is the reason we choose length of membership as the most important variable. Okay. You can confirm that with the correlation matrix, which we did, and then you can also explore the bivariate relationships visually. Now the next thing is we also have to explore the univariate relationships. So now we have explored the bivariate relationships and we know we have ranked the feature variables as per their importance. So we said length of membership comes first, and then we have time on app, which comes second, and then the average session length, which comes third. Right? Now let us go for the univariate relationship. Why do we have to go for the univariate relationship? Or check the distribution of each of the variables here. Why is that important? Because the distribution, the data distribution of each variable also plays a major role. The distribution might be skewed. So one variable might contain extreme values or outliers. Then we need to scale that data before proceeding. Okay. What is scaling ideally? Yes, people. What is scaling or standardization? Scaling means putting all the values within the same range or within the same scale. That is scaling or standardization. So one variable might have extreme values. So if it has extreme values, it needs to be scaled. Okay. Or all the values need to be put within the same range. Regression models ideally does not require much of a scaling. Okay. It can work well without scaling. The regression models are ideally very strong models. So we can do without scaling, it will still give us a good accuracy. For that, we explore the data distribution of each variable. That is called univariate analysis. It's a part of EDA. Okay, now for this univariate, rather than doing it one by one, let us combine all the plots together. Once we combine all the plots, so when we are exploring each of these variables, these are all numeric. So if I try to explore each of these variables one by one, I'll go for a histogram or say a hist plot or a distribution plot or a disk plot. Means the plots which are meant for numeric variables. Let us go for a hist plot because histograms ideally do not give us a very clear idea about the shape of the distribution. Numeric variables should ideally follow normal distribution. Then only we can say all the values are comparable to each other. If the values are not comparable to each other, then there are outliers in the data. So to check it, first let us, if you want to do it in the same place, that is creating subplots. Now, why do we create subplots? So that we do not have to do what we are doing right now, scrolling up and down. Here, scatter plot, I'm seeing this, then again scrolling down for the next variable, again scrolling down to the next variable. That I do not have to do. I can have all the plots within the same place. And if I have all the plots with the same place, then it is easier for me. I do not have to scroll through. So that is why we create subplots. Now to create subplots means I'm having all the plots at the same place. So first let us change the figure size. It means I want to enlarge it and I want what is subplots. People, do you have an idea of subplots? Can I get a response here? Everyone has an idea of subplots. What are subplots? All plots, we split the plotting area. Say we have got one plot here, right? This one plot. And if I split it up into 4 parts, this is the default plotting size, right? If I want 4 plots together. So what will I do? I'll split up this plot into 4 parts. Okay, I'll put plot 1 here. I'll put plot 2 here. I'll put plot 3 here. I'll put plot 4 here. So breaking up the plotting area into 4 parts and accommodating 4 plots in the same plotting area, so that I do not have to scroll up down. That is, these are called subplots. So what do I have to do here? Here, if I split it this way, how many rows do I have? I'm splitting the x-axis and y-axis to create this 4 divisions, right? So how many rows here? How many columns here? 2 rows and 2 columns. I'm dividing both the axes, the x-axis and the y-axis, splitting both the axes into 2 parts. Then I can create these 4 divisions. If I want to create 6 plots, plot 5, plot 6. So split the axis how? 2, 3. Right. So it depends on how many plots you want to accommodate within the plotting area. That will give you an idea of how to split the axis, the x-axis and the y-axis. Okay. Here we have how many variables? We have got 3, 4 variables, right? That is length of membership, time on website, then time on app as a dependent variable. Average session length 1, 2, 3, and 4. 4 variables here. Even if we skip off average session length, which or the time on website, which does not have a significant impact on my dependent variable, so I can let it go. I'll not include it in my analysis because it does not show me a significant relationship. So what are the 3 variables we are zeroing in? The remaining 3, as well as the dependent variable. So let us do that. First, let us fix the axis and the size. So I'll say plt.subplots. Okay. 4 plots. So 2, 2. Depends on how many plots you want to fit in. 2, 2. And I'll enlarge the figure size. Why? So that I can get to see all the plots clearly. I'll increase the default figure size. So it is, say, the length is 15 and 8. Okay. So I've set this. Now let me go for the next part. So I'll go for a histogram plot. So I'll call that hist plot. In next, what do I have? I'll go for a single variable. So let us go for the first one. That is average. Let's go from first. Average session length first, right? Average session length. And then what is the position? I have to give the position to. If I create 4 divisions, then where will the histogram plot of average session length appear? That I have to specify. Okay. So I'll say axis. I want it in the first place. So that is first row, that is 0, and first column, that is 0. This is the position. Now, if I'm going for a hist plot, it gives me the histogram bars. But we do not get to understand the shape of the distribution by just bars. So what do we use? A KD, kernel density estimator plot. What is it? A smoothing line over the histograms. Why do we need a smoothing line? Because a shape can be specified by a line, not a bar. Right? So that is why we give KD equal to, so display the smoothing line, so that a smoothing line over the plot, so that we can get an idea about the shape of the distribution. Now, data source we'll have to specify. That is a data frame. And we can give a color because we are having multiple plots here. Something red. Now I'll repeat it for 4 variables for the remaining 3 variables. So I'll just copy this. And we'll just change the variables in question. Okay. The average session is we are done. Let us go for the next variable, that is time on app. Right. So let us copy time on app here and replace it, make the minor changes we have to do. So let's change this to time on app. What is the position? I want it in the next position. So 0 row, same row, and the second column. So I'll change this to 1. Color, I'll give it a different color so that we can differentiate. And that is it. The next variable in question, time on app, is done. Time on website we are not taking up because the relationship strength is very, very less. I mean, it is not related to my dependent variable. Okay. Close. Let's skip it off. You can keep it, but ideally it will not help you, even if you keep it. The relationship strength is very low, so we cannot find out the value of the yearly amount spent with the time on website information. Length of membership 0, 1. So we are done with this. Next row. So what is the row number? First row, right? First row, second row, first column. That is the position. Now I'll change the color again. So let's go for a different color. Okay. Now that is done, which is the next variable, yearly amounts. That is the only variable we have left. So we'll go for yearly amounts. I'll share this file once I'm done. So we'll go through this and ask me questions here. What is the position? We are in the second row, right? Second row, first column, second row, second column. Everything else remains the same. We can change this to green, say. And then nothing else. We'll go for the global display of the plot. Okay. So all are normally distributed. So all the variables have values which are comparable to each other. So we do not see any particular very skewed distribution. All the distributions are nearly normal. So we do not have to worry about scaling or standardizing the data. Now, it might be the data distribution looks skewed. Then what will you do? You have to standardize the data. In this case, not required. Nearly normal, all the variables. Okay. So that is, so we have a file, we have a data set where all the variables are nearly normally distributed, where all the variables are numeric. Okay, so we have everything as a plus, no missing values. So clean data. We have also decided on the number of variables we are going to include in predictive method. So everything is set here. Now what is next? We're done with the data paper. So what are we left with? We'll build the model now. So this data pre-processing is something which you need to be very, very clear with. Okay, because with the change in the data, it will not be the same. So you need to prepare the data well to get the model work well. So if you feed in bad information, wrong information, the model's predictions will be impacted as well as the model's performance. Okay, so you go through this and let me know whatever questions you have. You can ping me one-on-one. Go ahead, people. I'll ask you questions once you are done. 1 minute more. People, let me know what is the difference between KDE and a histogram plot. Why do we use a KDE instead of histogram plot? Why did I write KDE equal to true? If you do not give KDE equal to true, what happens in this plot here? Getting the curve to get the smoothing line. So if I do not give KDE equal to true, what you're ideally going to get is, say I skip this off. So for the first two, I'm doing it. Okay. Now let me see. So if I do not give KD equal to true, what will the histplot function give you? Only histograms. The basic, we create histograms with Matplotlib library too, right? With the hist function. And with Seaborn, we use the histplot function. That is the difference. Now, if I use Matplotlib library, I'll get this bars, histograms. But it is very difficult to understand the shape of the distribution using only bars. But when you have the smoothing line here, that is a kernel density estimator plot, you can understand the shape because you know how a normal distribution looks like. Right? If you know how a normal distribution looks, then you can easily understand whether this variable length of membership follows a normal distribution or not by the curve. So by understanding this smoothing line helps us to understand the shape of the distribution. If you do not give the KD equal to true, you'll ideally not get an idea about the shape because interpreting the shape from the bars is very difficult. Now, kernel, what is the difference between kernel density estimator plots and histograms in general? Kernel density estimator plots will plot the density of values against the intervals. What do histograms do? They plot the count of values against the average, against the variable. Okay, so here we are just having the count, the frequency. When we go for kernel density estimator plots, we go get the density against the intervals. So that is why we have a shape. With counts, we cannot have a shape. Difficult to interpret the shape. Why we are doing the scatter plots? Because we want to check the bivariate relationships visually. What we did is we inferred about the variables from the correlation values, strengths. So if I want to understand the relationships visually, like I'm checking it with a visual representation. Stronger the relationship, steeper will be the plot. Yes, KD we get only in histograms, his plots. Plot a KD as it is without his plots. That is also good. For a kernel density estimator plot separately without histograms. That will again give you the shape without the bars. In the graph, no. So when you're going for univariate means for one variable. You're exploring the distribution of values of one variable. You do not, it's not a bivariate, right? It's univariate. Univariate means one variable. You're not comparing it against anything. You are checking the distribution of values for that variable. Bivariate means two, by two. Here we are doing a comparison against two variables. We are checking the relationship between them. Univariate means I'm just exploring the distribution of values of a single variable. Some more time, you can take up the time, please. Let me know once you're done. Okay, go through the codes. Just go with the data and go for KDE. So see, Okay, whenever you have so many functions, right, it's difficult to understand all the functions. So what do we do here? See, in histogram plot, in hist plot, we just the histograms, the bars will be automatically displayed. You do not have a choice here. So what are the arguments you can give? Like I gave the KD argument, KD equal to false. By default, it is false. So if I want to plot the KD, I'll go for true. Similarly, you can just directly go for the KD. Like from the data, you just go for a KD plot. You cannot go for the data frame. You have to create it with an array. If you want to go for a KD separately, we can go for the other plots too. Let's take time on that. We have dist plot, we have dist plot, where you can always remove or eliminate the histograms and directly go for the kernel density estimated plot. Let me check if checking one variable. No. Series object has no attribute KD. Okay. Let's go for dist plot. Just for KD. SNS.dist. Now you have got dist plot. You also have dist plot. Let me go for dist plot. Okay. Now how do you check? You can check the what we have here. Histogram equal to true. Now the function is very simple. Like we give the argument for the variable for which we want to create the distribution plot. So I'll give x is equal to, let's take the same variable, time and hist. I'll give false. Check it again if this is what are the arguments say. So how am I checking it? I'm going for shift tab. So hist is an argument. Default it is true. I do not want it. And remaining is the same. Give the data source from where you're getting this variable. Because I'm directly giving the variable name, right? And say color is optional. Still, let us give a color here. Then go for plot.show. His plot by default will display the histogram, so you do not have a choice. Data equality okay. Then we'll have to do it this way. So when you're confused with the function, like I am constantly checking the arguments. So all the functions work differently. Okay. So you get a KD plot without the histogram. So his plot will definitely give you the histograms. If you do not want the histograms, only the KD, just go for dist plot. Or you can also go for dist plot. Okay, that will also give you. Next one, another function which we have is dist plot. So the T is not there, dist plot. Now check the arguments which we have here. Row column, okay, kind histogram. Now instead of kind histogram, if I give kind KD, the argument here kind, and I give, you get the option. Now if I say, no, I do not want KD plot, I want histogram plot. So just here. It will give me what? Only the parts. Why it is not an option in hist plot? Because hist plot is for histograms. So you do not have a choice of removing it. KD is an option. But for distribution plot or dist plot, which is ideally a distribution plot only, it's the revised version of dist plot, revised method of dist plot. So now we use dist plot, not dist plot. Dist plot is what we used to use before. Revised dist plot, distribution plot. Now here you have the option whether you want to plot the KD and check the shape of the distribution, or you want to go with histograms or the bars. Now in hist plot is just the histogram function. So here we do not have the choice. It will display this. I can additionally go for a KD. So data preparation is more or less done. We do not have anything else to do in data preparation. Now the final stage is model building. So let us build the model and then take a break. Okay. And on the other side of the break, I'll be giving you a problem statement which you'll solve. So now the next step is we have already done with the data preprocessing. Next step is what? Find out the feature set or separate this data, split this data set into two subsets. One will contain only the features, one will contain only the dependency. Let's talk about the future. Which variables am I taking? We already decided the variables. Right? One is average session length. This is the variable which I take. Again, when I said that scaling is not required, it depends on the distribution plots which you have done right now. So here we see more or less they are not normally distributed, so we do not have to go for standardization. Features. Third variable, you can include time on website, but it will hardly have an impact. Dependent variable is simple. It is like data. Like I said, the feature set should always be in a two-dimensional format. Dependent variable can, because we are creating only one, so it can be in one-dimensional form. Year label spent. That is it. Now we have created two subsets of our data. One is X and the second one is Y. Now let us go for the next split. So what is the next split? I split up X further into X train, X test, Y into Y train, Y test. So from it, okay. And then I create the subset X train, X test, function, and what is split X and Y. And then we need to give the proportion in which we want the split to happen. So this time we are giving 70-30. So that is also a choice which you can go for any splitting ratio. Test size is 30% and I'll use a random state to fix up the selection with a number, say, for example. I've got X train, X test, Y train, Y test. Next is what? Simple from Scikit-learn linear model. Regression. I'll give you more attributes and more work we'll do, but I'm just showing you the basic parts where we are just building the model and stop here. And the other side of the break, you'll be solving a problem statement. And I'll include more metrics here so that it is a complete use case. You can refer to it later. Linear regression, creating an object from this class. Steps are same. Okay. Now what do? We train this model, right? How do we train it? Just have to build a model on the other side of it. Train the model, how do we train it? We fit, using the fit method, we fit the training data, right? X train and Y train. Next step is to test the model, how well it has learned. So what do we do here? We use the model to predict. We use the X test as an input and allow the model to predict. Okay. We store the predictions into another object. So let it be read. Model will predict. How will it predict? Using the predict function. On what will it predict? On the input which the model has not been trained on. So X test is new data. X test is new data for the model. Okay. The model is predicting on X test now. It will generate the predictions, and where will the predictions get stored? In pred. Okay. Now time to evaluate the model performance. So where do we get the functions? From metrics, right? We import at. And again, this is a class, so we'll have to create an object. The object which will perform the computation is Arctu. It is an instance of which class? Arctu score. And what inputs do we have to give this function? The real values and the answers given by the model, and then print out output. That gives me an accuracy of 98%. So 90% of the variation in Y is explained by the model. So the model can explain the 98% of the variation in Y. How much it cannot explain? 2%. So ideally, that is the error component, right? So ideally, the model is highly efficient. So R-square value closer to 1, we have built a very good model. And that is what we get here, 0.98, close to 1. Okay. Now this is the simplest way I'll close this use case. Now this is the standard. So where do you have to think here? The steps are all the same. So where you have to split it into training and testing data, and then you fit the training data to the model. These steps are same always. Now when I give you, where do you have to think much? You have to think on the data, how you want to prepare the data, which variables you need to include, which variables you do not need to include, how to check the variables, which features are more important, which features are less important. That is where you have to think. The steps of modeling is fixed. How do you have to prepare the data? That is where you'll have to spend more time. That is where you have to do the thinking. The model building steps are standard. Like here, we did not do a scaling. You might need to do a scaling. So that depends on the data. So I hope these steps are similar to what we have done before, and you're all familiar with the steps. Now we'll go for a break. On the other side of the break, I'll give you a problem statement. Try to work on it. Okay, if you fail to do it, then I'll help you out. Okay. Or if you're getting stuck, the basic steps where you have to focus on are the data pre-processing steps, where you're preparing the data for modeling. You can always import the model and create a model object and train the model. And the model's performance. But the model's performance will be very much dependent on how you're preparing the data, the input data. So that is where you have to think. Anyone who's done with the use case, people, create the plots by yourself. And if you have not created it, in case, if you have not done it, then what do the plots tell you about the distributions? If I go for expenses on TV, nearly the same, constant expenses. So I do not see a major rise. I do not see a major fall. Yes, there is a fall towards the end. Allocating the resources towards TV ads. That is what we understand from the plot. These people, can I just have a response? Do you all see the plot from my screen, or you are creating your own plots? That is that TV expenses are more or less constant, with a sharp fall towards the end. Now, if I go with the radio expenses, nearly same, constant. So they are not increasing the expenses on the radio ads. It is relatively the same. But newspaper ads, we see a sharp decline. Means they have stopped spending on newspaper ads. That makes sense, right? Newspaper ads, how many people buy seeing ads from newspapers? Most of the people hardly read newspapers. And people who read newspapers do not go by the newspaper ads and go for and make a purchase. Mostly. People are mostly focused on TV ads, or say radio ads are still. But newspaper ads, hardly people will purchase. So newspaper expenses have gradually gone down sharply towards the end. So the data is not symmetric here. In TV, what do we see? The data, there are huge expenses in the beginning. Towards the end, the expenses fall. So we can have very low expenses for TV ads as compared to the rest of the expenses. If we compare all the expenses, then TV ads show very low expenses as compared to the others. Now, radio ads are nearly the same, constant. The expenses do not have a very sharp increase nor a decrease, constant expenses. For newspaper ads, what do we see? There's a sharp decrease, means some of the expenses are very low as compared to the other expenses. So what do we want? We want the data to be normally distributed, means all the expenses should be comparable across each medium. So in TV ads, in newspaper ads, and radio ads, all the expenses should be comparable to each other. If it is not, if some expenses are very low as compared to the others, those expenses are not considered in the analysis. A very low expense might bring down the overall average, which is happening in the case of newspapers. Okay, so if I keep a very low value, a negative outlier, ideally these are outliers. So all this data, all the expenses have outlier values, means extremely low values or extremely high values. Now, extremely low values will bring down the overall average, right? And extremely high values will bring up the overall average. So whenever we infer about any collection of data, we always go with the average values, right? So what does the average say? Instead of addressing each value separately, individually, we go with the overall average and infer about the expenses. Be it TV, be it radio, be it newspapers. So because newspapers has negative outliers, means very low negative values or very low values for the expenses, it might bring down the overall average and give us a perception that the expenses made on newspapers is ideally overall is very low. But that is not the true case, right? When we go for the plot, we see there is a high expense and then it gradually falls. It was not always low. It was high at one point and then it decreases. Overall average will be low. So to avoid this kind of inference, what do? We put all the values within the same range. So all the values are similar, all the expenses are comparable to each other. And how can we do that? We standardize the variable. When we standardize the variable, all the values are fixed within a constant range. So we do not have an extremely high value, nor do we have an extremely low value. All the values are comparable to each other. That is what we do with standardization. Now, do regression models depend a lot on standardization? No. Even if you do not standardize the data, they give us a decent accuracy. They're very strong models in that aspect. Yes, but if you want to fine-tune the model, optimize the performance further, then we need to standardize. So that is what standardization is, but we'll deal with it separately when we are going for regulations, like when we are trying to fine-tune the regression model. So till we have done it is decent. 91% accuracy is decent. Okay, now what did I do extra here? That let us go through that. Now mean squared error, we have brought in another metric which is which you all might have heard before, root mean squared error, and which I explained in the last session. One is mean squared error and one is root mean squared error. Now it is idly the error component. So lower it is, better it is. So root mean squared error, we do not have a separate metric here. We have mean squared error. And when we just use the square root function, so mean square error is what? Error is a minus b. Actual minus predicted value. If I square it, that is squared error. And if I find out the average error, that is 1 by a. So mean squared error is added with the average error, prediction error. A minus b is a prediction error, right? What is a? Y-test. The right values. What is p? The values given by the model, the predictions made by the model. That is A and B. So it is giving the average prediction error. Now, why did I keep it in dollars? Because the yearly spend is measured in dollars here. And with that, we are finding out the root mean squared error. It is very, very low, 10.20. Less than 5 is excellent. If it is ranging from 5 to 10, it is low. Good model. There is no standard threshold which we can give here. Now, let us go for the next part. We discussed about coefficients, right? And we, by understanding the data, by understanding the correlation only, we decided, okay, length of membership, and by understanding the bivariate plots which we created. What inference did we come up to? Length of membership is the most important variable. Why? Because it has the strongest relationship with the dependent variable. That is what we infer. Then we came to time on app, 50% correlation. Length of membership at 91% correlation strength. Time on app had 50% correlation strength, and average session length had 35% correlation strength. Right? So they were very strongly related to the dependent variable. And based on that, we ranked the features by their importance in predicting the dependent variable. Now, if I check so this feature selection is ideally very important. Okay, that helps you include only the relevant variables in your analysis, and you do not end up working with too many variables. So what did I do? I stored all this. What is columns? Columns will give me the variable names. That is why I wrote x dot columns. Coefficient, we know how to find out the coefficient rate. We have done that in simple linear regression. The coefficient, the predicted coefficient value. So what will be the final regression model equation? It is the actual equation is beta naught. We have got 3 variables here, so I'll keep it till 3. Beta 1 x1 plus beta 2 x2, right? Plus beta 3 x2. This is the actual equation. Now, once the model is built, what will be the equation? Predicted values, right? Beta naught predicted plus beta 1 x1 plus beta 2 predicted. These are the predicted coefficient values. x2 plus beta 3 x3. This is the final model equation. No. I have to find out the values of this, and this. Actual values are there. I have to find out the predicted values, even predicted y. Then I can frame my entire equation right. But how would I get the values of beta 1, beta 2, beta 3? These are the coefficient, predicted coefficient values. The values I'll get from the model itself because the model has predicted it. So what am I doing? MLR, that is the model name and coefficient. Take all the coefficient value and store it into a new variable called coefficient, right? Then what am I doing? Sorting the values. Why am I sorting the values? Because these coefficients will give me then an idea of the relative importance. If the coefficient value is higher, that means it has a larger impact on y. If the coefficient value is lesser, it has a lesser impact on y. What does the coefficient measure? That is the slope. Slope measures what? How much of impact we have on the dependent variable due to a per unit increase in the independent variable. That is what we know about the coefficients or the slope. So in this case, when we go with the predicted coefficient values, we go for sorting it. Sorting it in what order? Now, whenever we use the sort values function, usually the sorting happens in the ascending order by default. Lowest values first, highest values at the end. But what do I want here? I want the highest value because that will be the most important feature. That is why when we apply the sort values, I have to say based on which variable I want the sorting to happen. I want the sorting to happen by coefficient. What is ABS, key absent? The coefficient might have a negative sign. It might be positive, right? If two variables are moving in opposite directions, they are inversely related to each other, the coefficient will have a negative sign. If the two variables are moving in the same direction, they are positively related to each other, then the coefficient value will have a positive sign, right? We're interested in the sign, we're interested in the value, because the value gives us the relationship strength. So that is why I've given absolute. Take the absolute value. Do not ignore the sign. Ascending equal to false because I want the most important variable on the top. So the highest coefficient value should appear on the top. Then what am I doing? I'm just printing it. Printing what? Coefficient dx. And what am I exactly printing? MLR intercept and just the text which I want the output to have. I want the intercept value to. Intercept value is what? Beta naught. That is intercept value. Give me the intercept value to. So when we sort the values, which is the most important variable? Length of membership, which we have already inferred earlier. We are checking it with the model output, whether our analysis was correct. And that gives us the same output. Length of membership, most important. Time on app, second. Average session length, third. In order of importance. Of time on website. Now you can, when you are practicing this, include time on website and see what happens. Intercept is minus 1034.18. Intercept does not have any significance in regression model. Intercept is the value of y when there is no x. But when we are studying a cause and effect relationship, we do not want to know the y when there is no x, right? We want to know the y value with the help of x value. So intercept does not have any significance in regression models, but we are taking up the intercept value. Now we can create the regression model from here itself. Just substitute the values of the coefficients. Okay, that will give you the, like we have done in simple linear regression. Find out the intercept value, find out the coefficient value, plug in those values. X1, X2, X3 will be different. It will be the input. Y predicted will be the output which I'll get by solving the entire. Now in this case, what did I do? I did not write the equation manually. I have used a function to do it. So what it is doing, coefficient df is going to coefficient df. Iter rows will give you the output in each row. For I, so I've created for loop. What is the first two variables and which will be iterating? One is the index, what is I? I will give the index. What is row? The row values. So it will give me the index and the row values. Df iter rows. Now what do we want to be printed out when each row is accessed? I want the coefficient value, which is rounded off to one place of decimal, and then the feature name, okay, which I want to add up to the intercept. So this is a way of writing a regression equation with the help of codes without writing it manually. So intercept is given first, and then I've given a plus sign. So plus is given here. Coefficient value is given 61.7. That is the coefficient value of length of membership, then the feature name. And similarly for the other. So I can frame the entire regression equation. Now we are building the model to predict for a new customer, right? So I'm giving the value to a new customer. Now, why did I give average session length first, time on app, and length of membership at the end? I could have gone with this order, right? Length of membership, time on app, average session length. See how you have inputted the variables in the model. I have given average session length first, then time on app, then length of membership. So I'll have to maintain that order. Now, when I'm predicting for a new customer, what did I give? This is the average session length value. This is the time on app value. This is length of membership value. Now, all these three values do not have any special significance. It can change, right? So that is what we are seeing. We are giving three different values for each of the variables. Correct. Then predicted. Now you know how to do that. Use the predict function. Or you can directly substitute it in the equation. So in case of length of membership, I'll get 50.2. So 61.7 into 50.2, 38.6 into 16.3 plus 25.7 into 5.7. If I substitute all the values, and we have the intercept, obviously. If I solve this, then I'll get the value of predicted value. Now here we are not substituting it to equation. We are doing it with the help of the function. That gives me the spend, a yearly spend for a new customer, for any new customer. That is the purpose for which we are building the model. So that the model can predict the average spend for a new customer, yearly spend for a new customer. That is what we are getting from new data. Now I want to plot the actual versus the predicted. That is what we are doing. What is the actual y-test? What is the predicted trend? What is alpha? Alpha is nothing but the transparency to make the plot look a bit better. If I do not give alpha, I'll get dark points. Like the circles which you see will not have this transparency. It will be bold plots. Alpha is just to make the plot look a bit. It shows how the transparency, like how dark or how light you want the points to. Then we are going for plot. What is y-test max, y-test min? I am fixing the range. So when I'm creating x-axis and y-axis, I can give the intervals. From where should it start? From where it should end. Now you can skip that. It will take the default range for x-axis and y-axis. I have given the range. Plot will give me a line plot. What do I want? What color do I want? Green. Line with this too. These are optional. Okay. Then X label is yearly amount spent, Y label is predicted amount spent. I want the equation in the plot. So what did I say? Actual amount is predicted versus predicted, which is a text, and the R square value. Fetch the R square value from the model itself. The model gives the R square value with by the object R2. I am rounding it off to 2 places of decimal. You see the value plot. So formatting your output is totally dependent on you, how you want to customize your plots. You can do without the customization too. It will still give you a plot. So if I do not fix this range, still it will give me a line plot. I can just go for green and line width. That is all. That will also give me the plot. So we talked about, okay, let us start off with the basic terms like multicollinearity. What are the problems of regression models? Why do they underperform? The regularization means applying a restriction. Or imposing some controls on the normal model. So we talked about fine-tuning, right? Fine-tuning means optimizing the model's performance, which we have seen in the deck too. So once we get the accuracy, we try to fine-tune the model. Fine-tune is ideally optimizing on the models, trying to optimize the model's performance. That is fine-tuning. Now for regression models are basically very strong models. So you can get a good accuracy. The models will perform well even with extreme values. Means if we have anomalies in our data, still the model performs well enough. The two problems which can come up and which can like impact the performance of a regressor. One is multicollinearity. And the second one is overfitting. Very important concepts, both of them. And we need to understand what is multicollinearity and what is the overfitting. The idea which we already have here. But let us understand it with a very simple example. That comes from the second assumption or classical linear assumptions, basic assumptions of classical linear regression models. It says that the independent variables should be independent. That is why they are called independent variables, because they are supposed to be independent. Means none of the variables should have an interrelationship. They should not have a mutual relationship. They should be independent to each other, and all of them should impact the dependent variable. If they have a relationship, it should be with the dependent variable, not among themselves. So when we say y equal to 2x1 plus 5x2 plus 6x3, then x1, x2, x3, mutually they should not have a relationship. But all of them, x1 and x2 and x3 should have a relationship with y. If that is not there, we will not consider it as a predictor or independent variable. So that is the linear relationship assumption which we have, that y and x should have a relationship, a linear relationship. But x's among themselves should have no relationship. That is the independence. Now what happens? Why do we have such an assumption? First of all, when we talk about the first assumption, that y and x should have a linear relationship or a relationship, that is justified, right? Because we are predicting y with the help of x. Now, if x and y does not have a relationship, then we'll never be able to find out the value of y given the x's, right? So that is justified. It should have a relationship. The second assumption, now, independent variables should not have a relationship. Now, what is the reason that we have such an assumption? See, y is the price of a house, okay, which is determined by several factors, say x1, which say is a locality, okay. Then say x2, which is say the square feet area, plus x3, which is say the number of bedrooms in the house, and x4, which is say the age of the house. All this will impact the price, right? Locality is a determinant of the price. So the price of the house is definitely dependent on the locality. It is dependent on the square feet area of the house. It is dependent on the number of bedrooms the house has. Okay. It is also dependent on the age of the house, how old the house is. If it's a new house, then naturally the price will be higher. If it's an old house, the price will be lower. So all these are determinants, right? So the first assumption holds true, that all of these four variables, x1, x2, x3, x4, they all have a relationship with y, a linear relationship. Now, the second assumption says x1, x2, x3, x4 should be independent. Now think about x2 and how do we understand the feature importance, which we did yesterday. We determine it by the strength of the coefficients, right? So if I say this is beta 1, if I'm just writing the coefficients for each of the variables, this should be beta 3 and this should be beta 4. So beta 1, beta 2, beta 3, beta 4 are nothing but the coefficients of each of the independent variables. Now the coefficients play a major role, as we have seen with yesterday's use case, right? If the coefficient value is greater, then that variable is more important because it has a coefficient value measures the impact of the independent variable on the dependent variable. So the larger the coefficient value, greater is the impact of that particular independent variable on the dependent variable. So if beta 2 is greater than all the betas, then x2 has a larger impact on y. That is why beta 2 is greater. So x2 is more important than the other variable. So the coefficients play a major role in determining the feature importance. Now say we have got two variables, square feet area and second is the number of bedrooms, locality and age is there. Now when we look at these two variables, x2 and x3, when one increases, so how do we find out the feature importance using the coefficients? So coefficients play a dominant role in choosing in the feature selection. Now suppose say when the square feet area increases, what happens to the price of the house or the dependent variable? It will increase too. This is x2 and this is y. Direct relationship, linear. So when square feet area increases, price of the house increases too. That is for x2. Now again, when number of bedrooms increase, the price also increases. Again, a direct relationship between x3 and y. So we can find out now when we try to find out the value of beta 3, say I want to understand which features are more important. If I try to find out the value of beta 3, what will I do? Del y by del x3. Right? If I want to find out the value of beta 2, it is del y by del x2. That will determine the values of beta 2 and beta 3. But when I try to find out the value of beta 3, it says how much did the price change when the number of bedrooms increase. It will have an impact on the price. But this impact, this beta 3, is not due to only the number of bedrooms increase. Because when the number of bedrooms increase, the square feet area increases too, parallelly, right? So the price increase, which is captured by beta 3, is not only due to the number of bedrooms increase, it is also due to the square feet area increase, the overall square feet area increase. So both these X2 and X3 are impacting Y at the same time. So beta 3 is not giving us the individual impact. It is giving us a cumulative impact. Same goes for beta 2. If I try to understand how much will the price change when the square feet area changes, beta 2 will give us a total impact on price. But if the square feet area changes, the number of rooms also change. Like think of it as a number of rooms, not bedrooms. So if the square feet area increases, then ideally the number of rooms also increase. Both are directly related to each other. Right? Number of rooms increase, square feet area increase. Square feet area increase implies the number of rooms have increased. So number of rooms will have an impact on price. Area increase will have an impact on price. So beta 2 is a cumulative impact, not an individual impact. But when we choose the variables for understanding the importance of each variable, then we are judging it by the individual impact, not the cumulative impact, right? That is what we did yesterday. Length of membership has the highest impact, 81%. We were talking, this 81% increase or 81 units of the yearly spend, which increases, is only due to the length of membership factor, not due to other factors. But when two variables are correlated, then we have a cumulative impact, not an individual impact. And if I do not have an individual impact, then I cannot choose the individual variables here. I cannot choose between X1, X2, X3, or X4. Ideally, choosing between X2 and X3 will be difficult then. Because whenever I go for beta 2 and beta 3, for choosing the variables, it is measuring the cumulative impact. So beta 2 might give me an increase, but I do not know how much of the increase is due to area or how much of that increase is due to the number of rooms increase. Okay, so that makes it difficult to select the right features to predict the value of the price, predict the value of Y. That is why we have that assumption. So what is the solution here? We'll drop one of the variables. Either we have to drop area or we have to drop the number of rooms. Both cannot exist together when you're building the model. So multi-correlated will have an impact on the overall analysis, overall finding of the price, because you are ideally not choosing the right variable. So it will impact the prediction. That is the problem of multi-correlated. Okay, so that was multi-correlated. Now there is another very common problem in machine learning, which is called overfitting. Now, what is overfitting? Let us first understand it from the file which I've shared. So that is much more easily explained. Let's go back to that file, overfitting. Go with this example. Now, there is a very simple example which is given here. That is, there is a child at home. You show him the picture of a car. The car is red in color. First day you show the picture of a red car and tell him, okay, this is a car. Kid learns, okay, this is a car. Second day you again show the same picture and tell the kid, okay, see, this is a car. So beta 2 will get some values of beta 3 and no, beta 2 is capturing the impact. So when I say beta 2 is the value which we get or the increase in price which we get is due to the cumulative impact of area increase as well as number of rooms increase. Both are increasing together, right? If X2 is, say, area and X3 is the number of rooms, when the area increases, automatically the number of rooms are increasing. That is why the area is increasing. If the number of rooms increase, then automatically the square feet area also increases. But square feet area and number of rooms, think of it individually, they all impact the price. If I increase the square feet area, the price will increase. If I increase the number of rooms, the price will increase. But the problem here is area and price will increase together always. X2 and X3, these two variables have a direct relationship. When one increases, the other automatically increases. And both these two variables also have an impact on the price, right? That we already know. But the problem here is the two factors, independent variables here, are increasing together. They will always increase together, directly proportional. They have a very strong correlation. And when both of them increase together, both of them will increase the price as well. So when you're talking about beta 2, it is not only the increase which we have in price, it's not only due to the number of rooms increase. It is also a parallel increase in the square feet area. So that is why we say that it is not an individual impact. It's a cumulative impact. So when I say there is a high value of beta 3, it makes it difficult to choose X2 as the important variable because beta 2 is capturing the impact of X2 and X3 too. So then I cannot go with single choice. then what is the solution? We'll drop either x2 or x3. One can capture both the impacts, right? If I keep only x2, then it is capturing the impact of square feet area as well as number of homes. So why will I keep two different variables? So I'll keep one variable there. So now let us come to overfitting. Now overfitting, what happens? One day you show the child a picture. Say a 2-year-old child, you show him a picture of a red car, the day fun, and tell that, okay, this is a car. Second day again you show the same picture, red color car. This is the car. Third day again you do the same thing. Fourth day again. 1 month you just keep him showing him the picture of the car, the same picture every day, and tell him this is the car. By the end of 1 month, he has learned what is the car. Now, after 1 month, you take a different picture, say a blue colored or a black car, and ask him, okay, what is this? He'll not be able to respond accurately. He'll not be able to identify it as a car. Now, why will that be? Why will he not be able to recognize a black car when he shows the picture? Because it has already learned that a car is red, because you have taught him that. You keep on showing the same picture to him. The moment you change the picture and you ask the child, okay, what is this? The child gets confused, does not have an answer. Because what the child, if you are showing him a black car, the child will never be able to respond accurately, okay, or identify the object. Now, why this is happening is when you're showing the same red color car picture, the child is not focusing on the features of a car. It is not seeing how the car ideally looks like. It has got 4 wheels, it has got a steering wheel, it has got 4 doors. It is not focusing on that. What is it focusing on? The color, red. So the moment showed him a car of a different color, say black, it does not focus on the features of the car, of the object idea. It is focusing on the color. So it says it's not red, so it cannot be a car, right? So what is it? What is the child learning? The child is learning incorrect information from the training you're giving. It should learn the basic features of a car, how a car would look like, basic features of the object. But the child is not learning the basic features of the object. Apart from learning the actual information, it's learning the wrong information. That is a color. Okay. So that is ideally overfitting, when the model does not learn the actual information. What it learns is information which is it should not be learning. It learns the incorrect information. And when does this happen? When we repetitively give it the same information. It should actually capture the patterns, right, from the data, how the things are working. Because we are giving the input, we are giving the output. So it should learn that, how the output is related to the input. That is the actual information what it should learn. When the input is increasing, how does the output behave? Or when the input is decreasing, how does the pattern or the information, the actual information, which it should be capturing. But when I keep on giving the same information repeatedly, at times the model fails to capture the actual information and picks up the noise element. Noise is what? The error component. Like in this case, the child picked up the clue, the child picked up the color as the information, whereas it should not have picked up color as the information. It should have picked up the features as the information. It has learned wrong because I'm repeatedly showing him a picture of a red car and telling this is the car. So it correlates red with car, not the object. It does not focus on the actual information. So when we repeatedly fit the training data to the model, sometimes the model learns the training data way too well. And because it learns the training data way too well, it fails to perform on any other data. It learns it so well that it does not only learn the actual information, it also learns the noise element or the error component in the data. Now, every data which we talk about has got an error component, every data. So when data is constantly getting updated, the error component also gets updated. Error component means the errors which we cannot measure, market imperfections, price fluctuations. That is not in our control data. That will have a direct impact on the data. So these are few factors which are not in our control. The residual sum of squares, which we talked about. So those are not in our control. We cannot detect it. We cannot measure it. That has an impact on the data, overall data. So data keeps on changing. The error component keeps on changing. So learning the error or the noise is incorrect information because it will keep on changing. You cannot learn it. But the actual pattern or the actual information will not change. That will remain the same. But sometimes the model learns the training data so well that it does not only learn the actual information, it also learns the error component. Okay? And that is why it cannot perform on a different set of data with a different error component. It tries to look for the same error component, which is not present. Like when we talked about the child, what was the child looking for? If you show him the picture of a black car, he's looking for the color red. He does not find the red color. He fails to identify it as a car. So he's looking for something, some information, which is not correct. Now, if you show him the picture of a red bus, he'll tell this is a car because he's capturing the wrong information. Now, how do we control this? How do we tackle this? That is, if I would not have shown him the same picture of a red car all the 30 days and told him this is a car, this is a car. Had I showed him a red colored car first, and then a blue color car, then a black color car, and kept on changing that, then he would have known that that is not the clue he should be catching. Red, not the color, the features. Then he would have focused on the actual information. But because I'm every day showing him the same picture, this is a car, this is a car, it seems that, okay, this is only a car. Nothing else can be a car. So repeatedly giving the same information. It is learning the same information. So whenever I give him a different information, it is failing to learn. Similarly, the overfitting, when it happens to the models, we are giving the same data to the model. The model is learning the training data too well. It might be we are executing it once, twice, thrice. The model internally might be learning the training data way too well. Now, to break that, we need to keep on changing the training data. Like showing the child a red car on the first 10 days, then a blue car, then a yellow car, then a black car, then a green car. Okay, change the information so that they can focus on the actual information and not on the noise element, which is the color of the car. For that, we have to change the data, because when it will perform in production or say the testing phase, it will be performing on a new data altogether, which is very different from the training data. When it is deployed in production, again, it will be predicting on real-time data, which is very different from the training data or the testing data. So data will change. So the model has to adapt to that change. So the solution to this would be changing the training data. Because the training data will keep on changing, the model will never be able to learn it well. If I keep on changing the training data, it will never be able to overlearn the training data because it is constantly changing. If it is fixed, then it will overlearn it. If I keep on changing it, it will never be able to learn the training data. That is point one. Second point is, the model ultimately has to perform on unseen data, new data. So it will be able to generalize well. Generalization means what? Generalization is, say, I'm taking all the training sessions from. So you're kind of used to my delivery style or my pace. Now tomorrow some other trainer comes and takes a session. You should be able to focus on not the delivery style, but on the content. If you're too used to the trainer's delivery style, then you're not only used to the information the trainer is passing, also the delivery style. But ideally, what you should be doing, you should be focusing on the information and not the delivery style. So if tomorrow there is another trainer is taking your session, you should be able to learn from the session as well. That is generalizing. You are not fixed to a certain data. You're not fixed to a certain information. You need to adapt to the change. So if I'm fitting the model with a certain data set or with a certain information, it should be able to perform on changing data as well. Data will keep on changing. So it should be able to adapt to that change. It is not that when it is given the live data, it fails to perform because it's used to only training data, okay, or the historical data. That is called generalization, where the model can perform equally well on unseen data or new data. Okay. In one line, if you say what is overfitting, overfitting is overlearning, learning too much. Model does not have to learn too much. Learn only the information which you should be learning. Do not learn everything. Overlearning. Now, what is the opposite of overfitting? Opposite of overfitting is underfitting. Underfitting means what? What is overfitting? Overfitting is the model is learning too much from the training data. Then what is overfitting? It is learning too much from it. It is learning information which it should not be learning at all. Overlearning. Underfitted models are when the model is not learning at all. Okay. So if the model is not learning, then it will not be able to perform. So underfitting is bad, overfitting is also bad. In overfitting, it's learning way too much. And when we test the model on training test data, it fails to perform because test data is separate, right? When the model is the training phase, what do we fit? X train, Y train. X test is new data. That is the proportion of data which we keep separate. We do not expose the model to it. So for the model, it is new data. That is how we test the model, right? But so the model, when it's overfitting, then it's learning the training data too well. But when it is performing the test data, it is new data and it fails to perform. So test set accuracy will fall down. Training set accuracy will be very high because you're giving it information which it has overlearned. So if I try to test my model's performance on the training set, it will always be high because it already has overlearned that information. It will always perform well on training data. But the moment I try to test my model on testing data, it will fail to perform because it can perform only on the training data. Testing data will have a different noise element. Maybe the trend, the information is the same, but the error component is changing. And the model will not be able to align to that new error. So it will underperform. On any other data, it will underperform. It will only perform on training data. But how do we evaluate a model's performance? On the testing set, right? Not on the training set. Training set is the information which you give the model. We are ourselves giving the answers, right? We are giving the input, we are giving the output. If I try to evaluate the model on the training data and tell, look, I'm giving you X train, give me the predictions on Y train, obviously it will give it right? Because it is learning from X train and Y train. If I use the model and tell it to predict on X train, then it will obviously give the right predictions for Y train because it has learned from Y. Training set accuracy will always be high. Where do we test the model? We test the model in test set because that is new data. In overfitting, what will happen is, but if the model has learned well, it will perform equally well on training and testing. Like the usual models which we have. Till now, what we have done, we have captured the model's accuracy on the test data. We did not evaluate it on the training data. Okay. But what is the understanding? If my test set accuracy is as high as 90%, as in our last model, multiple linear regression model, which we did, it was 98%. That is on new data. Then it will definitely perform well on known data. Test set is new data, right? And it's giving me an accuracy of 98%. Then it will definitely give me a greater accuracy on the training data. Because training data is the data which the model has learned from. It is already aware of Y train. Now, if I tell the model predict Y train, it will definitely give me right predictions. So training set accuracy will always be high. Now, how do we know the model is overfitting? When the training set accuracy is very high, say 98%. But the testing set accuracy is 60%. Then there is a large drop. Means on my training set, my model is performing very well. It is giving right predictions for Y train. But when I'm fitting X test to the model and asking it to predict, it is giving me incorrect predictions for Y test because test set is new data. The model has learned the training set very well. Means it has marked up all the values of Y train. Now you ask, tell me the values of Y train, giving it X train. It will give you all correct answers. So 98%. But whenever I'm using some other data, the model is failing to perform. This huge difference in the training set accuracy and the testing set accuracy is a clear indication of overfitting. Now let me know, did you understand this? How will you detect whether the model is overfitting? So your model gives you a very low accuracy. That low accuracy might be due to multiple reasons. You did not prepare your data well. That can be one of the reasons. So if you're giving wrong data to the model's performance will be bad. So if I get a low test set accuracy, it can be due to multiple reasons. I am not including the right variables. The right features I'm not including. Right. I did not encode the data. I did not scale the data. There can be multiple reasons for your model's low performance. But how will you know whether it's due to overfitting? That is the goal. So when you're going for a low accuracy, check the training set accuracy. If it is very high compared to the training set accuracy is very high compared to the test set accuracy, then ideally the model is overfitting. How do we say that? The model is learning too much of the training data. That is why it's performing excellent on the training data. But is that learning a good learning? No. It is overlearning it. Whenever I give some other data, the model fails. So this discrepancy is because the model has not learned well. That is why we have a huge difference between the training set accuracy and the testing set. This is a likely reason of that is how we detect overfitting. Now the other one, underfitting. Overfitting is overlearning. Underfitting is what? Not learning at all. In this case, the model will have a low accuracy, test set accuracy. Okay. The training set accuracy will also be low. Means it does not learn from the training data at all. Overfitting learns too much. Underfitting does not learn at all. So in underfitting, the training set accuracy will also be low. The test set accuracy will also be low. Both will be low. In overfitting, this will be high, the other will be low. So the problem is the model is learning too much from the training data. And why it is learning too much? Because it is learning the training data too well. So what we have to do is change. periodically let us keep on changing it. Then it will not be able to learn the training data well. So the solution to overfitting is cross-validation. It is called k-fold cross-validation. Now, what is the meaning of k-fold cross-validation? We are reserving this, say when we go for a split of say 80 and 20%, what do we do? 80% of the data we reserve as training data, training set, right? Say this is my training set. This represents 80% of my entire data. I break this 80%, this training data into, now K determines what, how many folds I break it up or how many partitions I make. Say I'm going for 5 partitions. I'm going for 5 fold. K is equal to 5. Means I'll split up my training data into 5 parts. I split it up into 5 parts. Where K is, so I'm going for 5 fold cross validation. 1, 2, 3, 4, and 5. And what is this? My training data. Okay. Now what do? I execute the model 5 times. In the first execution, second execution, third, fifth. For each execution, I'll have a training set like the usual. I'll have a testing set. I'll have an accuracy. See, for the first execution, this for the second, third, fourth. In the first execution, this is the entire data which I have 5 parts divided into 5 parts. I'm taking up 1, 2, 3, 4 as my training set. The 5th part I'm reserving for testing my model. And in this execution, the accuracy which I get is A1. Now I go for the second execution. In the second execution, I go for 1, 2, 3, and 5. These are the parts I use as my training data. The 4th part I reserve for testing the model. It gives me an accuracy 8. Third execution, I go for 1, 2, 4 part, 5. These parts I take for training the model. And I reserve part 3 for testing them. It gives me an accuracy 8. Then in the 4th execution, what I do is 1, 3, 4, 5. I use it for training the model. Part 2, I use for testing the model. It gives me an accuracy 8. And in the final case, what do? I go for 2, 3, 4, 5 as my training data. 1 I reserve for testing my model. It gives me an accuracy 8. Now, what is the overall accuracy of the model? The overall accuracy will be the average of A1 plus A2 plus A3 plus A4 plus A5. I'll add all the accuracies. But the final accuracy will be what? It is A1 plus A2 plus A3 plus A4 plus A5 by 5. That will be the final accuracy. Now, when we do this method, then what usually happens is the training set is constantly changing. Now, if the training set keeps on changing, the model will never be able to learn the training data too well. Alongside, I'm also changing the testing data at every point. So now the model can adapt to change. Okay? And it will never be able to overrun the training data because I'm constantly changing the training data. It gives me 5 different accuracies. I'll take the final accuracy as the average accuracy. This is called k-fold. Now k can be of any value. Usually we take the value of k as 5 or 10. Okay, see this, and then I will copy this part as well. And tell me if you have it. Give me a while. Read it. All probabilities, I'll have an internet issue right now. Okay, people, read this out. Now we'll go for, now these are the 2 problems which can impact the performance of a linear regression model. One is overfitting and the second one is multicollineating. Now we'll talk what does ridge and lasso regression models do. So you have basically seen the definition, right? Now what happens in this case? Say, I've got 2 equations, 2 linear regression models. This is y. One is, say the constant. I'll leave the constant for now. Say x1 is 20x1 plus 15x2 plus say 18x3. And I have got another equation, another linear regression model, which is say 10x1 plus 5x2 plus 8x2. Okay. two equations, and I give you the values of x1, that is 1, x2 is 2, and x3 is 3. Now, which equation will be easier to solve, equation 1 or equation 2? These two models, which model will be easier to solve? Model 2. And why do you say that? Because you can solve it out verbally. You do not need to compute it separately. So 10 into 1 is 10, and 5 into 2 is 10, 10 plus 10, 20, and then 8 into 3 is 24. So 20 plus 24 is 44. I could just do it without using any other ways of computation. I do not have to use a calculator here. In equation 1, I'll have to use a calculator, or I have to use some other method. I will not be able to easily solve it like I did equation 2. And why is that? Because the coefficient values are low. Instead of 18, if I have got 86, then I'll again have to think, pause a while before coming up with the final value of y. So what makes model 2 more easier to solve or more easier to convert to a solution is because the coefficient values are low. So what is most important in regression models, as we have seen before, are the coefficient values alone. If the coefficient values are low, then we end up with simpler models. That is one point. Next is, say, in this case, x2 and x3 are related, are directly related. Then where will the impact of multicollinearity be more, in 1 or 2? So multicollinearity is present because x2 and x3 are related. But where will the impact of multicollinearity be more, in model 1 or model 2? Yes, in model 1. Why do we say model 1? Because the presence of x2 and x3 is more dominant. So I'm saying 15 times x2 and 18 times x3. So the impact of multicollinearity will also be higher in model 1 because the presence of x2 and x3 is more in model 1 as compared to model 2. So if there is multicollinearity, the impact will be more in model 1 than in model 2, right? Now let's talk about overfitting. Overfitting means learning too much. Now in model 1, I have given x1 is present 20 times, x2 is present 15 times, x3 is present 18 times. That is one lot of information. That is on what the model is getting trained. In equation 2, I have 10 times x1, 5 times x2, 8 times x3. So the information as in model 2 is much lesser than the information in model 1. So model 2 has less chances of overfitting than model 1 because model 1 is learning from more information. And overfitting is what? Overlearning, learning too much. So I'm giving a lot of information. So the model has more chances of overlearning this information. But in model 2, what am I doing? I'm giving it less information. So model has less chances of overlearning it. So even if there is an overfitting problem, it will be lower in case of model 2 than in case of model 1. So we solved 3 major problems here. One is the time consumption. Second is the overfitting problem. Third is the multicollinearity problem. Just by following a simple rule, that is decreasing the value of the coefficients. Just by decreasing the value of the coefficients, we could solve the 3 major problems for which the regression models might not work. Okay. So my solution lies in decreasing the coefficient value. That is exactly what we do in rich and last. What do? We scale down the coefficient value. Now, if I scale down the value of 20, scale down the value of 15, scale down the value of 18, then ideally I'll be able to resolve few of the most dominant problems regression models face. So it is all about, now how do I scale down the coefficient? There should be a method to do it, right? We apply regularization. We use a regularization parameter, which is alpha. And alpha can have any value from 0 to infinity, anywhere. Now, if I assign alpha to a 0, that means that is my multiple linear regression model, which we did yesterday. We did not use rich and loss. We used a simple multiple linear regression model. The value of alpha was 0. Means we did not regulate the model. We are not attempting to scale down the coefficient value. The model is performing well. We do not need to do that. But see, if the model is underperforming, I get a very low test set accuracy, it's overfitting, or there might be too many variables. If I have got too many variables for which we do feature selection, right? We are singling out the variables which we need. If we do not do that, and we work with all the variables, there are higher chances that the variables which we are working with are related to each other because the determinants are nearly the same, right? There are larger scopes of multicollinearity if I'm involving too many variables. All these variables are having an impact on y, right? So if I have too many variables, there are higher chances that few of them will be correlated to each other, and we'll have the problem of multicollinearity. So how do you detect that there might be multicollinearity present when I'm working with too many variables? I do not understand the meaning, I'm just including all the variables. There are higher chances of multiple. How do you understand if there is overfitting? We'll go for the test set accuracy and the training set accuracy. Compare. You'll get to understand there is overfitting. Now, how do I control it? I know I have to scale down the coefficient. But how would I scale it? There has to be a method to do it. So the regularization parameter is alpha, which does the scaling down of the coefficient values. Now this alpha can range between 0 to infinite. The lower the value, the less is the regularization. Means I'm not imposing any restriction. So multiple linear regression model, what we have done till now, the alpha value was 0. We did not specify it, but ideally that was the value of alpha. The moment I want to apply restrictions or I want to scale down the coefficients, I'll increase the value of alpha beyond 0. So say alpha is equal to 0.01. That means this is the amount of restriction I want to apply on the model. So what will the model do? It will internally scale down the coefficient values so that the problems of multicollinearity and overfitting are resolved. Now I can increase the value of alpha. This infinity. So I can go with a larger value, say 100. So the restriction is much more stronger. Now we do not have a optimal value of alpha. So use alpha equal to 20. We will not be able to say that because it depends on the data, how complex the data is. Okay. So we do not keep the value of alpha too high. If we keep it too high, then the coefficients will be scaled down too much. Right? There is a trade-off between a higher value of alpha and a lower value. If I give a very low value of alpha, then I'm not applying restrictions at all. So I am not scaling down the coefficients well enough that the problems of overfitting and multicollinearity are tackled. Because I'm applying a very low restriction. The scaling down is not much. So the problems of overfitting and multicollinearity remain. I cannot go for a very high value of alpha. If I go for a very high value of alpha, then what happens? The coefficients will be scaled down a lot. Say you're working with a model like this. 2x1 plus x2 plus 1x2 plus 3x3. Now this is an oversimplified model. When I say I'm building a very simple model and I'm oversimplifying the model, then what are the problems? The problem is underfitting. What is underfitting? When the model does not learn from the training data. It does not learn only. So it fails to learn from the training data. So it performs poorly with the test data. Naturally, if it is not learned well, how would it perform? So performance is low in both the cases, on the training set or the testing set. Why? Because I'm giving it very less information. I'm giving it a oversimplifying the model. Means the coefficients are scaling down so much that what I end up is an oversimplified model, where the amount of information I'm giving is very less. So the model does not learn at all and performs poorly in the test set, in the training set as well. So we are ending up with an underfitted model. So the value of, so there is a trade-off. I cannot give a very low value of alpha. I cannot give a very high value of alpha. I have to choose the value of alpha properly. Now you might say, what then? How do we choose that? So there is a method by which we can say there is no optimal value of alpha. It depends on the data. Now we do not have a control on the data. The data can be anything, right? You might have to work with the client data. Right? That can be, it can be very simple data, very good data, or it can be very bad data. So you do not have an optimal value of alpha. Neither it is said that this is the optimal value of alpha. How do we then come to the optimal value of alpha? We'll go for many guesses. Say I start off with a low value, 0.01. I give it as one of the guesses. Then I slowly increase it, say 1. Then I further increase it, 10. Then I further increase it, 100. Now I run the model on all these values of alpha. Let us start off with 001. Then let us go with 0.01. Slowly increasing the values. And let the model run on 0.001 as the value of alpha. One execution done. Second on 0.01. Then on 1. Then on 10. Then on 100. Multiple executions for different values of alpha. And what do? We go for the checking of the final accuracy. Whichever value of alpha gives us the best accuracy, we go with that value of alpha. It is a trial and error method. So we give all the possible values of alpha and execute the model for each value of alpha which you have provided, because we cannot determine the actual value of alpha. So it will not only give you the best alpha with the best accuracy, so you'll get to know what is the like the extent of restriction you might have to apply on the model. Done by a method which is called the grid search method, which we'll do. Now, The next thing is we have talked about ridge, we have talked about lasso. What is the difference between ridge and lasso? In ridge, we only tackle the multi-coordinated part. Means I've got too many variables. Now, with too many variables, and like I said, if you're involving too many variables, all having an impact on y, there are higher chances that these variables have a mutual relationship. So that is multi-coordinated. So we can, if I have too many variables and my model is overfitting, then in ridge regression, what happens? The scaling of the coefficients are done. So the problems of multi-coordinated and overfitting are tackled. But in lasso, it goes one step further. It not only reduces the value of the coefficient, so scales down the value of the coefficient, it scales it down in such a way that it ultimately becomes zero. Now say, if this is my model, which we used a while back, 50x2 and 80x2. I'm scaling in ridge, what happens? The coefficients are scaled down. Say now it becomes, say, 5, this is 2, and this is, say, 4. So after scaling down, this is my model. This is what ridge does. So if I scale it down this way, then ideally I'm ending up with a simpler model. Overfitting is reduced. X2 and X3, they are related. The multi-coordinate impact is also reduced. So we are good with it. Now what does lasso do? Lasso, on the other hand, will reduce it further. Now say, go with this equation. Which is the most important variable here? Yes, people. If this is the ridge model, say this is the model now. Now, which is the most important variable here among x1, x2, x3? The important variable x1, x2, x3. x1 is 4. I did not get it. Yes, x1 is the most important one. Which is the least important variable here? Which is the least important variable in this equation? x2. Now, we have the coefficients. Now, which coefficient will converge faster to 0? The lowest value which we can have is a 0. Now, if I scale down the coefficients further, which coefficient will converge to a 0 fastest among x1, x2, and x3? x2. 2 will scale down to 0 faster, right, compared to 5 and 4. So x2, this will converge to a 0 faster. Now, if that happens, then if it converges to 0, what happens to x2? It is dropped from the model. We are dealing 0 into x2 is 0. So we are working with x1 and x2. So what did we just do in lasso? We dropped a variable. But dropping information is not good. But which variable did we drop? The least important variable. And that is what we do. That is exactly what we do in feature selection. We choose the most important features. We work with the most important features. We drop the least important ones. That is what we do in feature selection, right? Like in our case, what did we do? Time on website, I dropped it from the model itself because it had no impact on my, right? The correlation strength was nearly 0. There is no point keeping time on website. Drop it. And your model will not have a change in accuracy if you include it later because there is no relationship. It does not help us verify. So what we did is we dropped the most important, but we did it after understanding, exploring the data well. In ridge and lasso, you do not have to understand or explore. It will do it automatically. Now let me have responses here. So that is the difference between ridge and lasso. Ridge regression will scale down the coefficient but never make it 0. Lasso will scale down the coefficients so much that ultimately it will become a 0. So ridge does not help us with feature selection or feature elimination. Lasso helps us with feature elimination. So if I'm working with too many variables, the least important variables will be automatically dropped. We do not have to understand the variables and do it ourselves on our own. So feature elimination will be done automatically by the lasso model. In ridge, feature elimination will not happen. The impact of overfitting and autocorrelation will be, overfitting and multi-correlating will be reduced. And the model's performance will be enhanced. Okay. Lasso goes one step further. It not only reduces the impact of multi-correlated and overfitting, it also helps us with feature elimination. It will drop the least important features first. You can see the problem statement with the list of variables we'll be having in our data set. Problem statement is very similar to with the example I talked about. We will be predicting the home price. It's clearly said the objective of this project is to apply regression techniques to identify which features affect home prices the most in the city of Melbourne. So what is the dependent variable? We are predicting the home prices. And you can see the list of variables which are used as the determinants. To go through that, now this is when you have the variable name and then the meaning of the variable alongside, that is called the data dictionary. So when we talked about the steps of machine learning, we said the first thing is to understand the problem statement. The second thing was to extract the features or to understand the data set. When I say understand the data set, ideally the data which you get, you will not be aware of all the terms that I used. So you'll receive something called a data dictionary, which explains the meaning of every term used in the data dictionary. Okay. Means every variable. So what we have after the problem statement is the data dictionary, which gives you the meaning of the variables or the variables which we have in the data set. So it is essential that we understand the meaning so that we can decide on which variables to work with and which variables to skip from the analysis. So suburb will impact the home price. Address, does it impact the home price? No. So address is not required. Rooms required. Price will be required. What is method? Method is a property sold. Property sold prior. Sold after auction price is not disclosed. Price or highest bid not available. Vendor bid withdrawn prior to auction. So all these are different methods which are applied. Ideally categorical billing. But it will have an impact on the price, final price. If a property is already sold, ideally it will have a resale price if it has. If it's sold after auction price not disclosed, property sold prior not disclosed. So this is a categorical variable which might have an impact on price. So we will not be able to drop this variable. Type, we have bedrooms, house, cottage, villa, semi, terrace, duplex, townhouse. So it depends on the type of the house. So that will also impact the price. Seller, real estate agent. Now, whenever we are purchasing from an agent, we'll have to pay a certain commission to the agent too. So when we pay a certain commission to the agent, it adds up to our cost. So this will also be having a direct impact on the price. And how much commission we pay will be dependent on the price of the house. So it has direct impact on the price. So we cannot drop this as well. Next is date. The date when the property is sold. Now again, if you're talking about date, the date has nothing to do with the price of the property. So we can skip this off as well. Distance from CBD in kilometers, distance from the center of the capital city in kilometers. So this will have an impact on the price. Places, houses which are built in the center or which are there in the center or the capital city will ideally be priced, will be more expensive than the houses in the far off areas. Region name, the region will also have an impact on the price. Property count, number of properties that exist. So if it's a very deserted place, only few properties have come up, the prices will ideally be low. But if it's a property settled area where there are many such properties, then ideally it will have an impact on the price of the property which we are trying to determine. Bedrooms will have an impact on the final price. Bathroom will have an impact. Car spots will definitely have an impact. Land size will have an impact on the price. Building area. So there is the building area too, which is a built area, and then the square feet area. Both influence the price. Year built, year when the house was built. Again, tells about the age of the house. It's built long back. It's an old house. Then ideally, it will have an impact on the price. Council area, governing council, they have a major say in the prices of the properties in a particular area. So again, council area will have an impact on the price. Latitude, the geographical location of the house. Longitude, geographical location. Now, the geographical location of the house will not have an impact on the price. Now, as we understand each of the variables, we have an idea of which variables to include in the analysis and which variables to omit. That is the purpose of giving a data dictionary. Okay, now first let us import the data. So we'll go for importing all the packages. So import NumPy and the basic libraries which you always import. Import NumPy, import Pandas. Right? So these are the packages which you always import. Now let us import the data from the file into a data frame. So data equal to pd dot Melbourne housing data. And now let us print out the top 5 rows of our data set. So these are the top 5 rows of our data set. So we have suburb, address, rooms, type, price, method, synergy. So all the variables which we talked about are available. Now we do not need all the variables. We have already said we'll be skipping off the postal code. Postcode is not required. We have a variable called postcode. Address is not required. Date is not required. And price is my dependent variable, right? That is what we are trying to predict. So as there are too many variables, 21 variables. So let us list down all the variables first. Then we'll see what to include and what to exclude. So columns. Now we have got all this suburb, address, rooms. So let's try postcode. Okay. Postcode we'll delete. Address we do not need. Postcode we do not need. Then date we do not need. Latitude, longitude we do not need. Apart from that, all the other variables might have an impact on the price, so we'll include all. So the first set of like data cleaning or feature selection can be done if you understand your data well. So let me update the data which we'll be using. So from data, either I can subset like we did yesterday, or we can drop the variables, right? The first variable was date. So we'll take up date. Second was postcode, does not have any impact on the price because we have the location, region name. So postcode will not be of much help. Then we have date. Okay. Address, right? Address also will include. Address. Okay. Then we'll have latitude. Then we'll have longitude. These are the variables which we need to remove. But these are all columns, so we'll have to specify that we are dropping columns. That is all. From the data set, we'll go with the shape. Check it. We'll check it once, right? How many total number of variables we are including here. So I'll go with shape. So we have 16 variables now. We had 21 variables. So we dropped 5 variables. Next step. So what are the basic checks which you do? Dataset.shape, which we have done 34,857 rows and 16 variables. The other checks are what? We will go for dataset.info first. Give us the correlated information. Okay. 34,857. And we have few missing values for price, missing values for bedroom, bathroom, car, price, building area, year built, council area, region name, property code. Lots of missing values. And we have object variable. So how many objects? 6 object variables. Now these are all the variables which we want to include in an analysis, right? So all the object variables means the categorical variables. We'll have to encode it. We'll have to convert it to numeric so that we can include the data information in our final data set. The machines will be able to interpret the information. So encoding is required. Missing values we already have. Now the only thing which we have to do is check is whether there are duplicate entries. So how do we check for duplicate entries? Dataset.duplicate. Duplicates to 191 rows. So we'll drop the duplicates. Drop duplicates. So if you're not sure of the function, what will you go for a tab? It will give you the idea of what the function is. And then within the parenthesis, what I'll do is I'll say in place equal to true. Now, why do I have to do that? Because that will make the changes permanent. That will drop the duplicate values permanently for the data set. So drop duplicates in place equal to is retain the unique rows. We are making the changes permanently to the main data. Now, okay, so we remove the duplicates. Now the next step is we have missing values. We'll check it once more. Dataset.isName.sum. And we have a lot of missing values here. Okay, now how do we treat missing values if we are going for what are the different ways of treating missing values? Do we have an idea how to treat missing values? We usually compute we do not go with the count of missing values. Usually the best way to detect and treat missing values is to find out the percentage of missing values. Yes. We usually go for the percentage of missing values, not the count. Replace this. So we go with the percentage of missing values. Usually either I'll drop the rows if the count is very less. So go with always the percentage of missing values. Whenever you are, say, detecting missing values or treating missing values, go with the percentage. If the percentage of missing values is less than 20%, you'll drop the rows. If it is greater than 20% but less than 70%, you'll impute. And if it is greater than 70%, then you'll drop the variable containing missing values. Right? Because if a variable contains more than 70% of missing records, then it has very less information. So we can always drop the variable from our analysis altogether. Okay. For this case, now so we are talking about average. Yes, we will impute. So if say we are imputing the missing values, you can find out the percentage here as well. So if I just do this, it's in a sum, that will give me the count. Now to find out the missing value percentage, put this in a expression divided with dataset dot shape, and I want the first output of the shape attribute, and then I'll multiply it with 100. That will give me, now you can round it off. If I do a round off, it will give me better numbers here. Leave it like it is okay. Interpret from here. 0%, 0%, 21%, 23%, 60%, 55%. Ideally, what is 60%, which I said greater than 20%, less than 20%, I'll drop the rows containing syllables. But if it's between greater than 20% and less than 70%, then what do? We impute. Greater than 70%, we'll drop the variable. So all the percentages which you see here are all greater than 20, less than 70. So we'll have to impute. Now, when we're imputing it, then the next thing is, how do we impute? Yes, with the average or the mean. It's not always with the mean. We also impute it with the median. The safe thing to do is to impute it with the mean, which is generic. But usually you need to check the distribution of the variables which show outliers, means which shows missing values. See the variables we have: bedroom, bathroom, car, land size, building area, year built. You check the distribution. If the distribution is asymmetric, that is not symmetric, then we'll impute with the median. The median is a better representative for asymmetric data, which is not normally distributed. We go for the median as a standard representative. So it's not always mean, it is median, provided we know the distribution of the variables. Okay, that is for numeric variables. Now for categorical variables, what happens? We impute it with the mode. Not with the mode, with the first mode, ideally. Data can have multiple modes. We always do the imputing with the first mode available. So this is the data, now we have to impute it. Now checking the data types of the variable. How do we do that? We go for dataset.dtypes. And that gives you a clarity of each of the variables data type. Now I've got missing values in price. Price is my dependent variable. So ideally I cannot impute the missing values for price, because imputing means I'm filling up the missing values with a representative value. That is imputing, right? Now, for the dependent variable, we should not be doing a missing value imputation. If the value is not present, we'll ideally drop it. And it has got only 21% missing values. So we can always drop it. Okay. Before going with price, the dependent variable, check on the independent variables. That is where we usually do the imputation. So if I check for bedroom, that is the first variable with missing value. It's a float variable. So numeric, so we'll go for missing value imputation with the average. The next is bathroom, which is again float, car, which is again float, land size float, building area float, year build float. All these are float variables. So we'll apply the same method. Like I said, here we are going for average, but that is ideally not the correct method. You need to check the distribution of all these variables first, the data distribution. Then go with the appropriate representative before using mean as a standard method. So for now, let us go for mean. Let us do this task. We have which variables? We have bedroom, bathroom, car, land size, building area, and year built, right? These are the 5 variables. I'll highlight it. So what we'll do is, we had used this subplots, right? And we have found, okay, how many variables? I'll tell you the axis division. So 1, 2, 3, 4, 5, 6, right? Ideally, we have 6 only. 1, 2, 3, 4, 5, yes, 6. I'll give you a task now. Check the distribution of the 6 variables using the subplots function. See, the code will remain the same. In the previous case, when we are doing multiple linear regression, now we have got 6 variables. So how many divisions do we need in the subplot? If I split up my plotting area, right, for 6 plots, I'll have to find out, right? So I'll split it up this way. Either way, you can do. So in this case, how many rows have I taken? 0, 1, 2. How many columns? 0, 1, 2, 3. So when you're splitting it, you go for, rather than 2, 2, you'll go for 2, 3. Means I'm taking 2 rows and 3 columns. When you go for the hist plot, ideal because these are all numeric variables, so you'll go with the same code. Only the axis reference will change. They have given 0, 0. This is 0, 0. For the next plot, it will be 0, 1. For the next plot, it will be 0, 2. Then 1, 0. 1, 1, 1, 2. That is only what is going to change. And the variable names. Please do it. Give me the thing. What are the variables? Okay. Check the distribution. So that the question is check distribution of the variables. I'll put it down so that we can impute the missing values right. So what are the variables? I'll list down the variables here. The variables are bedroom we started off with. So bedroom total it will be 6. Bedroom, and then we have bathroom, then we have park, then we have land size, then we have building area, right? Building area and year build. So check the distribution of all the 6 variables, and then we, rather than blindly going for mean, which is wrong, this is the right method to do it. 1, 2, 3, 4, 5, 6. That is what. Go with the code which we did yesterday with his plot in subplots and modify wherever required. If you're not doing it parallelly with me, you do not have to do all the steps. You know what code we used in subplots. I have told you what axis you'll go for. Rather than 2, 2, you'll go for 2, 3. And then you'll change the position of each plot. Like I had done in the previous case, 0, 0, 0, 1, 1, 0, 1, 1. Similarly, you'll do for this plot. I have given you the references too. Please do this. Let me know once you're done. Check the code. I'll paste the same code in this notebook. And when I say suitable representative, once we run the code, then we'll talk about how to choose the right representative. Contrary to popular opinion, which we have here, is average. Okay, so let me keep it as a question. Let us paste the codes. Very nice. Okay, let us, but I have to change the data set. The DF to data set. Give me a while. Okay, no. Yes, we are getting all the plots accurately. Let's check this. Would we have it done right? No. Rather, all the variables, that is the generic idea which we have. Replace it with mean, replace it with mean. And that is ideally not correct if we do that. Bathroom, still we can think of it. A bathroom cell, okay, there are 0, 2, 3. Now, at least bedroom, bathroom, car is still doable. But building area, land size, year build, totally asymmetric distributions. At least bedroom, bathroom, and car still makes sense. But year build, building area, and land size, asymmetric distributions, totally. These are all our asymmetric distributions. Bedroom, bathroom, car, these are positively skewed. What about land size positively skewed, building area positively skewed, year build negatively skewed, right? So ideally, for every variable, we need to do the imputation using the median. Apart from year build, which is negatively skewed, all the remaining variables are positively, extremely positively skewed. The longer tail, if it lies to the right, that is positively skewed. If it lies to the left, it's negatively skewed. So we'll put it down here. And when you use mean, now you know I'm not writing it. When do we use mean? When we have normally distributed data. Okay, now let us go with the imputation. Imputation will be similar. And in same course, we'll just copy paste, change the variable names. So imputing. Data set now will be again with the variable names. Slice out the variable names. Let us copy the, I'll copy the variable names that are. One works. Data set. Modify data set. In this series, we'll go for is NAs. Okay, sorry. There will be NAs. We'll fill up the NAs with data. Then what we'll do? Close this. Now we will copy paste for the rest of the video. How many? 5 times. Then the last one is year build. Now let us check for missing values again. So price we have missing values, and we have got council area, region, and property count. Now we cannot impute the missing values for price. So what will we do? We'll just go for data set. Out of 37,000 rows, nearly 34, we do 7,000. No, not a problem, and we do not have a choice here. It's 21%, so it is good. In place equal to true. Make the changes permanent. Now let us check the shape of the data. Dot shape 27,000. Okay. Okay. So this is done. Next is what once we have done the imputation of the missing values. Now let's go for a check again. Data set dot. Now next step is what? We have the object variables, right? So we'll have to encode it too. So let us encode the object variables in our data set. Okay, so what is the simplest way of encoding? We can do it 2 ways. One is using label encoders, right? Label encoders will do what? It will not create extra variables. It will encode the variable itself by the labels, by the names. So say in this case, we have object variables are, say, region name. So it will not create a separate variable for each category. The region name is a categorical variable, right? So it might have several categories. Now what it will do is it will not create a separate variable for each category. It will directly encode the categories within the variable. That is label encoders. What is the most standard method which we usually use? That is dummies. Dummies will do, okay, people, what are dummies? Yes, people, what are dummies? Yes, if it would have been a normal distribution, we would have taken the average mean. For encoding, what is the difference between dummies and label encoders? Okay, label encoders you do not know. What happens in dummies? Yes, it is one of the methods of encoding. Like label encoders are also a method of encoding. You can use a map function for encoding. There are several ways of encoding. Now, how are dummies created? What happens to the feature count in case of dummies? And we have got 5 voters, okay? And there are 3 political parties. The first one is Republican. Second one is Democratic. And you have to predict the election results. Name of the political party is required, right? We cannot omit this variable. If I am asked to predict the results of the election of the elections, yes, then I'll leave the names of the political party. But when I go for the names of the political party, I've got these string values, category. It's a categorical variable. And how many different categories we have? How many different political parties we have? 3. There are 3 categories, right? This is a categorical variable. Now, but if I write Democratic, Republican, and Independent to the machine will not be able to interpret that information. So what do I have to do? I have to assign it to a number. So I'll say Republican is represented by a particular number, which machines can only interpret numbers. So I'll replace the name of the category by a number. Say this is 0, this is 1, and this is 2. Python starts counting from 0. So it will assign 3 numbers. Now Republican will be represented by 0. Democratic will be represented by 1. Independent will be represented by 2. Now, before we do that, let us call it D1, D2, D3. This is D1, this is D2, this is D3. What is D1, D2, D3? The representation of the category. So this categorical variable has 3 unique categories: Republican, Democratic, Independent. What is D1? D1 will be representing the Republican category. D2 will represent Democratic, D3 will represent Independent. Okay. Now we have got 5 voters. Say 3 voters we have. The first one votes for Republican Party. Second one votes for Democratic Party. Third one votes for Independent Party. So we have to capture this information too. If we have to predict which party will win, so we have to capture the voting information too. But the machine will not understand what is Republican, Democratic, Independent. So in this case, say the first person votes for Republic. Then which variable will be present? Then D1 is present to it. Democratic, D2 is present. Independent, D3 is present. So what is D1, D2, D3? These are the dummies. What are dummies? Dummies are numbers. It's called a dummy because it does not reveal the actual information. What it represents is an information which is, say, a representative of the actual information. That is why it's called a dummy. Now, because the actual information will not be interpreted by the machine, so the dummies will always have a numeric value. The purpose is so that machine can interpret that information. So dummies will always have numeric positive integer value on this. Now in this case, say when we create dummies, then we are creating extra variables too, right? If this is the political party name, it will be, say, party name. This is the name of the variable. This is one column, right, which has 3 different answers: Republican, Democratic, Independent. But the variable is one only, party name. Now, when I'm encoding it, instead of one variable party name, I'm creating 3 variables. The first one is D1, second one is D2, third one is D3. I'm creating 3 separate variables. So instead of working with 1 variable, I'm working with 3 variables. I'm increasing the feature count. So to prevent that, what do? We keep the base dummy as 0. We do not create a dummy for the base category, first category. Now, how does Python decide which is the first category? The 3 categories which we have is Republican, Democratic, Independent, right? Now go with the alphabetical order. D comes first in the alphabetical order. So this will be treated as the first category. So when we are creating dummies, we usually create more features. So to prevent that somewhat, we do not assign a dummy to the base category. Now, how will that solve the problem? The problem will not be solved. Ideally, we'll still create more features than the variable itself, more features here. But at least we'll reduce the increase in the features. Now, what happens here is, say, Democratic is a base dummy. So I do not create a dummy for Democratic. I create a dummy for Republican and Independent. Now, how will the machine interpret the information? We say the first person has voted for Republican, right? So if he has voted for Republican, then D1 is equal to 1. Because this dummy is present. What is this dummy representing? Republican Party. So for the first person, D1 is equal to 1. For the second person has voted for Democratic. So Democratic dummy is a base dummy. So if he has voted for Democratic, he did not vote for Republican, neither did he vote for Independent. So D1 will be 0 and D3 will be 0 too. Why zeros? Zeros means Republican Party is not present in the second case. Neither is Independent Party present. So both the terms are 0. Then what is present? The person has voted for at least one party, right? If two parties are absent, then he has obviously voted for the third option left, that is Democrat. If the person has voted for the Independent Party, then what happens? This term is present. So even if I do not create a dummy for one category, the machine can interpret that information for the missing category. Because the dummy for the missing category, if the missing category is present, base category is present, then the remaining dummies will be 0. When we create dummies, if k is the number of categories, the number of dummies is always equal to k minus 1. So I've got three categories. How many dummies did I create? D1 and D3. That is the concept of dummies. Now the problem is, even if we are creating dummies, the feature count will still increase. But we'll somewhat try to minimize it by not creating a dummy for the base category. But we'll have to encode this because we'll be including all these features in a final analysis rate. So we'll have to create dummies. The feature count will increase. And that will increase the problem of multi-coding it. And it will make your model more complex. So let us first do this. So we'll be creating dummies. So I'll be updating my main dataset first. Dataset is equal to, how am I updating it? I'll say PD dummies. I'll create dummies for dataset. I'll say drop first equal to 2. Okay. And I'll say D type equal to integer. I'll explain. Whatever is there, whatever we are doing on the right hand side, will be updated in the main dataset on the left hand. Now, we are creating dummies for which dataset? For dataset. Drop first equal to true means drop the first category. Do not create dummy for the first category is which one? The base category. D type equal to integer means what? When we are creating dummies, usually the presence of a category or the absence of a category is revealed by true or false. That is Boolean values. But Boolean values is not something which we want. We want integer values. That is why we specify data type should be integer. Otherwise, we would end up with Boolean values like true and false. I'll display the two records here. See the count of the column 746. Let us go with the data types simply. Data types. The different 746 variables. It is not giving you all the variable names. Let us go for info. That will give you a summarized view, so you'll be able to understand. Summarized view, info function is 746 entries. 746 columns we have. Rooms to region name. What are the final data types? Summarizing. 9 float data types, 736 integer data types. 1 integer data type, 737. And out of this, 9 are float variables. So in totality, all the variables, all the 746 variables which we have are all numeric. But why did we get such an increased count? Because the categorical variables have several categories. And for each category, barring one, dummies are getting created. A new variable is getting created, which is representing that category. So what is the final shape of the data set we have? That is huge. Going by the number of columns, we end up with 594 and 746 variables. Now, the problems of multiplicity might happen. Overfitting will always happen with 746 variables if we are working. And the problem is we cannot delete either of the variables here. We will not start off with the final ridge and lasso. Yes, we can do a simple linear regression. That is always doable here. But we will not start off with the main concepts. We'll reserve it because we will not be able to complete given the time. Eliminated variable. Yes. Now till what we have done.
Now we have come to the end of the session, and I hope so you would have got a brief idea how to use Python in machine learning. I hope so you would have liked this video. And also guys, do not forget to hit that subscribe button, click the bell icon such that you don't miss out amazing tutorials like this. Thank you guys for watching this video.